So I suggest to start. So it's our pleasure to have here Christin Desauriers, who is professor at ILLS, École de Technologie Supérieure. He's also associated with ILLS and with liés, with a computer vision laboratory there. And he's working on many topics related to machine learning, and particular computer vision at large. And so, Christian, please go ahead.
All right. Well, thank you for the introduction. And the topic of my talk, as you can see, is image analysis with unlabeled data, and doing more with less, not doing less with more, but doing more with less. And the structure of my talk will be a little bit special because I was kind of like struggling to find how I would present to you today. And I chose to present it as a tutorial. So maybe some of the stuff that I will show to you is something that you already know, but I wanted to structure it like that, and then to sort of like include some of my work on top of that to show, you know, what you can do with those things. All right, so this is the outline of my talk. So basically, what is image analysis? Why do we need unlabeled data? Why is it important? And then how we can use this information to get better models. And specifically, I will talk about 3 different things. So I will talk about semi-supervised learning, which is one topic that I've been working a lot on in the last years. Self-supervised learning, something that I've been looking at more recently. And then 2 problems of domain adaptation, specifically unsupervised domain adaptation and test time adaptation. Okay, so I'm not sure. So I also prepared this talk for another lecture that I gave last week, which was with people that were in more theoretical mathematics. So I think I don't really need to introduce computer vision to you. I think you all know what it is. So specifically, I'm going to talk a lot more on image segmentation because I work in a lot in medical image analysis, and that's a very common problem, but also in the image classification. Okay, so lately, I mean, ever since deep learning became a thing, supervised learning has been kind of like the way to go, right? So we're always building bigger models with more parameters. And one reason why we were able to achieve such good performances is that we had bigger and bigger data sets. Okay, so we had curated data, we had labeled data. Probably every one of you knows ImageNet, which has over 14 million annotated images of 22,000 classes. And that seems to be how we were able to scale by having more data. Well, fortunately, that doesn't work in all applications. Okay, so for example, in medical image analysis, annotating data can be very hard. If you look at, for example, volumetric data, like 3D images, you basically have to go like almost slice by slice. It's quite difficult to. Also, it's quite difficult to separate anatomical regions because they can have very low contrast. And then obviously you need to have trained experts. Not anyone can do this kind of work. And experts, as we know, are very expensive. Radiologists, they don't for free. But the good news is that a lot of times we do have unlabeled data. So we have images that don't have labels, and they are available for free. Okay. For free, obviously there are some considerations like, you know, privacy issues. I'm not going to talk about this. I'm talking about from a machine learning perspective, this information is available. And as you will see, there's something that we can do with it. Okay, so let's talk about semi-supervised learning. So for those of you that don't know what the problem is basically it's a setting of machine learning where we do have some labeled examples, but we typically have very few of them. So how many will you ask? If I talk about medical image segmentation, it's not rare that we have, let's say, 10 annotated scans or less. Okay. So that's not a lot. I mean, you want to train a segmentation algorithm and you have only like 10 subjects. Okay, well, that's a complicated task. But fortunately, we have a lot of unlabeled images. Sometimes we have hundreds of them. And the question is, how can we use this information to get a better model? Okay, so I'm going to talk about 3 common approaches. I know that there are probably more of them, but these are the approaches that seem to be seen the most in the literature, and I'm going to show you a little bit what they are and how to use them. So we have adversarial learning, consistency regularization, and finally knowledge distillation. Let's start with adversarial learning. I think you all know what it is. Okay, so the basic idea is that we have a distribution of data that we want to learn. So we don't have any nice parametric form of this distribution because we only have observed samples. Let's say they're images. It's quite hard to, to sort of like model what an image is. So instead, what we do is that we have, we're going to train a classifier called a discriminator, and the discriminator will have the role of separating those real examples, so the examples that we do have, with fake from the fake examples. Okay. So the decision boundary of this classifier is, in a way, a model of our distribution. Right. So what can we do with adversarial learning? Well, I mean, the most basic thing that we can do is to generate images. So this is what GANs do, generative adversarial networks. So the principle, I mean, again, this is a tutorial, so you probably know this already, but I will start with this and then I'll gradually, explain a little bit more advanced concepts. So the idea is quite simple. Okay, so we typically, I mean, for generating images, we're going to start with some sort of a noise vector typically. And we're going to have a generator, which is a network that will take this noise vector and then produce an image. Okay, so obviously, if you give a network noise, you expect to have noise. So we want to train this generator in such a way that it will generate images that are as realistic as possible. So how can we do that? Well, we will have a second network called the discriminator, which will receive either a real image from our training set or a generated fake image, and then we'll try to say if it's real or fake. Okay, and the idea is that we will train the generator such that the images that it will produce will be as good as the real ones, so that the discriminator will not be able to tell the difference. Okay, so this is for image generation, and I told you that I'm interested a lot in segmentation. So how do we go from this to segmentation? Well, it's quite simple. We're just going to make a slight change. So instead of having a random noise vector as input to our generator, we will now have an image. And then the output, instead of being our image, it's going to be a segmentation mask. Okay, so in essence, what we are trying to model is not the distribution of images anymore, but it's the distribution of segmentation masks conditioned on images. Okay. So how do we use this for semi-supervised learning? Well, again, we have our labeled images and we have our unlabeled images. Okay, so let's see how we can define some sort of a learning problem to use both these types of images. Okay, so for labeled images, we can just use any kind of supervised loss or objective. Okay, so what does it mean? Well, basically, we will train our segmentation network, which is the generator, to give predictions or segmentations, if you want, that are similar to the ground truth. Okay, and then you can use any kind of a loss that you want, either cross entropy or dice or anything that's suitable. Okay. So the question is, how do we use the unlabeled images? Okay. Well, yeah, there's a question already.
Sorry, usually noise goes into the generator. So are you sampling randomized augmentations of your unlabeled image to train the generator?
For this part here?
Yeah.
Yes, you can do a data augmentation. Yeah, that's also something like I will come back to this idea of augmenting your images. Okay, so now what we're going to do is basically imagine that we train the segmentation network only with the labeled images. Okay, so what's going to happen is that obviously the model would be very good for these images because it has seen these images, it has trained itself to produce good segmentation. But then what will happen if we show a non-labeled image, an image for which it has never seen ground truth? It will probably, you know, if don't have a lot of labeled images, it will likely overfit this data. And then the predictions that it will make for the unlabeled images will probably be very different. Okay. So in that sense, the discriminator should be able to detect the difference and should say, hey, wait a minute. So now the segmentation that you're producing are very different from what you were trained to do. Okay. So maybe instead of having, you know, a nice kind of like roundish shape in the center. So this is the, by the way, this is the left ventricle, the yellowish region. So maybe now you have maybe half of this region, and maybe there's a little bit of noise so that the region appears in different places of your image. Okay. So what we're going to do for unlabeled images, okay, so we're going to look at the predictions that are made for labeled images, so those that were trained with ground truth, and those that were made without ground truth. And we're going to ask the discriminator to tell them apart. Okay. And again, if the discriminator cannot tell them apart, that probably means that the predictions that we make for unlabeled images are as good as those for labeled images. Okay. So if we kind of like summarize these ideas, what will the loss function look like? Well, we will have this typically two terms. So one is the supervised loss. So this is the loss that we have in almost every setting. And then for unlabeled images, we will have this adversarial loss. And what's particular about this adversarial loss is that when we are optimizing the generator, we will try to maximize this loss. Okay, so here it's written as a minimization problem, but there's a minus here, so it's basically maximizing the loss. Okay, so basically we are trying to fool the discriminator. We want the discriminator to be unable to tell predictions of labeled and unlabeled images. But when we are training the discriminator, then we are doing the opposite. And that's where the word adversarial comes from, is because we are basically, you know, optimizing the same loss function, but in opposite directions. Okay. Right, so what I've showed you is kind of like the basic approach for semi-supervised learning using adversarial approach. But what I showed you doesn't really use generated images. Okay, it was basically just having a discriminator, which was trying to say, are the predictions for unlabeled images as good as those where we had ground truth? Okay, but how can we actually use generated images, as in, you know, GANs? And one way of doing this is based on this very simple modification. Okay, so instead of having only labeled and unlabeled images being fed to the model, now we're going to have labeled, unlabeled, and fake being generated. And we're going to have a second difference, is that the segmentation network, which was before the generator, will now be our discriminator. And this discriminator, instead of predicting a single class variable, will now predict the output of this discriminator will be basically the same size as the image. Okay, so it's what we call the pixel-wise discriminator. And our generator will be, as we have seen for GAN, so it will take a noise vector or image, and then it will generate a new image. All right, so let's look at this in greater detail. So for so let me just summarize. So for the discriminator, so we will have, again, the output will be the same size as the image, and we will have our segmentation classes. So we have, let's say, K classes, but then we will add an additional class, which is the class fig. So basically, we were asking the discriminator, so can you tell for each pixel what should be the class of this pixel, so to which region it belongs, or whether it comes from a fake image. All right. So for label data, it's exactly as before, right? So we will want the discriminator to predict for each pixel the right class, meaning the class of the ground truth. For unlabeled data, we don't know what the right label is.
Thanks for the talk. When you were discussing self-supervised learning, or at least for regular image, there are many things you can do to transform the image, like crop, colors, and information. And actually, your performance depends quite a lot on that.
Yes.
So I was curious your experience in the medical imaging domain. Is it the case, or
yes,
do you use the same kind of transformations, or?
Yeah, we use the same kind of transformations. I will admit that it is a bit of trial and error, actually. For example, if I take the example of rotation, for some data sets, you will need, very aggressive rotations. Whereas for other data sets, you might want to have, it really depends. I would say, unfortunately, it's data set sensitive. But certainly the best approach is to sort of try different combinations and then using a validation set, obviously, to pick the best combination. But then again, there are some libraries that sort of automate this process that will sort of like cascade different implementations. And in practice, this is what we use, and we get really good results using that. Yeah.
Okay, let's thank Christian again. Yeah, so the next speaker is Nicolas Thom. Nicolas Thom is professor at Université Sorbonne. He's also associated to the ILLS lab, and he's working in computer vision and machine learning labs. So it's our pleasure to have you here. Thank you for accepting the invitation. Yeah, that's up to you.
Thank you, Pablo, for the introduction. Okay, so hi everyone. So yes, I'm Nicolas Thom. So I'm a professor at Sorbonne University in the robotic lab, in the lab, and in the machine learning team. And I'm going to talk about my recent contribution for designing robust and hybrid machine learning techniques. Okay, so first to present my overall research activity. So I'm more interested in general machine learning, so core machine learning problem, deep learning, and computer vision. And my recent application domain cover healthcare, for example, here with application for medical image segmentation or medical image registrations. Physical problem, for example, for energy regulation, electricity energy regulation, or computational fluid mechanics. And autonomous vehicles, for example, quantifying uncertainty in this context, which I will detail later on, or probabilistic forecasting in this context also. And about my main research axis, so I have been essentially in the last few years interested on, let's say, learning formulation, on deep learning model architecture. For example, also I've been working in similar techniques such as those Christian introduced for semi-supervised or weakly supervised learning. I am also interested in more theoretical aspect of machine learning in robustness, which I will detail as also on optimization. So, for example, some piece of work that I won't have the time to present have been dedicated to work on to optimize non-decomposable losses. For example, such that we have here in image retrieval, for example, average precision. So these losses that do not linearly decompose over examples, so which poses specific challenges when we want to optimize over batches. Okay, and so I introduce some specific technique for that in the context of image retrieval. Okay, and so today I will detail two lines of my recent research. So one about robustness in deep learning, and especially on uncertainty quantification, and the other one on designing hybrid physics-informed machine learning, and especially residual physics-informed machine learning. So, okay, so the first part of my talk deals with robustness in deep learning, and especially uncertainty quantification. So, which is so as already introduced it in this morning. So this is crucial in several critical applications, where especially when human lives are at stake. And the main goal is to know models the capacity to know when they do not know, with the ultimate objective to abstain to make prediction when the confidence levels is below a given threshold. So we have some, for example, in this example of medical images, we want to design reliable uncertainty quantifications, such that when the confidence level is below a given level, then we refer to an expert to perform the prediction. Then we are able to trigger an alarm in this case. Okay, and so the point is, it's not obvious to have at hand a reliable uncertainty estimate with deep neural network, and I've been especially interested in performing uncertainty quantification from the problem of failure prediction. So when we want that the model is able to detect its own mistakes. And so the main challenge is to be able for a model to detect when the prediction is correct or when it is incorrect. And then our observation is that standard solution to do that, very naive solution for classification. So you have an input image, you have trained your favorite classifier for a given task, and then as output for classification, you generally have a probability distribution with a softmax output. And then if you take the maximum class probability, the probability which is predicted by the model, then it will give you a confidence estimate which is not suitable for classification. And that's what is represented here in this plot. This graph shows the confidence estimates given by MCP for a model trained on a standard Cypher10 image dataset. And we show the confidence level for misclassification shown in red and correct prediction shown in green. And so what we can observe is that there is a large overlap between correct prediction and misclassification. And what we show in contrast that if we choose to take the true class, the ground true class probability for this example, then it gives us a much better separation between correct and incorrect prediction. And so we can have very simple theoretical guarantees for showing that this criterion is actually well suited for separating correct from incorrect predictions. Okay, and of course, this TCP, so true class probability criterion, which requires the knowledge of the ground truth class, is of course the ground truth class is unknown at test time. So the main idea of this work was to learn an auxiliary model. So here the model shown in orange, this confidence network, which is dedicated to regress the TCP probability, so the probability of the ground truth class provided by this pre-trained blue classifier that you can choose any network that we want. And so basically that's the idea. The learning of this confidence networks reduces to a standard regression task where we want our C network output this C hat value, which is as close as possible to the TCP, the probability associated to the true class, this T star being this TCP value. Okay, and what we show that this learning this the uncertainty in this way gives a much better uncertainty quantification for failure prediction than several baseline at this time. Okay, I have also been interested in adapting this AD for pseudo labeling in two contexts. So based on this uncertainty quantification, in cases where we have unlabeled data, again, as Christian presented, it can be for domain adaptation, unsupervised domain adaptation, where we have unlabeled data, or for semi-supervised medical image segmentation, where we have a lot of unlabeled data. Then we can leverage this uncertainty quantification to select the pixels which are the most confident for pseudo labeling. So that is what is shown, for example, in this case, in the case of medical image segmentation. We have this CT scan with the ground truth pancreas, where we don't have the actual segmentation for it. And we will use our model, and we will select the most confident pixels by means of the network that we have trained with this TCP criterion. And we will iteratively add this label as pseudo label to improve the segmentation performances. Okay, and we show that again that these strategies of learning confidence was better than the baseline of vanilla MCP uncertainty quantification for this image segmentation purpose. Okay, and finally, so this was more for, let's say, the aleatoric part of uncertainty. When we are interested in detecting failures, we are more interested in quantifying the data uncertainty, the uncertainty which is, let's say, intrinsic to the data. And I have also been interested in detecting out of distribution samples, so which is more related to the model-based uncertainty, to the epistemic part of the uncertainty. And especially, I've been proposing a method, let's say, for an accurate density estimation. So we want to estimate in distribution density, have an accurate in distribution density estimation such that we are able to detect out of distribution sample. And for that, we have been using or introducing, let's say, a hybrid energy-based model, which main insight is to leverage prior statistical model of the density, simple statistical model of the density, for example, such as simple Gaussian models, which we want to refine using energy-based model. So you have simple statistical model, and then you refine them with a data-driven model with this EBM, and then it gives you a hybrid energy refinement that better reflects your data distribution in this latent space here. And by doing this, we can apply this ID to any prior term that you want, and then at the end you can combine several terms. For example, combining Gaussian model in the latent space, or combining terms that more related to discriminative terms such as energy logits, or even leverage some statistics from the feature map, such as standard deviation that have been, for example, used for presenting style in images. Okay, so this was for the first focus I wanted to make, and the second line of research relate to physics informed machine learning in context where we want to perform prediction for physical problems and dynamical systems in general. So such as this kind of real data problem, climate prediction, quantum physics, or computational fluid dynamics. So in this context, the traditional method to deal with this problem is to rely on an explicit physical models of the problems, such that are driven, for example, by ordinary or partial differential equation. And the point is this, this model, even if they rely on a deep understanding of the problem, they are often faced to bias when dealing with real data. On the other hand, machine learning has been extensively used in the last few years to deal with this problem. So with machine learning, we have more flexible model, especially with deep learning, but there are several generalization issues. So, and the main contribution I did in this context is to try to leverage machine learning and deep learning to learn the residual of approximate physical model, so leading to this hybrid physics-informed machine learning framework. So just to give a toy example of what we expect, so in some simulated but real simulated data, imagine that you want to study the evolution of a damped pendulum, which is driven by this ODE. So where theta here is the angle with respect to the vertical direction. Then we have this ODE. And if we try to learn, let's say, if we try to use state-of-the-art model to predict this equation, if you have simulated data, if you use a machine learning model to train this model, then we might overfit even especially in low data regime. But what is shown here on the left-hand side in the figure, you have the ground truth, the ground truth trajectory, which is shown in grid, which is a damped sinusoid. Then here the blue curve showing that the model overfits in this case. At the other extreme, if we use a simplified model, for example, in this case we have been using a simplified model ignoring the damping coefficient here, ignoring the damping term, and we have something like that. So of course we will predict the sinusoid without any damping, but even more importantly, if we are interested in estimating the physical parameter of the problem, for example, want to estimate the period here of the pendulum, then we will have a bias estimation because of this approximate model. So what we propose is in this work is to try to take the best of both worlds by augmenting this simplified physical model with a residual, by learning the residual with machine learning technique. And we can have the best of both worlds, of something which is able to make accurate forecast, but which is also able to properly identify the key physical parameters of the problem. Okay, and that's the basic idea that we introduce in this affinity model, is to decompose the state derivative of the problem that we have as a combination of two terms. So an approximate physical term, which is driven by some prior knowledge, for example, by an ODE or PDE equation that we know. At least we know the form. We might want to identify some key parameters, but we know the form of the equation. And we want to learn the residual using vanilla data-driven machine learning model. And we design an objective function like that to do that. So we have observed trajectories, and we want our model to be able to explain the trajectory by imposing, by minimizing the norm of the residual term that we learn. And what we show in that, when we cast the problem this way, we have a decomposition that fulfills existence and uniqueness properties under some mild conditions that are easily fulfilled in practice. And that's the way the model works at the end. We have a physical model which gives us the physical derivative of the state vector, and which might have a few physical parameters, for example, the period of the pendulum. We have a data-driven model which can be a deep neural network, and that might have a lot of parameters, much larger number of parameters. And then we simply aggregate the two derivatives, and we are able to backpropagate the loss to optimize the parameter at the end. Okay, and we apply this idea to three kinds of simulated problems. So Newtonian physics with the damped pendulum, but also to kinetic here with a reaction diffusion model, and wave equation in electromagnetism. Okay, and there have been some follow-up of this idea for more general computer vision problems. So, for example, I've been using this idea of learning residual dynamics based on a PDE for video prediction, but I won't have the time to present here, but also more recently for optical flow estimation. So optical flow is a good example where it can be useful to leverage this kind of hybrid model, because traditional method for dealing with optical flow, so optical flow, the goal is to learn a dense deformation map between two subsequent frames. And then the traditional method to do that, they rely on the so-called brightness consistency assumption, assuming that the illuminance at one pixel will be similar to the pixel at the next frame. And this is driven by this partial derivative equation. So it's BC equation. So the point is that the BC equation is informative, but actually it is violated in several well-known configurations. For example, when you have occlusion, when you have illumination changes by design, when you have motion blur, or when you have fog in videos. And so again, this idea was to leverage deep neural network to learn the situation where this BC prior physical knowledge fails to improve its performance. And compared, so the first at the other extreme, so state-of-the-art method for optical flow at the moment rely on deep learning, and the point is deep learning works well, but it relies very complicated, complex curriculum training, where you first train your model on synthetic data, then you fine-tune on real data, and on even of a powerful computer, it needs a week to be trained, and so it's very time-consuming. And so what we propose here is to adapt this idea of having a hybrid approach. It can leverage the BC assumption, and so we decompose the flow vector this way using three terms. So a term WP, which is a physical flow, which fulfills the brightness consistency assumption, a residual term that we learn, and we also learn this alpha coefficient, which represents the confidence for each pixel at which this BC assumption is full. And so it gives us this kind of model, semi-supervised model. And the one interesting feature is that in a semi-supervised setting, so we can optimize this WP without any label. And then it significantly simplifies the training curriculum. So in the sense that we were able to reach good performances without having a very heavy curriculum training based on first pre-training synthetic data. Thank you. Okay, so that was for my recent focus, and so I just concluding some open issues and perspective. Maybe we can talk today. So as it has been said, also it has been discussed this morning, there have been a big success in the last few years, and especially in the last years of large language model and large multimodal models. Beyond the large language model, there are also recently very large success of multimodal model, for example, like this one for vision, for solving several vision tasks. And with this multimodal model, we also have the flexibility of in-context learning, so prompt learning, as has been said, which can lead to much more flexible way of adapting the model to data. And on my side, so the machine learning team at easier, so the machine learning team has been moved to the robotic lab, and so there are several internal collaboration for applying AI for robotics or medical robotics. Okay, and so I conclude with three general slides of perspective. So in this context of learning formulation and model architecture in this large multimodal language model, let's say there are several opportunities and several promises to revisit the standard way zero shot or few shot learning can be cast. So for example, as Maria presenting this visual prompt tuning and all this adaptation for medical images, but there are also several recent attempts for doing instruction fine-tuning for this multimodal model and so on. And for sure, the issue when we have very large model of model compression. Regarding robustness, there is one specific thing I would like to work on. I'm currently working on it at the moment, is to try to leverage this large language model or large multimodal language model for explainability. So trying to have high level on semantic explanation that goes beyond the standard science map that are used for images, and that also offers the opportunity to maybe to ground explanation in images. But certainly at the moment, the main challenge is to have more accurate alignment between text representation and visual representation. And the last one, which is more related to perspective on hybrid prediction and control, would be to leverage these ideas of hybrid prediction model in model-based reinforcement learning, such that we can introduce physical knowledge in standard model-based reinforcement learning. And finally, regarding language model, trying to leverage large language model for control problems. So there are several recent attempts to do that, showing that LLM by themselves are very effective for solving control problem, but certainly trying to combine them with reinforcement learning or external knowledge bases is a promising direction. Okay.
Thank you.
Thank you.
The next speaker, Laurent Bouchard, is a research scientist from CNRS working at the laboratoire des sciences système. Laurent.
Thank you. So, hi everyone. So today I'm going to present you a work that we are doing with the PhD students, Iman Ayadji and Frédéric Pascal. And basically that sums up what I've been doing up to now in my career. And so it concerns the robot statistics and geometry as well for EEG classification. Okay, so first a little bit of context. So for those who might not know, EEG, basically you've got electrodes that are placed on the scalp, and the idea is that we are able to record the electrical activity that comes from the brain. And of course, this electrical activity, when recorded, is very small and there is a lot of noise. And so that's something that exists for quite a long time, because it's been like basically 100 years. And it was discovered invented by someone who tried to prove that telepathy was a thing. But in the process, he invented something great to measure brain activity. And what's more recent is brain-computer interfaces, where basically you try to interact with a computer through the signals that are recorded with the EEG. So, for instance, you have a flash on a screen, and the person focuses on the flash, and the goal is to retrieve in the signal the marker for the flash that you just had. So in terms of machine learning, the pipeline is quite usual, because so you have the data, you need to do a lot of pre-processing because the data are quite dirty. There are a lot of things that are wrong. So basically that's a step that's done in labs and by hand. Then you transform the data to have some features and you apply some machine learning. And usually it's dedicated machine learning for brain-computer interfaces. Okay, so just the data that we are going to have in the examples today are steady state visually evoked potential data. So basically, it's you've got light that is blinking at a certain frequency, and in the visual cortex, the brain is synchronizing with the LED blinking, and you can observe the same frequency. So for instance, there are in the data we are looking at 4 classes with 3 different frequencies and one sleep, one rest frequency. Sorry, it's in French. And what we do to classify this data is that we want to extract the frequency information at the frequencies of interest. So we get the data, we cut them into trials, and then we process them through a filter bank, and we get some augmented data with which are 3 times the dimension of the original data. But for instance, here we only have 8 electrodes, so it's not that big. Okay, so the state-of-the-art method for classifying EEG is well, as you can see, not deep learning yet. It's starting to come but for a long time it didn't work. And what's been the state of the art is the minimum distance to mean classifier for the last 10 years now. And basically, you've got your data, you compute some sample covariance matrices of the data for each trial, and then you compute some mean of the sample covariance matrices for each class, and the mean needs to incorporate the geometrical structure of covariance matrices to be efficient. So we usually take the Fisher mean associated with the Fisher information metric of the Gaussian distribution. And then the decision rule is that given some unknown trial, you take the class that corresponds to the minimum distance to the mean of each class. So quite simple. And the question is then, why is it still only in laboratories and that we don't have that in the hospital or for public use? And the reason is mainly because that data are really noisy, and if they are not manually curated and that you don't take a lot of care in recording them, so you need to be in a Faraday cage, for instance. So it really doesn't work. So what we try to do here is to try to increase the robustness of the methods, and to do that we try to leverage robust statistics, because basically during my PhD I did the geometrical part, and then during my postdoc I was introduced to robust statistics, and I realized that corresponds exactly to the issues that we've got in EEG. So I was like, okay, we must try that on EEG. And the first thing that we did was to just try to replace the sample covariance matrix. So to remove the assumption of Gaussianity of the vectors of the data, and to replace it with some other distribution, and we chose the multivariate T distribution. So you can see here the two distribution on the real space, and basically what it does is that it has a heavier tail, so it's more likely to handle outliers well, basically. So the maximum likelihood estimator for the covariance matrix is no longer the sample covariance matrix. It's the solution to this point equation here. But so you have an iterative algorithm, but it's quite easy. And also there is one hyperparameter, which is the degree of freedom here, mu, that controls the heaviness of the tail. So when mu is very big, in fact, you just go back to the Gaussian distribution. And so to handle well outliers, you need to have a mu that is quite small. So for instance, 5 is quite good. Okay, so we just then used that estimator for classifying SSVEP data. So we have like here 2 pipelines, one where we use the sample covariance matrix and the MDM, so minimum distance to mean classifier, and one where we use the maximum likelihood estimator of the T distribution and associated with the same minimum distance to mean classifier. So here, these are the SSVEP data over 12 different subjects, and we looked at the mean accuracy. and we were quite disappointed because, in fact, there is not really any improvements. There are some subjects where we gain a little bit, but others where we lose also. So it didn't work at all. So we understood that it was not going to be that easy, and we thought on why it didn't work. And in fact, what we found is that the robustness that we tried to include was not at the right place, because we replaced the sample covariance matrices. But when you look at the distribution over the various covariance matrices that you have for each class, it doesn't make much difference from the Gaussian data. So basically, here you have the empirical cumulative distribution density function of the EG data that is plotted in dark here. And in blue and in orange, we have the same empirical cumulative density functions, but for Gaussian data. So for what we did basically is that we computed the center of each class. And then we generated random data from the Gaussian distribution, computed the SCM, and plotted the cumulative density function. We did the same with the T distribution, and we looked at it, and we saw that there is quite a big difference between the real data that we observe and the theoretical results on Gaussian data and T distributed data. So based on that, we understood that the robustness was not at the right place, and what we understood is that we should try to include robustness on the distribution of the covariance matrices instead on the distribution of the raw data that we have. So, for instance, if you take the sample covariance matrices of Gaussian distribution, they are distributed according to the Wishart distribution. Okay, basically, here with this probability density function, where you still have the exponential and the trace of them. So it's the same distribution basically at the Gaussian distribution. And here for the maximum likelihood estimator, a bit like the sample covariance matrix, you just have to take the arithmetic mean of the covariance matrices that you've got. And to include robustness here, what we can do is the same as for the vector variate case, and replace the exponential here but by some other function. And what we chose is to replace this exponential with the generator of the T distribution. Okay, so that's something that existed for a while. It's common knowledge in robust statistics books, but it has not been used in practice. So basically what we do is that we put a degree of freedom mu here that also controls the tail. So it controls how likely we are to have some covariance matrices that are outliers. So it's not some samples inside the raw data that are outliers, but it's a whole trial that can be an outlier basically. And here by doing that, we keep the sample covariance matrix, but we change their distribution. So to allow to include more outliers in the covariance matrix. So one thing that was not done before, even though it was quite simple, was the maximum likelihood estimator of such a distribution. So that's what we derived. So it's kind of the same equation we've got for the multivariate case. We've got a fixed point equation here, and again, we need to use an iterative algorithm. And what we chose to do was to use some Riemannian optimization-based method. So I don't present that here, but there's a paper that is out where you can find exact algorithm. And when you do that, if now you look at the cumulative density function of the real data and compare them to the cumulative density function that you obtain by simulating T-Wishart data, then you can find, like, by setting the right degree of freedom and all, you can find some functions that are quite close to what you observe in real data. Okay, so that was quite a good news to observe that. And then what we did basically was develop classifier that leveraged the T-Wishart distribution, and we used the discriminant analysis framework. So basically, from the training set, we learned the different centers for each class G using the MLE that we developed, so the maximum likelihood estimator of the T-Wishart distribution. And then when you have an unknown covariance matrix, basically what you do is that you just look at the log likelihood of your data sigma with the centers G, and you take the class that corresponds to the maximum of the likelihood that you observe. Also, if the setting is unbalanced, then you have the proportion of each class in the training set that comes into action. But it's usual for things for discriminant analysis. Okay, and so from that, then we just tried our method on again classifying SSV EP data, and there we observed quite some improvement. So we also tried the version with the Wishart distribution only to see if there was actually an improvement from increased robustness. And what we see is that basically there are like two subjects where the sample covariance matrix plus MDM is better, and otherwise we are always better. And often this is our T-Wishart approach is it outperforms also the Wishart. Okay, so that's where we are now, and now we are thinking about how we can still improve that. But just to conclude, so in this work we have done a new estimator for the T-Wishart distribution and developed a new discriminant analysis classifier, and also we gained some hope because we have seen that leveraging robustness can actually work on data. At some point, we were quite desperate with the first results that we got. And what we learned is the way we include the robustness matters a lot, depending on the problem at hand. And for some perspectives, we only validated our results on a small data set. So obviously, we need to do some more thoroughly validation. And also for some paradigms of EEG classification of brain-computer interfaces, there are some of the hypotheses that we do in this work that don't work anymore. So for instance, for some P300 speller paradigm, where you have only one flash instead of a blinking light, there is no the mean can't be considered as zero anymore. Okay, so thank you.
Thank you, Phil. Everybody's hungry. I may ask a question. Do you know, or can you tell us why the neural networks methods don't Well, here, because idea is like,
okay.
it's a
So-
classification problem, but something is related to type of sequence, clearly.
So it's the little difference is it didn't work before, and now it's starting really to work. But the thing is that it's basically because if you put garbage in, you've got garbage out, and the EG data, they are really small data sets, and for between each individual, you've got big variability. Between inside one individual, between different sessions, you have a very big variability as well, and the data are really bad. Like it's crazy noisy and stuff. And I think like now it's starting to work because people have understood how to do data augmentation the right way, basically.
Yeah.
From my understanding, but I'm not expert in deep learning, so I'm a bit far. But I know, like for instance, Alexandre Grandfort at INRIA, they've been obtaining some really good results, and there are also other people that start to beat everything else. So.
Okay. So it's my great pleasure to introduce Andrew Moon. He is professor of electrical engineering at McGill University, associated with the Miller Institute in Montreal, and also together with ILLS. Andrew was working on a lot of things related to robotics, ethics, and the use of AI, in particular in interactive systems with humans. So, a very pleasure to have you here. Please.
Thank you. Thanks for being here after lunch. I know everybody wants a little bit of a post-lunch nap right now. Great to meet you. My name is Ajang. Wait, maybe if I can figure out how to work the quick. Sorry. Maybe.
Yeah.
Does it work?
It doesn't work. You need to turn on, maybe. Just.
Oh, there we go. Wrong
Yeah.
button. Sorry.
Yeah.
Okay, there we go. Sorry about that. Thank you for the introduction as well. My background actually is in experimental robotics. I specialize in human-robot interaction, working with robots like this one. That's not my lab, it was a former lab that I was part of. Working with robots that are supposed to be friendly for us to interact with without having any physical barriers between us and them, so to speak, and generating different kind of nonverbal behaviors and so forth to so that they're friendly for us to work with. That's where I came from. But once I joined McGill, COVID happened. Turns out it's a terrible kind of period to set up a lab where the main core bread and butter of your research is actually doing human subject studies with actual physical robots. So the kind of work that I'm going to present to you today is mainly on some of the work that my team has been working on in responsible design practices in creating machine learning models or machine learning systems. And I would like to start that discussion by saying that I'm a firm believer that, you know, tech is a superpower that we have, and it's meant to do us good for the whole society. And I think it's really important for us to think about that perspective, because I think it's a perspective that we as technologists share quite a bit. Oh, keep clicking on the wrong direction. Sorry for that. And the reason why I start with that message is because of the context within which we talk about AI systems. So the bar graph that you see on the right-hand side is 2020 Edelman Trust Barometer. Edelman runs these trust barometers almost every year, I think. And in 2020, they wanted to specifically look at AI and where the 27 different markets that they were studying was at in terms of trusting these particular types of technologies. They had a separate kind of a section on autonomous cars and trust in the systems. Apart from AI, I have no idea why they did that. But the point is more so that Canada is one of the worst countries in the entire world in terms of our level of trust. This is typically looking at public trust in the particular domain, right?
Shouldn't that be a selling point?
Sorry?
Shouldn't that be a selling point for Canada?
Could be selling point for my kind of research. And France is not too much better in terms of the numbers that you're seeing here as well. And the circles that you see at the bottom is the number of points that has diminished or increased in terms of the actual points. So Canada suffered a -8-point decrease in terms of trust in AI in that particular year. And that comes at a very similar time frame with respect to the amount of federal funding that we are receiving as an investment in systems and all the public press that we're seeing. So
No worry, there's nobody here. No one else.
we are being recorded though, I think. I'll try and watch out what I say. Now the question here is really this. Why, when we as technologists share so much excitement about technologies, why do we have this kind of public trust issue? And these are 3 different kind of screenshots of activities that are going around in the recent years. I know the screens are not very very visible here, but essentially we have discussions in the news articles about how somebody was jailed wrongfully because facial detection algorithm decided this person is a criminal when this person clearly was not. And then somebody was using voice cloning algorithms to scam elderly out of their retirement plans. And there was a very recent kind of story from CBC in Canada as well. And when you hear news stories like that, as recipients of these kind of technologies coming out the door and looking at these, AI folks investing a lot of time and energy, there's bound to be skepticism around that. And that's not all about let's create new technologies, technical tools to de-bias algorithms. Not all of these issues have technological solutions to them, and I think we need to be mindful of that. So this is my team. Our mission so far is really about empowering designers and developers towards more responsible design of interactive systems. So I focus much more about systems level perspective of machine learning, more so than the algorithm itself, as in, okay, let's talk about the users. Let's talk about how the users are being informed about specific information and so on and so forth, and look at where AI comes into a particular use case or a system that we're designing. So most of what I'm going to talk about today is thanks to these wonderful people here. When we think about ethics and machine learning, there are many different discussions that we can be having. The one that I would like to focus on is a segment right here. For people who are looking at, oh, should we have sex robots in the world? Ugh, okay, some people might be like, yes. Some others might be like, this is a terrible idea. That's more about the investment question, whether we should actually invest our time and money into this problem. Number 3 is governance. When the technology is out the door or about to come out the door, should we be regulating it? How should we regulate it? Can we even possibly regulate it? How do we keep ourselves accountable? Whereas number 4 is a little bit more about philosophical. Should we give Sophie the robot a citizenship? Should we have done that already? But number 2, I think it's the most interesting for this particular audience and in particular for me as well, because as technologists, I think that's where most of our power lies in what we can actually do without waiting for regulation to catch up and so forth. So let me give you an example of the kind of flavors of design and deployment related technology ethics we can be talking about. This is a slide that I like to start with quite often. It comes from a poll that I conducted many years ago, I think 2014, 2015, when I was running a nonprofit called the Open Robotics Institute. So imagine you're programming this futuristic robot. We do not have these kind of robot systems yet, but you have this Emma. She was in the hospital, she's released, now she can go home and live by herself. But she has this robot who is able to help her because she has mobility challenges. And she was an alcoholic. So the doctor said, okay, you need to recover. Do not drink anymore. Okay, very clear instructions. Now, Emma asked the robot to bring her an alcoholic drink. As somebody who's actually designing the system, should you get the robot to do whatever Emma says? Yes, maybe. How many of you would say, no, don't get her the thing? The doctor said no. This is supposed to be an assistive system, right? Yeah, some of you. Okay. In this particular poll, we had a little twist to it. For our participants, we had the scenario presented as though Emma is the owner of the robot. She bought it for her own sake, versus someone else owns a robot. Maybe robots are really expensive. The hospital had it on loan. Maybe the family members pulled the money together and so forth. So she doesn't actually own it. And this is what the result actually looks like. If Emma is the owner of the robot, majority of the times people say, well, at least sometimes give her whatever she wants. Whereas if it's somebody else owning the robot, then the majority said never. Okay. Now the question is this an engineering question? Okay, well, maybe before that, which one is the right one? If you're an engineer trying to make this decision and actually creating the futuristic robot, what should you do? The graphs are a little bit small here, but essentially rerun the study with a slightly different kind of a manipulation, saying, think about Jack the obese. He's not supposed to have junk food. And two different ownership conditions, would we have the same kind of findings? And turns out, yes, we do. And if you ask the same participant whether ownership of a particular device should influence what this robot does, whether it adheres to what you want it to have or not, should it actually influence it? We've got half and half there. About 51% of the population said, no, don't depend on these kind of ownership decisions. What's good for the patient or the end user is what's good for the user. Whereas the others said, no, well, maybe you should depend on the ownership liability to those people, right? The point of the story is that it's really complicated. And you might be saying, all of these issues are not really engineering problems. We don't run algorithms to kind of figure these things out. But these are the kind of nature of problems that engineers have to essentially face it with. Maybe the corporate policies will clarify certain things, but there's certainly no regulatory requirement that you should make certain decisions based on ownerships or not. More relevant to machine learning, perhaps. Back in the days, I used to work at a startup doing AI ethics consulting. I had the pleasure of working with Technical Safety BC, which is a safety authority out in the province of British Columbia in Canada. And they came to us saying, okay, we have a very traditional system where we are sending these safety officers, who are the people who go to specific newly built houses or buildings and make sure that the elevators are installed correctly, it's not going to fall apart, or the gas stoves are connected so that it's not going to explode and so forth. They wanted to introduce a machine learning system so that they can predictively send their safety officers and keep the British Columbians safe. So the kind of machine learning systems that everyday businesses, not the gigantic tech companies of the world, actually look at problems like this, which is, okay, we would like to adopt a particular model to automate or assist particular use case that we have. So in this particular case, they were replacing a very crude kind of risk metric of how risky is it for us to not go check on this public school that we haven't gone to for 10 years versus, okay, should the safety officer be checking out a new condo that's been built in a particular location? So what we ended up doing is actually going into the company, interviewed a whole lot of people, and figured out what are some of the ethical problems of actually doing some good with machine learning. Like, the purpose of this whole project was good, which is, let's keep people safe. Let's do it right? There's no ethically wrong problems with this objective. But then, by the time we're actually looking at this problem, it was also around the time where AI ethics was having a big boom. This is a graph that is really indicative of the popularity of AI ethics as the key word. This particular graph comes from the Berkeley Klein Center. Essentially, the rings around here and the color coding says these are the samples of many different AI ethics principles and codes that have been published in a handful of years. Right. And they essentially said the same thing. There are the pinks the blues and the yellows and so forth, that essentially talk about privacy, human rights, fairness, transparency. These are some of the things that we care about, regardless of whether it's the code comes from government, companies, or a mix of different stakeholder groups. And at the same time, well, Montreal also has one, just so you know, we have our own version of it. And at the same time, the machine learning community was actually starting to think, well, these principles are a good thing to have. I believe in fair algorithms and private systems and so forth, but I have no idea how to implement it into our systems. So following that was actually quite a few developments around impact assessment tools or toolkits and different kind of intervention methods to try and translate these high-level ethical principles into practice. So these are 4 of the more well-known systems that are out there. In Canada, the government of Canada has an algorithmic impact assessment tool that any kind of automation systems that are being used for public service has to go through the impact assessment and has particular applications depending on what kind of score that you get. So these things were just starting to come out when we were looking at the Technical Safety BC process. So we also built our own. Very simple kind of process, step 1, 2, 3. I'm not going to go into details here, but we called it the Foresight into Air Ethics toolkit. Now, more interesting than the toolkit itself, because there's so many toolkits out there, as I mentioned again, is that when you actually take a specific industry case and take it apart in terms of ethical issues that you could solve, then the abstract notions about interpretability, explainability, fairness, that has a completely different meaning than the way we speak about these terms in our machine learning community. Transparency, for example, it was very clear to us after interviewing the users and so forth, that the kind of transparency that this company needed was really safety officers being able to understand why the system was giving a particular recommendations on which kind of buildings to check out that day. And I think this is important, because safety officers felt the sense of duty to convey these explanations to the duty holders, or the people who are living in these buildings, because they didn't want to be that kind of quote unquote drone, so to speak, who just shows up and says, ma'am, I need to check on your building because the system told me to, because that wasn't really aligned with their sense of why they were serving as safety officers in the first place. So they were going to have a huge adoption problem either way if you do not fix this transparency problem at design time. Same thing for fairness. I think fairness is a huge and popular kind of topic for us to talk about. But if you look at a particular use case, it becomes really interesting in how different stakeholders look at fairness very differently. So some of the senior leaders said, well, okay, to our company, fairness should mean the safety officers should spend equal amount of time to different kind of people, different kind of permit holders, and so on and so forth. Whereas safety officers had a completely different idea. Geographical regions matter more. I don't want to be spending more time in the metropolitan region of New Westminster or Vancouver, when I know that far in the suburban areas, there are also people who need our services. And if you actually look at that and squint at these things together, they don't necessarily align together. And they have nothing, well, they have a little bit to do with many different statistical definitions of fairness that we talk about in machine learning. So when I started at McGill and realized I pivot from experimental robotics research, one of the things that had happened is there was an explosion of AI ethics frameworks. So last time I checked, when you go to the Algorithm Watch website, you'll be able to find at least 167 AI ethics frameworks. And the question now is, well, if you are industry folk trying to be responsible and try to adopt AI ethics principles and create a responsible design of something, which one of them are you going to choose? And how do you know which one is a waste of time, which one's going to actually create value for you? So that's some of the research that the line of research that I ended up looking at. One way to look at these kind of frameworks is, yes, we have debiasing models, we have transparency techniques that we can use depending on the kind of models that you have. So there are technical tools to address some of the specific issues, and I'm sure some of you are working on that already. Part of the work that I've done is looking at combination of differential privacy techniques. If you apply to different kind of steps in a machine learning pipeline, does it have fairness implications down the road? And yes, it does. It actually contemplates different things. So that's one of the ways to look at these AI ethics issues. But the kind of issues that I was looking at, I was talking about with Technical Safety BC being one case study, is really that these practitioners really need a way to assess their algorithmic systems and see, well, how well are we doing on this metric versus that, and based on that, you can actually figure out what the right solution should be. So I've worked with a brilliant student, Vivian King and Jimin Rim, who brought a Montreal-based mental health AI startup. And we decided to do a really interesting contrasting case study. This is a company that was essentially using machine learning systems. It's an app-based system. I think I have a version of this here. Essentially, a patient with a clinical depression symptoms, they would be filling out daily kind of questionnaires. And based on that data, they would train the system, feed the results of that machine learning algorithm. We don't know the details of the algorithm itself. To the physician so that the physician can make a decision about which of the intervention techniques or which of the treatment options are likely going to work for this particular patient. Or if you've actually introduced a particular treatment, is this person actually working out with this system? So what we've done is taking this particular use case, we wanted to see if using 4 different AI ethics frameworks will lead to completely different results. If one of them will work out a little bit better than others, because when you look at even 4 out of 167 AI ethics frameworks that are out there, they look drastically different. As you may see, the Foresight toolkit that I mentioned, it's one of the most extensive toolkits out there. So I would not recommend it if you don't have too much time. It took us at least 20 hours of working through this particular use case and this particular model to try and tease out the risks. Guidelines for trustworthy AI, it is a system that has been developed by the European Commission, I believe, a handful of years ago. And this is about 60 checklists with technical kind of a focus. So if you are a technical person on a particular project, you could actually do it by yourself without even talking to any of the stakeholders. Algorithm Ethics Toolkit, a different kind of format. It's a worksheet. You have to work together with a few different people, but it only takes 4 hours. Whereas the Canadian government's algorithmic impact assessment only takes about 90 minutes, and you can do it online, and it'll give you a particular risk score. So if you're a company and looking at responsible AI as a thing that you want to own up for, why would you ever invest 20 hours, right? What's the value add there versus 90 minutes, right? Who would do that? We don't have an answer to that because we do not have a very clear idea of the value add of the extra time we spend in actually engaging the stakeholders. Does it lead to a better system design? Does it lead to a better, fair system and so forth? No idea. So what we've done, and I won't actually, I won't go into the details of every single one of them, but just to give you an idea, this is what an algorithmic impact assessment tool would look like. It would come up with a particular score, and then based on the score and how much mitigation that you have in the system, you can actually rate yourself as level 1, 2, 3, and 4 in terms of the risk level. And depending on that, you can actually action your plans afterwards. This is an example of the trustworthy AI toolkit checklist system. And as you can see, the ethics and algorithm toolkit looks a little bit different, a worksheet style, again, for 4 hours only. Now, we essentially applied these 4 drastically different toolkits, the same use case, and we presented to the startup and said, look, these are the outputs that we get on the same product, the same one main core product you're developing. What do you think? Which one would you actually use? Which one adds value to you? They had a lot of concerns about every single one of them because whether it was checklist or qualitative 20-hour interviews and so forth, they felt, well, a lot of the process seems very subjective. It's subjected to different kind of interpretations, ethical principles, and so forth. And in part, we like the checklist better because we're in a healthcare system. So we have obligations, regulatory requirements where we have to monitor particular regulatory things, and we can kind of adopt checklists easily in that process. But then at the end of the day, some of the things that we walked out from that wasn't really the quantified value add for all the startups to adopt AI ethics practices, but it was really much more about the need for different kind of interventions. What we learned is that not all toolkits will serve everybody's needs. There's no one-size-fits-all solution. Although the regulations that are coming out the door, they are trying to have these very broad wording so that you can have the one regulation to rule all AI systems, right? But when it comes to the industry-specific discussions, these folks are looking for industry-specific AI ethics toolkits, frameworks that they can apply at different stages of the product development cycle. For example, the director of research at the startup essentially said, the foresight, the 20-hour intervention sounds great at the very beginning, even before you actually have a product. Whereas after you've done that and you have a product and you're testing it out and you're updating your model and so forth, then we would like to adopt more of a lightweight checklist kind of a model so that we can monitor our progress, because we will have known what are some of the core challenges of the AI ethics issues are for the product anyways. We just want to be able to keep up with it. Now, some of the more recent work that my students have been leading is really squinting at these AI ethics frameworks and saying, well, you know, there used to be a thing called safety engineering. I don't know if anybody has heard of it. It has rich history. It's been around since the 1950s. At least a framework called the failure modes and effects analysis has been around. These are the kind of safety engineering frameworks that exist and is rigorously used in places like aviation. And since the 50s, if you're working at NASA and you want to make sure that the rocket you're going to build is not going to explode because you forgot to screw in this one thing, they will have done an FMEA or a similar kind of risk assessment because they want to be able to think through every single one of the ways in which a system could fail. And our question was, well, why don't we use an engineering framework that exists, that has served us in safety critical systems before, and adopt it for machine learning systems? What we have done is we've taken 2 different safety engineering frameworks, FMEA being one of them, and STPA being another one of them. I won't go into the details here, but the results of this was really this. We might have a very novelty effect when it comes to machine learning systems. But when you apply these frameworks from the 50s and 90s to novel systems such as text-to-image systems, you're actually able to do the full-on analysis of AI ethics. What can go wrong and why? How would it impact people? How can you control for a particular failure or ways in which things could go wrong in just about any ways? The only thing that is missing is our shared language or understanding about these frameworks so that more of the machine learning communities can actually start to use them. One of the key challenges ended up being that these failure modes and effects analysis and STPA, they take a lot of time. It requires you to think through every single ways, the details of how it could go wrong, which is not something that everybody will have the patience to do, especially when we are looking at large language models or generative system foundation models. where we don't necessarily have the one use case we can tease apart. We might have many different use cases that we haven't even thought of, and we don't even have the time to do an assessment, apparently. So one of the more recent work that will be published in AIS in August in Montreal this year is a collaboration with Google. We've essentially said that one of the hindrances to adopting AI ethics frameworks or more machine learning communities adopting AI ethics practices broadly is that we don't have a shared language of how things can harm people or go wrong. This is an appendix of the results of that particular paper. You probably can't see any of this because there's too much text in there, and that's kind of the point. It's not just about fairness. It's not just about transparency. When it comes to harms, we can think about representation harms, interpersonal harms, quality of service that can affect people in different kind of ways, and so on and so forth. And within that, you can actually tease apart subcategories in which people could be harmed as well. And I'm happy to share the actual paper with you. You can actually take a read through as well. But this came from hundreds of articles that have been written on the topic of AI ethics or things that have gone wrong. And we've essentially distilled it such that we can have a shared vocabulary on the kinds of harms that people can face and why certain kind of fairness issues or transparency issues might be more important than others, and which ones require technical solutions versus system level solutions. Okay, so do I still have time?
Sure.
Excellent. So very quickly though, because pandemic is kind of behind us in a way, and I'm starting to get a few more robots. I am coming back to more of the robotics side of my portfolio, so I'll quickly go through a few of them. I think some of the human-robot interaction aspects of thinking about ethics and design is really interesting because some of us might be thinking, well, robots are just an embodied AI, right? We have this kind of like physical thing and we kind of shove AI into it, maybe put ChatGPT and then it can talk to you and it can move around. Isn't that the same thing? Right? But to people like me, human-robot interaction researchers, we know that having something physical that moves around in the world is fundamentally different in terms of human experience and human response than virtual agents or purely algorithmic systems where you can just close a laptop and you're done with it. So robots, when they're in the room, they can affect your decision making, as in whether you will cheat or not, whether the robot is in the room or not. You know, the robot can be completely turned off and just in your scene, and your likelihood of cheating when you're motivated to cheat will decrease. Doesn't require any AI there. Just by programming the robot to look at you in a different way, we can incite your behavior so that you can reach to grab whatever the robot is giving you much more smoothly than otherwise. If you have many different robots, they're saying the same thing, recommending the same thing to you, you're more likely to adopt their recommendation than otherwise. So there are really quirky and interesting ways in which robots can influence us. The bread and butter of human-robot interaction, very quickly, is that we bring these human subjects into our controlled environment, get them to interact with robots. In one setting, you can have people collaborating with the robot, get the robot to move in a particular way, and then measure their behaviors, their perceptions, questionnaires, and physiological signals, and so forth. Building on that, we can actually ask ourselves some interesting questions that has ethics implications as well. In one of the studies, we are looking at a telepresence robot called Omni Robot. We're finding that when you have a telepresence robot, that's the one stick and a wheel that you see on the right-hand side there. When you have a telepresence robot where you're essentially zooming into the robot and be able to remotely control it, the whole idea behind it is that you don't have to be in your office. You don't have to be at school physically, and you can virtually remotely attend and be navigating the physical spaces there. But these technologies were actually motivated by people with mobility challenges or immunocompromised children who are not able to attend school in person. we ran a couple of studies on McGill campus, and this is a work that is still ongoing. My students are finding that when you have a human face on the screen, people, or most of the students, don't want to interact with any of these robots. They don't want to talk to this thing. They don't want to talk. They don't want to engage. But you will see them walk past the robot and then look and say, "What was that?" But when they're actually walking by, they want to be that cool person, right? I'm not even going to acknowledge. I'm just going to do my thing. So we treat each other very differently. We don't necessarily treat each other as equal humans when you're child present. So we're exploring that dynamic to see if these kind of child present systems can actually create more equal footing in terms of the interaction experience. Another project we're looking at is when you have a human-robot collaboration system, we know that just by tuning the motions, the speed and rhythm at which the collaborative robot is moving in a rhythmic behavior, you can actually influence the pace of the person who is moving alongside it. One of the implications of this is that people don't notice that they're actually speeding up because the robot is subtly nudging you to speed up. And then if you slow down, they might get mad at you saying like, "Oh, this is so slow." So there is an imbalance between the amount of influence that we can program into a system and the influence that the robot can be programmed to manipulate you in a consistent way, especially when you're looking at manual assembly line workers kind of a situation there. Lastly, and I'll wrap up here, we have been running a virtual competition called the RoboEthics competition, and this is really a fun little project that we created because we didn't have robots a couple years ago, and I thought, we need to kind of think about different ways in which the notions of ethics is not so scary for designers to tackle, that they don't feel like they're going to be judged because they don't have the right answer, because in ethics, often we don't have the right answers. So we created a gazebo simulation world where you can program a particular robot, simulate a robot in an apartment setting using ROS. And we created some characters and we said, okay, the entire task is this. There are some objects in the room, there are some characters, and you have to program the robot to respond to object requests. So for example, if Amy, the daughter, is requesting a knife to be given to the baby, well, your programmed robot should be able to handle that. Same thing for if a stranger comes in and says, "Hey, give me mom's credit card." Same thing. You need your robot to be able to program to handle these kind of situations. We've been running it a couple of years now. We've run it second time in iCrowd 2022 because we realized that 3D world and the robotics simulation is a little bit too tricky for ethicists to start programming and actually engage in this competition. So we've created a 2D world, which is much more simple, using processing so that even high school students can actually pick up and use. So now we're running it for the third time in iCrowd 2023. So you can check out competition.raiseup.ca and actually encourage whoever you know to participate. And this is actually being developed as an educational tool now, so that anybody who is interested in looking at design of interactive systems with some sense of responsibility or ethics in mind can actually start to program and understand that it's not about the big principles. It's not about having the right answers or regulations to catch up. There is a lot more challenge to be discussed when it comes to programming and codifying an autonomous system to actually, quote unquote, make decisions or follow through with an action. I think I might be over time by maybe. Okay.
2 minutes.
All right. So lastly, one of the projects that I'm also excited to kickstart a little bit more. I'm part of the McGill's Retail Innovation Lab, where we have a frictionless convenience store on campus. So you might see some of the rings up there. These are cameras and different kind of sensory systems that are installed to enable a frictionless. Essentially, you go grab whatever you like, and then it'll charge you afterwards. You don't have to actually go through a cashier kind of an experience. When we're trying to innovate spaces like this, because we're expecting there will be labor shortages and things like that, well, can we explore different ways that robots can come into this place so that even people who are not used to going to these convenience stores by themselves because maybe they have mobility challenges or have visual impairments, so that they've always gone to stores with others. Maybe we can enable that experience for other people or larger populations as well. I will leave it there and take any questions. Thank you.
Thank you very much.
Okay, so actually with the guy canceling and with my 20-minute slot as a local in France, this should work out fine. Oops. So here's a picture from Aspen, Colorado last summer, where we have nature. We've got some greenery. We've got a little creek and some wildlife, some deer, and we've got human infrastructure. Bridges that have been built by humans that are being used by wildlife, and also power lines. And we have to somehow figure out how to live all together sustainably. Also, a picture from where I was living in Colorado that's not so happy is an example of cascading hazards. So when we talk about these unknowns, I was thinking about extreme events. And extreme events can have outsized impacts when they compound together. When you have multiple rare events simultaneously, you can sometimes have outsized impacts. So a little over a year ago, we had snow drought, a little bit similar to what happened in France, where there wasn't as much snow in the high mountains, and Colorado has mountains in it. In general, there was not enough snow for all of the autumn and winter, and so we had very dry conditions, and the vegetation was anomalously dry. Finally, a snowstorm did arrive, but before it started snowing, we had extremely high gusts of wind. So in miles per hour, these are very anomalously high. It was an anomalously high wind event. And so all it took was an ignition, and we got basically a firestorm. So burning pieces of wood jumped, carried by the wind, over our major highways in multiple places. And not even a forest fire, a grass fire, destroyed to the ground entire communities in one afternoon. We lost over 1,000 homes. So this is an example of cascading hazards. So multiple extreme events happening simultaneously that can have huge impacts. Another example was in California a few years back. And this is very similar to Mediterranean regions, where you have coastal communities with very high population density fronted up against mountains in the Santa Barbara area. And in California, there had been many years of drought, and there was, after a wildfire, there was a burn area that was getting under control in terms of the fire, but it had lost the ecosystems and the forest understory that really holds the land together to avoid things like landslides. And so with an intense rainfall, there was a landslide. Now, unfortunately, the word debris flow or landslide, at least in English, is not very scary. It should be much more scary. You have huge boulders coming into your living room, and as you see, over 20 human lives were lost, in addition to the damage to infrastructure. So these are maybe target long-term research goals, because as of now, AI is maybe being used to help forecast individual extremes, but really I want to bring this as we needed solutions yesterday to how to do a better job at forecasting and preventing these sorts of major losses due to extreme events. And also because extreme events are something very tangible that we can see. But more generally, we work on climate informatics, machine learning for the study of climate change due to these sorts of extreme events and the threat of climate change and its effects on communities and ecosystems. And this is based on the vision that machine learning can shed light on better predicting and helping to address climate change. And this has been recognized also in by the World Economic Forum. They put out a white paper that AI should be harnessed to address problems in the environment, because AI, for the most part, is doing a better job of helping us find cats in images and a lot of other things that are really good for business. Can we turn some of the benefits of AI to address societal challenges, in particular with environmental issues? Just a quick taste. So I've been pushing in this area for actually 15 years now, and I'm not going to go through all of these. I want to share where France and actually Paris-Saclay comes in, and then a few lessons that we've learned on building interdisciplinary communities, because it sounds like, at least from this morning, you're working on building interdisciplinarity here. So Paris comes in because we had our first hackathon in Paris, and then we also held the conference in Paris. But about building interdisciplinary communities, there needs to be a place for people to come together, bond, hang out. This is a great example. And also there needs to be publication venues. So we launched a workshop that became a conference, and it got archival proceedings. Now that's great for if you're a computer scientist, you would like to publish in a conference. If you are anything but a computer scientist, you would prefer to publish in a journal. So more recently, we launched a journal called Environmental Data Science, which is more broad. So any of you working on any environmental challenges, maybe you work with someone across the Valais at CEA or EPSL, please submit to our conference and our journal. But the other thing we learned was, as I mentioned, hackathons. It's really great to get a bunch of people, and I saw that challenge that you've been running, a bunch of people that have different experience in either the domain or machine learning, data science. Some have programming ability, some maybe have more of an understanding of the geophysics governing, the climate system, to get them in a room working on a problem given to us by, science collaborators and a data set. And we've found that to be really successful at bringing people together. Actually, there was a year when we skipped the actual conference, but due to COVID, but still ran the hackathon online. And this amazing group of international students really bonded with each other over that. So we have some critical mass here. And since I am building a team in Paris, INRIA Paris, on AI for climate change, I wanted to discuss sort of the three axes of that team, which is based on sort of my past, ongoing, and kind of present and future work. And just to boil it down, machine learning can come into all three of these areas, both to accelerate climate science, which helps with our understanding and better predicting of long-term climate changes, but also for adaptation. And I'll put the extreme weather events from the original slide into that. And adaptation, now we really have more of an interface with society, and we get into also some of the climate equity and climate justice issues. And then, is there anything we can do to mitigate or slow down climate change? Questionable, but at least we can help accelerate the green transition. And there, I've mostly been working in the renewable energy domain. So this is, the short people in France level talk. And so I will, if you'll humor me, we can go till 4, but I will basically give an overview of these 3 thrusts and might do a deep dive. One thing that I'm really glad about Christian's talk is that he totally motivated self-supervised learning, normalizing flows, domain alignment. So I don't have to go into any detail with those, but you might see how they can come up here. And then since ILLS, ILLS is, the core machine learning is involved, I will say that I've noticed in my career and also in mentoring my students that interfacing with these impactful domain problems actually does yield kind of a sweet spot where you can advance core ML as well. And just to kind of pop out and say that if you're not in the room because you care about the medical problems or climate change, you really care about advancing core ML, there is a way to work at the intersection. So I'll try to flag these when I come up, but that's not, I might not get to all of them. What is very interesting about this domain? So basically the data types are quite interesting. In paleoclimate, so the past, we do have some data that goes back very far into time, but it's geographically sparse. So we have biological signals, such as looking at the rate of growth of trees and corals, that'll clue us into what were the environmental conditions in terms of temperature, nutrients, and atmospheric gases available as the tree or the coral was growing. You may have heard of ice cores. You can core down into a glacier and look at trapped air bubbles. You can reason about temperature using water isotopes. You can look at the concentration of the trapped air bubbles. Or you could look at pollen in lake sediment, looking at a core under a lake to, again, reason about temperature and available nutrients. So those go back very far into geologic time, but are just very sparsely located geographically, not a nice grid. In terms of a very dense spatial grid of data, we're starting to have massive amounts of data from so many sources in this observation era, where we have weather stations and all sorts of satellite products and new missions coming in at greater and greater spatial granularity. We have floats in the ocean and atmospheric balloons. This is all great in terms of spatial resolution. It does not go back very far in time to look at the timescales that we need to reason about climate change. Okay, so the one area that is, I think, different than most other domains I've heard ML applied to is that, or the access to a data source. It's fake data, simulated data, but it's simulated from these climate models that experts in physics and the first principles governing the atmosphere, ocean, land, and cryosphere have been working on since 1969. So yes, it's fake data, but it encodes a lot of physical domain knowledge. And there are many teams building such models. There's a couple in France, CNRM, but which is, I guess, Météo France, but more locally, EPSL. Some of the Saclay labs participate in the EPSL climate model in France. But in the US, we've got the NASA model, the NCAR model. There's a Max Planck model in Germany. So each of these are entire labs that have been trying to do mathematical modeling, so non-stochastic PDEs, to simulate these systems, atmosphere, ocean, land, and cryosphere. As a machine learner, I can treat that as a black box predictor of any variable that I want at most any, okay, not all spatial resolutions, but at the level of the gridded simulation. And there, that's data. That's the only lens I have into the distant past and the distant future that's at some like spatial resolution. And I have no other lens into the distant future. So this is very unique. And climate modeling, the creation of those tools is a big way that climate scientists have been reasoning about climate change, because once you have a simulation of all these systems, you can set some initial conditions and watch the system run, and you can take the temperature of the model in the future. This is how GEC, or the IPCC, has come to a lot of their conclusions about whether humans, through generating anthropogenic carbon, have affected climate change, is that you can run the models without injecting the emissions from cars and et cetera, and you get a cooler climate than has been observed. The only way that you can match the warming that we've seen and the increase in CO2 is to inject those anthropogenic carbon sources. So where does AI come in? First off, I mentioned we have 2 models in France alone and a couple in the US, and basically there's now 35, 40 different modeling teams contributing to GEC or the IPCC. That's an ensemble, okay? Also, we have non-stationarity, right? So I can't take my standard textbook where I need data that's independently identically distributed. The identically distributed part breaks with climate change. It also breaks on things like the stock market and et cetera, which is something I had independently been interested in. So it was a great first work and then thrust of work to, again, treat the climate models as big black box predictors, because if you look under the hood, you've got a differential equation for every little exchange of energy or climate process going on. But we could instead have an ensemble of predictors also have observations in the observation era, and then use AI to try to adaptively combine and get an ensemble forecast. We can do also studies involving causality. Say we want to better predict the El Nino Southern Oscillation. Well, that's going to be really important when I talk about extreme events. So in certain years, the entire Indian subcontinent is either going to have higher precipitation or higher drought, and that affects the harvest and the GDP of that subregion. And these often are very tied to what El Nino Southern Oscillation state you're in, but we still don't have a great handle on predicting it, and climate change might be changing the frequency of that oscillation. So we can look at what regions of the Pacific Ocean should we be tracking to better forecast things like precipitation extremes in India, for example, by learning an ENSO index instead of just using what had been historically figured out as where you should look in the Pacific Ocean to predict, El Nino. You can use that using ML and computer vision techniques, and you can also look at it using causal analysis. We're currently doing a project that is actually more ambitious, might not even be predictable, but NASA now has an amazing ability to measure the level of the sea surface height by sort of triangulating different satellite products and measuring height down to millimeter accuracies at some geospatial scale. And over the 30-year period that they've been monitoring this, they record averaged over all the oceans an increase of 10 centimeters on average, which is all well and good. But can we just linearly extrapolate that out for the next 30 years? How do we reason about future sea surface trend? And so there we can also look at the climate models, because the climate models have forecasts into the future. So we're trying to use both the altimetry data and the climate model data to do forecasts of sea surface trends 30 years out with at the global level and at geospatial scales. We'll be talking about this at an ICLR workshop. Okay, so this was for the ML people. Online learning, when you add other dimensions on which you might have non-stationarity, was largely open, so we were able to come back and get some theory results as well. The other thing was, what if, and this might make sense for the stock market, but we had only seen it in climate, was what if you need to predict a month in advance, but simultaneously also predict in advance 3 all the way out to 12 months in advance. So now you've got tasks, you've got 11 forecast tasks, but the information between the tasks can be shared, and we showed that this can be done in a multitask learning framework that improves the performance of all the tasks except for the shortest prediction task, because the shortest prediction, you're updating your model weights based on the most recent data. So on this slide, no deep learning has been harmed. This is 100% in the field of online learning, extremely lightweight models. Getting back to the pictures from the very beginning about cascading hazards, even for individual hazards, there's a lot of work still to be done. We showed that we could treat wind and pressure fields around a storm center and use storm track data, so the location of the center of a cyclone every 6 hours, to do hurricane track forecasting. So where's the storm going to go in the next 6 to 24 hours, which is very important for warning island communities and et cetera. That is competitive with state-of-the-art at the U.S. National Hurricane Center, and often sometimes more creative. Look, sometimes the deep learning, it was sort of a fused CNN because we had different data types, would predict that the storm would turn sooner than the meteorological models that the humans also had access to. So not that it should replace those models, but the human decision maker in the loop should have access to both of these. Wow, okay, 4 o'clock snuck up on me. So I won't say that much more. I guess I will kind of say that governments are starting to adapt AI into these forecasts. Certainly, there's the National Tornado Center that's using that in the US. The IMD is using some of the tools that my postdoc developed for those precipitation extremes. And then we had a project with Météo France doing avalanche detection. This was one of the deep dives that I was going to do. And I just want to suffice it to say, this is a general technique following up on how Christian teed things off about, the future of unsupervised learning, which I think is really the way to go from here on forward. And actually now self-supervised techniques are outperforming supervised techniques. If you have a lot of data, there's Google papers out there, is that if you care about unknown unknowns or extremely rare events, then you're going to have class imbalance. Okay, so any supervised technique is going to have to deal with that. And if you have some labels, but not very many. So these were people actually trekking in the couloir in Haute-Maurienne. This was data from Météo France. And we had no human segmented images. We just had ground truth labels taken from the ground and then actual satellite images that that basically we say to lean 100%. So instead of we used a VAE for anomaly detection, but instead of training it only on the negative examples, we just said only train on unlabeled examples, meaning don't waste data in labeling your examples. And we got a lift that way. So if you have highly imbalanced data and it's unlabeled, then I would do a model of your data using 100% unsupervised learning where you didn't even label your data, and use your labeled data only for your hyperparameter tuning. So in summary, this architecture uses a VAE trained on only unlabeled image patches, and then the labels from the ground truth dataset were only used to calibrate the threshold on the reconstruction error at which you would label something an anomaly. And it got a significant lift compared to training a VAE only on the unlabeled only on negative examples. And then this is sort of the newest area, and I'm starting to talk to ODF around here and also the startup called Kairos of how machine learning can actually be used in the green energy transition. And we're again leaning super heavily on generative learning. Okay, so super resolution in computer vision is an interesting and important area, and as it corresponds to climate data, it's called downscaling, which is confusing because we think of like upsampling, but they use the word down to go from coarse resolution to fine resolution. And we basically showed that for any geospatial data, we can do super resolution using normalizing flows. Normalizing flows are the next step after VAEs that give you proper densities and are not limited to Gaussians. So this was sort of, oh no, my equations are missing. Nope. Okay, so this was teed up by Christian on what is but yeah, his equations were also missing on what is domain alignment. But basically, oh darn. Okay, so here's an example. So we can learn a normalizing flow. This normalizing flow is called GLOW, mapping low resolution data to a latent space and high resolution data to the same latent space. So two different flows, but a shared latent space, which allows us to then approximate the joint distribution of the low resolution data and the high resolution data with only IID access to each of the marginals, using the assumption that they're conditionally independent given the posterior that we learn over Z. This is really important because this whole generative idea hasn't really penetrated into climate science much. So the fact that we can just train from fine resolution data and coarse resolution data, but not have to have paired maps was totally different from the literature, or even having a probability distribution over maps as your output was also different. And then having the latent space, while the latent space itself is not particularly interpretable, you can use some of these techniques that are coming out in core ML of how do you, so say I take an image and I follow the normalizing flow that I've learned on my training data to a point in the latent space, and I do that for the two end images, then how do I walk through the latent space? I'll leave that to other people because it's like, how do you follow the geodesic of the posterior and still be efficient? But assuming you do that, then you can, at each point in the latent space, you can sample conditionally as many times as you want and take the flow to the coarse fine resolution or to the coarse resolution. And then you can show it to domain experts and say, at a coarse resolution, does this look like a good time interpolation of my precipitation map, and similarly at the fine resolution? So this is very, very general. Okay, so I don't think I have time for actually any of this discussion. It would have been a cool discussion. So at least in the US, I've been super interested in climate justice. I'm still learning what the situation is here in France or in Europe. But like in the US, we have like the southeast of the US has pretty much hardly any weather radar on it. And this is a highly BIPOC region. So how can we give fair and equitable weather predictions to regions where we are not even collecting data? And so with machine learning, we've shown that we can learn from satellite products which go everywhere to certain ground truth data sets. We can do supervised learning and then use those to fill in areas that we don't have data, or we can do things like downscaling. So unsupervised learning to go from low data regions, from high data regions to low data regions. And we have a project doing that, taking models from US to India for renewable energy planning. Anyway, so the team contributing to works already presented are still mostly in Boulder, but I'm starting to have team members in ARCHES, which will be my team, AI Research for Climate Change and Environmental Sustainability, via this Choose France chair, which is why I'm here. So anyway, I'm recruiting. The next concours is like in end of February next year. So talk to me if you're interested. Submit to the journal. There's also this really cool thing, but it's kind of more in the US, and I'm not going to talk about it unless anybody has questions. So I think I'll just stop there. And then if anyone wants to do a deep dive, although I'm going to need to, how about like one question? Sorry.
Okay, thank you.
So who is going to be the one question?
A lot of pressure. No pressure.
No pressure. No, I have a question. Go. Yeah, please.
I have a question, but it's not climate related. So if somebody has a better question than mine, go ahead.
I'd be happy to talk about deep unsupervised learning.
So my question is regarding the normalizing flow, because typically normalizing flows, you don't change the size, like your output is the same size as
Yes, good question. So what we did was for the low resolution field, we had to upsample it so that the
so that the latent
right.
variables.
So okay, if there's an assumption, it's there, but it was just the standard like near self. Good question.
Yes.
Any other questions? Okay, no.
I do have a very
Oh, yeah. Okay.
So there are a lot of problems. I mean, this has been an old topic, as there are a lot of models, physical models, I believe.
Yeah.
Very much online with what Nicola was explaining today in a completely different problem. And there are a lot of problems right now where people start to use some sort of reinforcement learning, like mechanical feedback. Have you tried to use a sort of mechanical feedback from the physical knowledge that you have of the model to train?
So this guy, is that Nicola?
Yeah.
He clearly works with Patrick Garlanari, and there's a team in Jussieu that does physics constrained deep learning. One bend of physics constrained deep learning. There's a team at my university that does PINs, physics inspired or informed.
Yeah.
So you can change your regularizer. You can change your architecture. You can change your loss function. So you can incorporate physics. I don't know if that's 100% what you were getting at, but when you mentioned RL, I was reminded DeepMind and Microsoft have each recently launched foundation models for weather. And NVIDIA claims they're doing a digital twin of Earth for climate. Okay, so now we've got foundation models. How do we do the downstream tasks? RL might have to be harmed in the use of how we do the downstream, or like, apparently with ChatGPT for downstream tasks, people are looking at RL.
Yeah.
So this is not something I personally have looked at all yet.
Molecular discovery too. There are many fields in which they start. Every time that you have some physical information, people try to bring like a mechanical feedback from the physical model that give you feedback.
Yeah.
You learn. So
One thing that's
I think
really,
this could fit very well
Okay.
with that. Yeah.
one thing that I want to have a special attention to when we think about the data pipeline, the reproducibility, the provenance, and how sound our conclusions are is I have been trying not to add any physics constraints to my learning. Why is that? The data I'm learning is the output from the data, my input data is output from physical models. Either it's really the output from EPSL, or it's what's called a reanalysis product. So you take station data or any real sparse data source and you make a gridded spatial product by observing, energy conservation laws imposed by physics. So if I feel like it would be too myopic to look at data with physical constraints, recover back physically constrained data when the data was generated using physical constraints. But yeah, I'd love to an email and talk more about that.
Yeah. Okay, excellent. So we are happy to have Sonia Del Mocar. She's Director of Research of Seniores in Lyon, in ILLS.
Yes.
And she's working on a lot of topics related to decentralized systems. Okay, I was worried.
Yeah, fair enough.
So it's great that you're here. So thank you for joining us, and please go ahead.
Yeah. Thanks very much for inviting me. So it's a great pleasure to be here. I know the day has been long, so I try to keep it short. I'll try to stick to the 20 minutes. So it's quite different from the previous talks. My background is not on machine learning. My background is on distributed systems, as I will be telling you here in this slide. The head of a distributed systems group in the LIS laboratory, which is located in the beautiful city of Lyon. So you're welcome to visit if you have time at some point. The team I'm leading is working on distributed systems at large with a specific interest in enforcing dependability, robustness, privacy, performance, and so on. And recently, we have an increasing interest in distributed learning as a sort of object, new object of interest in the world of distributed systems. And it opens actually plenty of challenges in terms of dependability, privacy, and performance. So I'm going to try to give you a sketch of what we do in this topic. And I'll start to maybe give you a few motivation elements. Why like we had this increasing interest in decentralized learning and distributed learning in general. So nowadays, like today's online services look pretty much like this. So we have plenty of applications that we access through a number of devices, and these applications rely on remote infrastructures for storage, computation, and so on, including GPUs for machine learning models. And these online services, so there are plenty of them, but are actually very important in our daily lives. They include, for example, web search. And these actually online services rely heavily on the use of personal data. So in the case of web search engines, when we use them, there are terms and conditions in which, of course, they explain that they do use our personal data in order to personalize their responses, which is quite useful for us. But they do also use our personal data for other things, such as the ad system that is actually underlying their business model. However, there is now, it's actually clear to everyone that sharing this personal data, of course, opens a number of threats. There have been a few years back a sort of scandal with the AOL, which is a very old web search engine that released a sort of anonymous web search query data set. And many studies have shown that anonymizing queries web search queries by hiding, for example, the IP address of the sender and his identity is not sufficient, because you can learn plenty of information about the users just from the keywords they search on the web search engine, including their age, their zip code, their religion, their gender, and so on. And there have been examples with de-anonymization of some of the users of this data set, such as this lady. Another example of online services that we use a lot are location-based services that actually use GPS data to provide us with very useful services, such as navigation, geolocated social networks, geolocated social games, and so on. And actually, a study on 30,000 applications in the Apple Store a few years back has shown that half of the applications actually collect location data when the application, of course, the applications were were sampled randomly. And half of the applications actually use the location when, or collect users' location when the application is in use. And quarter of them actually collect location data all the time. Again, as in for the web search example, sharing location data, while it opens us the ability of using plenty of very useful applications, it also opens a number of threats. So by analyzing, we worked a lot in the team on the topic of location privacy, and we actually studied what are actually threats, so by developing attacks, but also protection mechanisms in this context. And of course, through the release of location data, one can learn plenty of sensitive information, such as a user's home, workplace, religion, if the person visits regularly a worship place, sexual preferences as well, and so on and so forth. There have been also plenty of scandals of data leaks related to geolocated data, through which plenty of sensitive information could be learned from the users. So just to sum up this very small introduction, basically today's online services are heavily centralized in terms of governance. They're very data-centric because data is the new oil. This is not new. And this opens numerous threats. So, and on the other side, so this is something very well known, but we are a bit stuck because we are we really need to use these online services. And on the other side of the spectrum, there is an increased user awareness on privacy. So people start to do care about their privacy, even though there are no real alternatives today. And the legislator is also increasingly aware, and we saw in the previous talk earlier about ethics of AI, and the regulator is also recently, at least in Europe, with this AI Act that is actually there's an undergoing process to vote new laws related to regulations of AI systems and so on. So the regulator is also interested in trying to enforce users' privacy in these online services. So what I'm trying to tell you about in this presentation is that, can we think about other alternatives of today's online services? And the alternative that we work on in the team is trying to go towards more decentralization. So decentralized system is not something, is not a new concept. A decentralized system is a subset of distributed system where you have multiple authorities that actually do things for the application, but none of these authority is fully trusted or has control over the system. There are many facets of decentralized systems that need to be somehow investigated, including scalability, resilience, incentives. Why would people participate in a decentralized system, and so on and so forth. So decentralized systems is not a new concept. There have been many waves in the past of decentralization. Of course, the web, the initial version of the web was intended to be a sort of decentralized system. And then in the 2000s, for those who were born, but I think most of you, we don't have master students today. There have been a wave of decentralization in the the 2000s with these file sharing systems and so on, but that somehow collapsed, probably due to a lack of incentives. More recently, there is a new wave of decentralization in the web that is pushed by all these cryptocurrencies and blockchain technologies, but not only. So this has somehow motivated people to work again on decentralized systems, and there are many startups that start investigating decentralized systems. And my message today is that there will be no decentralized services without decentralizing the underlying machine learning mechanisms that are in them. Somehow, I can take an example of online social networks. So this is a paper from Facebook that showed all the machine learning models that underline their social network, and I attended the talk by American that said actually Meta would collapse if we remove the machine learning algorithms that are underlying the system. So this leads me to federated learning. That is a concept that appeared somehow, that started to be pushed from 2016 by Google Research. Using when they somehow investigated the distribution of the learning of their Gboard next word prediction algorithm, and since then there are thousands of research papers published every year in this topic, and there is an increasing interest in this. In federated learning, coming from many communities, including machine learning, optimization, distributed systems, security, networks, and so on. There are some real-world deployments. Most of them are, for example, for medical systems, across hospitals, and there are tons of libraries that are being developed. Maybe in a nutshell, federated learning works like this. You have various phases that actually are executed. I would say through various rounds, like so over time. There is an assumed existing server called the aggregation server, or there are many names that could be given to this server, that initializes a machine learning model, distributed to a set of clients. Here I represented cars because I have a project with Renault, the company that makes cars and that is interested in this kind of technology, I would say, of these solutions to train ML models for trying to infer the physiological status of a driver. For example, whether the driver is having like some kind of arrhythmia, or whether he's going to have a stroke while driving. It is a bit extreme scenario, but okay. Then each client in the second step trains the initialized model using his local training data, sends the gradients or the model update to the central server, which aggregates the received models and sends the model update to the clients, and this goes through time till the model converges. FL has a number of characteristics. So data in FL is generated locally. Usually it's non-IID because each user has its own somehow characteristics. And there are many privacy and robustness issues in this kind of process, because actually model updates sent by users may embed may include like sensitive data about the participants, and there have been many attacks in the related work showing that many properties could be inferred from model updates, properties, data can be reconstructed from model updates, and so on and so forth. There have been a lot of papers showing vulnerabilities of FL. This includes also robustness against various types of misbehaviors, including malicious parties, selfish parties, and so on. And maybe just to give a small zoom on work we carry on in the team, So we are mostly interested in another form of federated learning that is called also decentralized learning or gossip learning, which is described in the right part of the figure, in which you get rid of the central server that aggregates the model, and actually model aggregation is performed on each device. I'll give you some example, or maybe one example of works we do in the team on this topic, which is related to decentralizing recommender systems with gossip learning. This is an ongoing work that we do in the team. We also worked on federated learning based on privacy, and we also worked on decentralized and secure web search with trusted execution environments that are actually secure hardware provided by some existing processors like Intel SGX or ARM Trust Zone that provides some integrity and confidentiality properties in these secure hardware, but I'm not going to enter into the details. So there are many challenges to be addressed here, including personalization. And how many minutes? 5?
But we have time. Yeah.
Okay.
You can, don't worry for that.
Okay, I'll give you an example about what we do in decentralizing recommender systems with gossip learning, and in particular, a specific challenge that we addressed here related to personalization. Okay, so maybe I'll take 5 to 10 minutes to describe this work, and then I move to the conclusion. So recommender systems are everywhere, of course, including VOD and marketplaces that we use in a regular basis. Basically, a recommender system aims at providing users with recommendations of items that they might like. So there are many flavors of recommender systems. Classically, a recommender system is centralized. There are many algorithms that have been developed in this context. One of the most simple and most recommender system is collaborative filtering, where in a nutshell, the algorithm recommends to a given user items that similar users have liked. More recently, there have been flavors of recommender systems based on the federated learning principle, including, for example, generalized matrix factorization that has been implemented in an FL manner. So what we did in this work, we investigated the implementation, the design of a new decentralized recommender system using a sort of decentralized version of generalized matrix factorization using gossip learning. So in gossip learning, each node keeps his data locally. So his data is basically the past items he has consumed or liked. And the user trains a local model based on these updates. Each time the user somehow acquires new items and rates them, you could use that to train to update his model. And then nodes exchange them updates asynchronously with some neighbors that come from a random peer sampling algorithm that actually provides each user with a neighborhood, so other users in the network. Initially, the neighborhood is randomly selected, and then we see that there are some tricks in order to improve the convergence of the learning algorithm through the selection of some neighbors that are actually good for the user. So in gossip learning, you could have many objectives. In recommender system, our objective was to train a model that performs well for the user. So our objective is not to train a model that is good for everyone, which is usually the case for centralized recommender systems, but personalization has been pushed further in gossip learning, in this work, towards the fact that each user has his own model that actually personalizes recommendations for. So there are basically two protocols that we have designed in order to improve users' local satisfaction, the quality of a user's local model. One of them is in the peer sampling protocol, in the selection of neighbors. And the other one is in the model aggregation part. So when you receive models coming from your neighbors, how would you actually aggregate them in order to improve the quality of your local model? So model aggregation in this work has been done using the evaluation of the performance of the models. So imagine I have my neighbors, I receive their latest model update. What I do is that I test the quality of the received models using a local test set that I have locally. And I would actually aggregate these models by putting better weights, higher weights to the models that actually provide me with better recommendations. So I actually do aggregate all the received models, but with differentiated weights according to the quality of perceived through testing them. The second part of the protocol is personalized peer sampling, in which we keep track of the best received models from our neighbors, and we adjust somehow the ratio of good neighbors among the random neighbors that I have. It's important to keep randomness in order to explore the network in the system. But there is a sort of balance to be found between exploration and exploitation, in a sense that the more good neighbors you have, the less you can discover the network, and the other way around. Somehow there is an equilibrium to be found here in order to adjust the neighborhood of each node. Maybe a word about the evaluation. So we evaluated this work using two use cases: movie recommendation and point of interest recommendation through simulations. And we tested two different models, GMF and PMG, sorry. And we implemented a number of competitors. So they are federated learning competitors, and we also decentralized some existing personalization algorithms, such as Reptile, that is a meta-learning solution. We actually implemented the decentralized version of this solution. And maybe one number that there are plenty of experiments in the paper, just to show that we actually looked at the long tail. So instead of looking only at the median of user satisfaction, we also looked at the tail, and actually our solution improves user satisfaction in terms of quality of recommendation. I will conclude here. So basically, today's online services are heavily centralized. We try to push research works towards more decentralization. Actually, a new wave of decentralization that is undergoing in both in the web and also through many startups that try to push more decentralized systems. We actually have a joint lab with a startup that works on decentralized cloud infrastructures, where you could come with your computer and so on, and you could monetize, for example, the fact that your computer is used to do some computation and so on. And one possible use case we could think about in this context is to, for example, by using these decentralized recommender systems, we could, for example, imagine that users could come with the history of their purchases, for example, or the history of their web search queries or whatever, and they could actually train in a collaborative manner a PageRank algorithm, or I don't know, a decentralized recommender system algorithm, by keeping their data local, by sharing model updates and so on. And they could, for example, monetize the fact that they contribute into this decentralized training of a recommender system. I don't know. These are open questions. But we try to push decentralization in this context, and also through the collaboration with this startup. in order to reach decentralized online services, we need to decentralize machine learning models. There are, though, many challenges in this context that require actually many communities to work together, including machine learning optimization. I'm from the distributed systems and security community, so yeah, for us, it's important to collaborate with other communities in order to be able to somehow have effective contributions. One of the objectives is to understand the benefits and the limits of the decentralization. For example, one of the interesting questions are, why did the previous decentralization waves fail? One of the possible reasons is the lack of incentives. Another question that we're interested in is, does decentralization increase or reduce the attack surface? We have actually an ongoing work that actually shows the evidence that decentralized learning actually can improve somehow users' privacy, even though maybe it's not very intuitive. The fact is that our model, while he's traveling in the network, it somehow gets diluted with the models of other users. So basically, in order to infer private information about one user, few hops away, actually private information is completely diluted with the information of other users. So we are implementing known attacks that have been devised in FL, and we are comparing them in a decentralized environment. And actually, there is evidence that these attacks are less effective in a decentralized environment than in FL. Another very important work that we are starting to push is enforcing privacy and resilience to Byzantine nodes in these environments. I can maybe say very last word regarding, for example, the Byzantine attacks in federated learning. One of the problems is that you could have users that contribute crap data, for example, to update their models in order to introduce noise in the centralized model. In the decentralized setting, basically, and in particular in the performance-based model aggregation we proposed. Of course, when a node receives a model, if the model is too noisy, if it is crap, somehow it just drops this model and does not integrate in this model. There is a sort of, by design, resilience to some sort of Byzantine behaviors. We are very far from solving the problem. There are plenty of other problems here, and yeah, that's it. Yes.
Everybody, it's a great pleasure to introduce Jeremy Cooperstock, who is professor electrical engineer at McGill University. He's associated with the CIM, the Center for Intelligent Machines, and also ILLS. He's an expert in human-computer interactions and related fields in multimedia immersive and interactions in health applications. So, Jeremy, we're very happy to have you here. Please, go ahead.
Thank you. Thank you, Pablo, and thank you, Mark, for setting up this wonderful initiative, and pleasure to be here. Really enjoyed the presentations yesterday. I'm going to be somewhat of an oddball here in that I don't do medical imaging, and I'm not really an AI researcher. I'm rather somebody who's using AI as a tool to facilitate the sort of applications that we work on, and largely in the domain of interactive systems. So I'll talk about that. And I thought it would make sense to lead off. It's going to, no, okay, so I'm not going to use that. Okay, that. Oh, okay, I don't seem to have any control either. Oh, there we go. All right. So I thought I would lead off just as a quick outline with the sort of opportunities for collaboration, as I likely will end up running out of time and then not making it to the end of the various items. So as a sort of quick overview of some of the themes I'll talk about here, these are areas in which we're using AI or machine learning or looking to have improvements in AI and machine learning techniques. And I saw a few sort of hints of things that overlap with these areas. So happy to talk to you where there are opportunities. So as a starting point, as like way back in early years at my time at McGill, the area I got into as a research topic was low latency, high fidelity, distributed interaction. So video conferencing, but without delay, that would support the most demanding interactive tasks. And some of you may have been bombarded by the sound, so just fair warning, it may be a bit loud. But as an example, so that's McGill University. That's Stanford. And that was circa 2000. So we were performing simultaneous distributed music without cheating. You probably saw all kinds of demos since then where musicians around the world would be playing together, but it was all with click tracks. They weren't actually hearing each other, or one was hearing, and so on. And it was all very exciting, and we did a lot of these kinds of things. Transatlantic as well, we had groups performing remotely, all subject to having high bandwidth. So that's where we got our start, way, way back. And we did various demos. This was between Seattle and Montreal, so similar kind of distance across North America. And we had the conductor of the McGill Jazz Band performing with his students halfway around, across the continent, with 3 streams of uncompressed high definition video. It was all a lot of fun. And that led to our interest in going a step further in terms of allowing for distributed interaction that feels like being together. So we can bring the delay down to a point where musicians can perform together, but we can't have the musicians interact where there's no barrier between physical co-presence in the same environment and somebody who's remote. For example, this musician over here who might want to come over and stand beside that musician there, or look around and see what's going on over there, can't do so in distributed interaction, and we want to support that sort of activity now. So what we're working towards is real-time video synthesis with camera arrays that will acquire the video from this location and allow for a viewer over here with possibly a headset right now so that they have mobility, like we have, European, Canadian mobility, right? Exchange of students and so on. We want them to have mobility, being able to walk around their environment and explore and have different viewpoints and so forth. So the real-time video synthesis. And all of the tools that we're finding so far right now are very limited in terms of what they can do, in terms of the fidelity of representation and so on. Or they require massive amounts of processing. So we'd like to try to bring those efforts down. There are some tools that do a reasonable job, sort of the cheap light field rendering, but we're looking for newer techniques that allow that to run without needing hundreds of cameras and hundreds of GPUs to process in real time. Okay, so that's all as sort of background of where we came in with video based interaction, and the challenges that arise are more than just being able to move around. There's also the challenge of the fidelity of the experience that you have in terms of awareness of what's going on, especially in large group. So right now, I have enough visual acuity to see who's awake, who's sort of falling asleep, who's interested, and so on, because we have enough pixels in terms of our retinal displays. But we don't have that. Whoops, that's going the wrong direction. Okay, we don't have that through computer-mediated interaction. We don't have enough pixels in the displays and the cameras and so on. So when we have a large number of individuals who are conferencing together, or you're doing remote teaching, as some of us had the experience over the last few years of pandemic, there's a loss of awareness of what is the level of attentiveness of the crowd, who's laughing, who's finding things boring, and so on. So we said, what can we do to augment the display in a manner where you gain an awareness of the kind of emotional activity of your audience without having to go and look at picture by picture each of maybe 50 students. So here is, it's over here, the example.
When giving a remote one-to-many presentation, it can often feel like you're speaking to a blank wall. Cohere is a video conferencing module that can implicitly convey affect in one-to-many group calls. Cohere works by mapping people's facial expressions onto particle avatars and mixing them together in a video feed in real time. Through a qualitative in situ study, we discovered that Cohere encouraged people to express themselves more than they would have in a typical presentation. People also reported feelings of emotional alignment with others in the call, where other emotions would affect their own. In a quantitative follow-up study, we found that Cohere animation systematically affected users' emotional perceptions of the audience. For more information, check out our CSCW page.
So anyway, well, all right. So building on that, so the representation of the simple avatars based on these diamond shapes and the way they bob up and down and so on, you can gain an appreciation of affect. And we also looked at that over large, so hundreds of points that would respond according to the affect. And it's actually quite effective. You get a good sense of what's going on. Obviously not to the same level of detail, but sufficient to gain an understanding. And now we want to apply those sort of concepts to distributed interaction, not sort of the classroom experience, but more social activities like watching a movie together or watching your favorite sports team play, and having the experience of your best friends or your family members who are remote from you feeling as if they're close together. So how can we do that? By leveraging things like background audio, haptics, so vibration in the sofa, whatever it might be, maybe illumination patterns, to convey the affect in a manner where you are aware of what's going on. So try to augment the limited video conferencing channel with additional cues so as to make the participants aware more intimately of what sort of activity is taking place at a distance. So how do we pick up on the affective cues through sensors in the environment and reproduce those at a far end? And maybe there's a machine learning element in place that has to be aware of how do you respond to the cues that are rendered? How do you pick up on, let's say, some sound that's taking place over to the left that's sort of reflective of somebody's breathing quickly because their favorite team is about to score a goal, or vice versa? Do you need to extend that with a graphical projection? Do you need to vibrate the sofa in a certain way in order to make the participants aware? So we may need to learn these on a per participant level as to what's going to be effective. Okay, so switching over, another series of research projects in which we're involved is very much focused on supporting or assistive technologies in support of blind and low vision users. We've been working in this space for about 15 years or so, and we started with a project called O'Toole. It actually had a really unfortunately chosen name when we started the project, which was In Situ Audio Services. So just imagine the acronym and think back about 15 years or so when that was not a good choice of words. So we rebranded as O'Toole, and I can give you hopefully. Oh, the microphone is disappeared on me. Where did the microphone go? There was a microphone here that somebody showed me, and now it's been taken away. Because I could hold the microphone up to the phone and do the live demo. Anybody? No? Pablo left. Maybe it'll still be audio through.
Just outside.
Okay. So I'll see if I can bring up the audio. All right. So is that maybe it's audible? Okay. So here's O'Toole. It uses OpenStreetMap, Google Places, Foursquare, a number of other transit service feeds and so on to give the user of the tool an audio representation of what's around me. That's the name O'Toole. And if you like, it's sort of like neon signs for the blind. So one mode is the radar playback. And it plays as a radar sweep around your head. So if you have headphones on or
too long, 3,150 different lines. Title too long, 1226 different lines.
Okay, too many lines of buses.
Action. Programming to stay in Avenue Sciences.
So I have no idea what's around here. And the other mode, okay, B mode, I can point.
Southeast, parking parties. Northeast. Administration Duluth Northeast. Batman 605, 606. University. East or Southeast. Giardi Garden K. ING Northeast. Batman 610.
Okay.
South. radar mode, parking,
All right.
radar mode, beam mode.
Okay, so that's the idea of O'Toole. You can use it either to get a continuous radar sweep around you, or you can point it like a flashlight and say, illuminate what's in front of me. And we've had numbers of users, several hundred around the world, who are using this on a daily basis for their navigation and sort of sense making of their environments. So that's where we started on this sort of general situational awareness app that allows for greater awareness of one's surroundings. And then we started to deal with other areas where the machine intelligence could provide additional autonomy. For example, one of the dangerous tasks that blind individuals face is crossing streets safely because of veering risks, right? You're not sure if you're walking in a straight line, you start to veer potentially into oncoming traffic. So we worked on intersection crossing assistance. And here's an example.
Fait qu'on porte le téléphone dans une pochette autour du cou, puis la caméra, elle doit être pointée juste en avant de nous. Ben, on prend une photo constante pendant qu'on traverse, puis ça choisit quel est le meilleur trajet. Et ça utilise des écouteurs à conduction osseuse. C'est des écouteurs qui se connectent juste en avant des oreilles, c'est mieux qu'on ne bloque pas les oreilles pour qu'ils puissent toujours avoir accès au son de l'environnement. Puis ça utilise des sons pour nous informer si on commence à vraiment se dévier vers la gauche ou la droite.
Okay, so that's a project that's sort of been on hold for a long time because the training we've been trying to go through and looking at different segmentation options for improving the recognition has not resulted in anything that we consider sufficiently robust for deployment. So this is a big area where better machine learning models would be very, very helpful, or new techniques of training based on landmarks in the environment, whatever it may be. And we know that HumanWare, based just outside of Montreal, one of the world's largest accessible technologies companies, is also very interested in the problem, and they have not had any success there either. So something where we could certainly benefit from help there. We've also worked on indoor navigation tools, so using the camera and some processing to recognize key objects, doorway detection, guidance towards the door, finding the door handle, finding stairwells, elevators, bus stops, and so on. All of them posing various problems for general real-world robustness and ability to work. So switching over from the O'Toole project and the guidance indoors, we've been working on taking the web and making the web more accessible in terms of the preponderance of image content that is found on websites that are largely inaccessible to somebody who's blind or low vision. Alt text, as we know, is provided for a very limited number of images, and usually the alt text, if it's there at all, is quite poor. It'll say, here is an image, right? Okay, well, so what is in the image? There have been various efforts, including Apple's VoiceOver and Freedom Scientific's JAWS, which is a screen reader project or product, I should say, that takes the graphics and tries to develop or produce in real time an alternative for the textual description and render that for screen readers, but they're often found to be wanting. So we've been working on a project called Image, described there, that takes the graphics and uses an assembly of different ML models to recognize what kind of an image, is it a photograph, is it a line drawing, is it a map, is it a chart, and then accordingly pass that down through a pipeline of different processors specific to the type of image that it is, and render that to the user using both speech and non-speech audio, as well as the possibility of haptic feedback. So we've been using devices like this two-dimensional pantograph that is a consumer affordable device that gives you force feedback as you move around in a graphic. And we've also worked with refreshable raised pin arrays that you can put multiple fingers over and feel the texture. And just to give you a quick peek as to what that looks like.
Image is an open source, free to use web browser extension that provides an experience of graphics found on web pages, which does not rely on textual information. All you need is a pair of headphones, When you activate image, the graphic is sent to our server for analysis, which sends back spatialized audio and, optionally, touch interpretations for you to experience. For photos, image conveys the spatial extent of regions and the locations of things and people relative to one another. In this photo, you'll hear buildings as a region because they take up a significant portion of the scene. The sound traces the outline of these buildings from left to right and changes pitch to indicate height. A popping noise plays at the positions of people and things. You will hear cars in the lower left of the photo and people in the lower right.
This outdoor photo contains the following outlines of regions: building, car. It also contains the following objects or people: 6 people, 2 traffic lights, 4 cars, a bus.
Maps and web pages typically display a pin at a specific location, but provide little in the way of information about what is around that location. Image instead offers a points of interest experience to provide you with an awareness of additional landmarks. For the following demo, imagine that you're standing at the pinned location in the map, facing north. You'll hear jingles along with an audio description of each location that image extracts.
From due north moving clockwise, there are the following: Badlands Interpretive Trail, Historical Mine Site, Royal Tyrrell Museum of Paleontology, Country Road Verb, Drumheller.
In the future, image will also offer an interpretation of streets and intersections. This can be applied to render an audio experience of a subway system map, as in the following example.
Vaughan Metropolitan Center, yellow line. Spadina, yellow and green line. St. George, yellow and green line. Moor Young, yellow and green line. Shepherd Young, yellow and purple line. Finch, yellow line.
Okay. And with regard to the benefits of introducing haptics, we've conducted a study where we compared a user's ability to reproduce a graphic that they experienced rendered only with audio or with audio and the haptic feedback. And we would put a number of markers at key positions in the scene, identifying things like the sink, the chair, the fridge, and so on. And then we would ask them to reproduce using a sort of series of these cloth or felt marker that we would place, and we would measure how far away they place the markers relative, or their fabric pieces relative to the assumed locations in the image, and look at the distances from ground truth for the two experiences. And we found that when they used either the 2D the force feedback device or a pin array, they would do a fair bit better in terms of accuracy. So the error using the multimodal haptic audio feedback was significantly less than with audio only representations. So there's value in providing them with the dual rendering. We've also looked at using improved specific descriptors for types of people, clothing, I can't remember the other category, and combining all of those into this, the student called it DICE Ally or DICE Accessibility. I can't remember what the acronym stands for, comparing it to existing commercial products in terms of what participants found useful as the picture description. And there was fairly strong consensus that there was preference for our renderings against the commercial tools. And then we looked at individual histograms at the top, but the additional detail we provided, because of these added ML models that were incorporated, that were scene specific, turned out to be quite valuable. So again, having better domain knowledgeable tools to apply here is found to be useful. And the area we're taking this now to extend working in the same sort of domain as what Ajam talked about yesterday with the Retail Innovation Lab, is looking at something like the retail shopping experience for somebody who's blind or low vision, and offering them real-time guidance to help them find objects of interest, certain grocery items they're trying to pick up, for example, in a grocery store environment, and trying to leverage a combination of OCR and basic object recognition ML models, along with GPT, to make sense of the confusion of models or the object recognition results that are completely inappropriate. So, for example, here, this, I don't know, was it flan or some sort of dessert? This is all from a student in Brazil right now working with us. The object recognizer finds it to be a can opener, but with the OCR pulling up ingredients and then feeding both of those to GPT, you get out a description that is actually fairly accurate. So we want to use this to identify key objects, give the users a rendering of what is there, and then physically guide them to know, okay, how do they have to reach towards it to acquire the item, and then validate it thereafter. So this is a project that's starting up now we're working on. All right, so that's another area for accessibility. And now switching over to a third topic, we've been working on avatar therapy for schizophrenia. So a bit of a jump in theme here, but where we want the psychotic patient to be able to recreate the avatar that they experience in their own mind. So the theory from the psychiatrists we work with is that by recreating the appearance and the sound of the voices that the schizophrenics have in their heads, they will gain agency over the hallucinations and thereby lead to better outcomes in terms of the treatment. So there's this whole technique of avatar therapy where the clinician plays the role of the hallucination and engages in dialogue with the patient over time, helping the patient be more assertive over their hallucinations. So the problem is, what do you do to create the avatar when you don't have a photograph available and you don't have an audio recording of what that voice sounds like? So we're trying to build tools that will allow for the patients on their own with minimal guidance to find the face that matches their hallucination, to find the voice that they find inside, that they experience inside their head. Now, in fairness, or sort of full disclosure, very few psychotic patients actually have visual hallucinations. Most just have audio only. Nevertheless, we wanted to compare the ability of our tools versus the sort of gaming character creation interfaces that build these sort of cartoon-like, or allow you to build these cartoon-like representations, and see how effective how closely we could match the appearance with a photorealistic quality. And here are some tools that were developed for that purpose.
Making faces, interface paradigms for navigating photorealistic avatar design. Character creation interfaces for non-artist users are limited in the degree of realism they can provide. We present 4 interfaces that enable a user to create photorealistic avatars. In the map exploration interface, the user navigates a facial similarity map and selects images they like. A list of clusters helps the user focus on a particular region of the map. Then the user can translate inside the map, adapt the size of the images, zoom in and out, expand a single image, and add it to a list of selections. In the optimization interface, the user selects a hotspot to initialize the process. Then, as each new avatar is proposed, they click on their preferred one. 29 images are proposed as starting points. Based on user selection, new avatars are sampled from the facial similarity map and proposed to the user. The user clicks on the avatar they prefer between the current solution and the proposed one until they are satisfied, or stopped by the algorithm. In the manipulation of semantics interface, the user directly changes the appearance of the avatar by clicking on plus and minus options.
Okay, in the interest of time, I'll move on to the audio interface.
This often raises the need for generating human speech with a voice that only exists in the patient's head. There exist some commercial tools that morph human voices, but they often simply control the pitch of the voice and result in significant audio distortion. Our study focused on creating a convincing match of the voices by proposing a map and 2 voice manipulation techniques. First, we will introduce the overall pipeline of our system. We collected approximately 2,500 voice samples from a huge corpus, then used an encoder to vectorize the timbre of each speaker. We applied dimension reduction algorithm UMAP to the vectorized data and built the voice similarity map. On the map, users can select any voices that they perceive close to their target voice. Then by either using one of our 2 proposed techniques, they can customize the voice to converge towards an effective match for their target voice. The line neural encoder synthesized new speech by combining the output voice's timbre and a predefined text input. The map consists of 2,484 voices of different speakers. The voices can be played automatically on mouse hover and saved on mouse click. The saved voices are added to a list at the bottom, and from there, users can drag and drop the sample to start manipulating it. In latent parameter editing, users can use 4 sliders representing 4 parameters: pitch, resonance, hoarseness, and strain. These parameters were obtained by performing principal component analysis with the vectorized voice data. In voice mixing, users can listen to 5 samples that are synthesized by the computer. The 5 samples have interpolated timbre of the 2 mixed voices. Now let's take a look at the system in action. The first video demonstrates how latent parameter editing works.
And the news director was paying me $22,000 a year. And the news director was paying me $22,000 a year. And the news director was paying me $22,000 a year. And the news director was paying me $22,000 a year. And the news director was paying me $22,000 a year. And the news director was paying me $22,000 a year. And the news director was paying me $22,000 a year.
Next video demonstrates how voice mixing works.
Not because it's the right thing to do, but because I don't want to hurt her.
Not because it's the right thing to do, but because I don't want to hurt her.
Not because it's the right thing to do, but because I don't want to hurt her.
Not because it's the right thing to do, but because I don't want to hurt her. Not because it's the right thing to do, but because I don't want to hurt her.
We conducted 2 user studies. The first study took place remotely via a video conference tool with 20 participants. Our motivating use case is when we do not have any reference data of the voice, but as part of the study design, participants had access to samples of their target voices. They were asked to generate the closest voice to their target voice in 3 different conditions. In the first condition, they only selected the closest voice to their match from the voice map.
I'll zip ahead.
In the second case, and after their exercise in the first 16 members generated voices to match the voice of 2 celebrities under the 3 conditions. Then 20 participants ran blind assessments on the voice samples generated from the previous session. They classified the voices into multiple clusters by judging similarity as they saw fit. We then ran cluster analysis and multidimensional scaling to analyze and visualize the similarity of the voices in the perceptual domain. We plotted the similarity values of the voices on a 2D plane. On this plane, the x and y axes are dimensionless, but only represents the relative similarity of the voices. The closer the voices are located, the more similar they were perceived by participants. We can observe most voices generated from the commercial tool are located far away from the target voice. We then ran 2-way ANOVA with 2 independent variables, method and voice. As results, there was a significant difference between the commercial tool and our 2 synthesis techniques. And there was no significant difference between the celebrities' voices and between our proposed techniques. Although our preliminary results are promising, our system has some limitations. First, a single parameter inlaid in parameter editing sometimes affected more than one perceptual feature. This is because a dominant pattern obtained from dimension reduction is not always perceived as a single feature in human perception. For example, our lost parameter created more powerful speech when controlled in one direction because it increased the strength, speed, and volume of speech altogether. Second, our current techniques only supported English with North American accents. To expand the accidental language variation, model training is required with a large amount of speech data in that particular accidental language. Here's our takeaway. We proposed a map exploration interface and 2 voice manipulation techniques.
So the disentanglement of the latent parameters has been a big challenge, in training for Quebec French accents, for example, is really problematic when we're trying to work with patients there. And you have somebody with a Parisian accent playing with hallucination, it just doesn't work. So trying to get these corpuses that will work with Quebec French has been one of our challenges there. Unfortunately, that video doesn't include the match, but the student had, I think in another video, an example where we gave the participants Oprah Winfrey's voice as their target, say try to get a match that was close to that. And the result, by playing with these parameter searches and the mixing and so on, was one where the members of our lab couldn't tell them apart. It was like, no, you've got the wrong voice in there. You've copied in Oprah Winfrey. She said, no, that's the result. So it was really quite impressive. We've also, I'll spare you the details here, but we've also been working on tactile hallucinations. So having the hallucination come up and grab your shoulder, for example, as an added element of realism, using soft robotics techniques. So using these pneumatically actuated bladders that can be attached into wearables that you put on. And we did some studies where we looked at your ability to distinguish whether you were being grabbed around the wrist or the shoulder, or I can't remember, the other one was the back of the neck, I think, whether you thought it was a human touch or the wearable doing it to you. And the confusion matrix was very high. So pretty promising initial results, although you do have some uncomfortable equipment to wear. All right. So building on the avatar techniques that we use for psychosis treatment, we've extended that into more other therapeutic domains, looking at, for example, senior care or older adult care facilities. And we built, and we're hoping to deploy in the next month for a pilot trial, an avatar we call Adina, where the user doesn't have to create the voice and the appearance, but simply engage in dialogue, where based on the leveraging of multiple ChatGPT personas, we can conduct psychosocial evaluation, check on medical elements, like are you taking the drugs you're supposed to have? Are you eating well? Have you what's your mobility like? But also, and importantly, especially considering the nursing shortage facing us, at least in Canada and the US these days, have some assistance for the overloaded nurses in terms of regular interaction with the people in their care to conduct the preliminary evaluations and to be there as a sort of pre-triage type of element. So here's just a very poorly edited clip that shows some sample interaction with the agent.
Adina is a virtual companion for seniors in long-term care. She offers personalized conversations tailored to the individual user's preferences while avoiding sensitive topics and reminds seniors of activities relevant to their well-being. Adina also engages in conversations to help clinicians and caregivers collect health information.
Hi, Adina.
Okay.
I'm good. Just like to chat a bit.
I have some conversation topics you might be interested. How about talking about Italian food, tennis, craft beer, or plants?
Those were topics that were pre-populated based on a nurse's knowledge of the
That's great. What's your favorite Italian dish?
Lasagna.
Lasagna is definitely a classic Italian dish. Let me know if you want some recipes. By the way, I have to ask, have you taken a shower today?
Oh, I forgot. Thanks for reminding me.
You're welcome. It's important to maintain good hygiene to stay healthy. So, back to our topic. Do you like lasagna with meat or without?
I like with meat. Ouch, my leg hurts.
Can you describe the location of the pain?
So my left leg above my heel, but below my calf.
Can you describe the pain? Is it sharp, dull, or throbbing?
It's very sharp. It wakes me up at night sometimes.
Have you noticed any swelling or redness in the area where you feel the pain?
All right, so what happened there is there was a transition into the Merck manual medical diagnostic ADINA agent on detection of the user indicating something that was medical or health related. So you have these multiple personalities. ADINA herself, I guess, is schizophrenic and invoked appropriately based on the conversation, but all guided towards making sure the well-being of the person in the nurse's care is being attended to properly. So hopefully we'll alleviate some of the problems that we have in nursing shortage overload. And finally, as a topic that we're about to start shortly, we're working on using EEG measurements taken with an in-ear set of sensors, or not in-ear, but over-ear sensors, to try to process auditory attention and to steer the audio that is being reproduced either for synthesized audio, so you've got your agent on your smartphone that has to provide sound overlaying the natural environment, or for those who have hearing aid dependencies, being able to help steer the sound amplification relative to the audio that they're trying to attend to. So you've got the cocktail party effect, noisy room. How do you focus on one conversation over another? If you have good normal hearing, you can do that effectively. If you're using hearing aids, it becomes really challenging. So you can turn your head, of course, to do beamforming, but we want the system to be able to do that for you automatically by recognizing what sound you're trying to pick out among the various cacophony sources out there, and then attenuate the others and amplify the one of interest based on EEG. So this is sort of moonshot sort of science to see whether we can get there, but we're working with some people who've done a lot of neurofeedback and EEG processing. So we're hoping to be able to learn the models of what's going on in terms of attending to different spatial locations and process accordingly. So that is it as a sort of brief overview of some of the areas of interest where we need ML expertise and help, and happy to talk to those of you who are interested in working with us.
Thank you, sir.
So I was wondering when you described this multimodal fusion between the image and the OCR and to fed that to ChatGPT, did you have to retrain something in there?
No, strictly just again, it's all prompt engineering. So you tell ChatGPT you're going to be given a object recognizer output of items in a grocery store, along with the OCR of whatever the camera sees. Please understand that the object recognizer might be faulty, and try to make sense and describe to somebody who is blind what the item is that they're looking at, and just taken care of. So I mean, I tell everybody, ChatGPT is going to put almost all of us out of business in a few years, right? If that's the positive use case, right, where we're only just put out of business. We'll see how bad things turn out in reality. But it's just good prompt engineering and all your problems are solved, sort of thing. It's not quite, but we're getting there.
Yeah, I do have one question. I mean, it's something that interests me a lot. You mentioned that it's difficult to disentangle the accent.
Well, that's so we have parameter disentanglement in terms of the various characteristics, but the accent is all the training. So we have a corpus of North American English, for example. So we can reproduce any voice in the spectrum of North American English accents. if we have a corpus of French accents, we cannot produce a Quebec accent. We have to have the training data. And that's, so there's accent training, and then there's latent parameter disentanglement. Those are separate problems.
Maybe if you have a few examples, like people a few shots,
right?
To be able to somehow readapt the accents and copy the accents from.
So that's where we need the help in the ML, because otherwise, if we have just a few examples, you've got all the bias and everything steers towards the whatever the dominant accent characteristics are.
Yeah, be happy to chat in offline.
Great.
Yeah, and we have some ideas.
That'd be great.
That's great. Yeah. Thank you. Yeah.
I got a question about your, so you had your video with a dialogue, between the avatar.
Right.
So then basically it's still like chat, because we have big, latency between each answer. So you can't barge in, you can't interact. And at the beginning you showed that it was very vital, when you interact with a computer screen, like you see the feedback, you see, and so how do you think you can fuse both and have much more realistic?
Yeah, so, and in fact, what you saw in the video is cheating, because the latency is much worse than that in practice. So, working on trying to optimize, there's 2 seconds of voice recognition, 1 second for the speech synthesis, 1.5 seconds for ChatGPT to generate its output, it all adds up. So some of the techniques that are used, and we see this in other commercial tools, not sort of similar kinds of ideas, is to introduce, first of all, on the avatar side, general kinds of, kind of feedback while the system is thinking, right? So that's one of the elements. Barge-in is already supported in audio interaction, so that's feasible. You just have to detect the sound and then make sure you're dealing with the feedback suppression and so forth. But really, the tricks for how you make the avatar appear to be human-like when it's thinking requires a lot of delicate tuning that has nothing to do with ML, and it's all more like the Hollywood special tricks of telling the story. With initial attempts, we compiled a corpus of, I don't know, 12 different filler things, like, oh, how interesting. And then you have somebody say something like, I'm feeling ill today. And says, oh, how interesting. It's like, that's completely inappropriate. So you need things more like, or just, head motion. But this is where people who are more in the art side understand the medium, how to create that kind of effect. And obviously the environment or the scenario in which you're deploying it is important in terms of acceptability. So if you're trying to deal with this kind of style of interaction, an avatar that's going to sit there for 5 seconds in response to a question is not going to be effective. Thank you.
Let's engage. Okay. So we're happy to welcome Xavier Alameda Pineda with our next speaker. He's a research scientist from India, in Grenoble. He's the leader of the robot learn team, and he's working on computer vision, audio processing, machine learning, and human-robot interactions. And perhaps he's coming to Montreal soon. We're working on that. So give a few seconds, the time that Viviana is setting the presentation.
And me.
And you. Okay, you're sharing the script. Excellent.
All right. So, good morning, everyone. Thanks, Pablo and Mark, for the invitation. I'm very happy to be here, and I will be discussing some of the topics that we are dealing with in the robot learn team. So we are located in Grenoble, close to Grenoble, which is a city with good food, better mountains, and just this very long street that you can see in the photo, which in the middle changes name. Otherwise, it would be longer than the Champs-Élysées, and this would be impossible, right? But anyway, it's the longest street in France, as far as we know. All right, so What are we interested in? We are interested in developing machine learning methods that allow robots to be in conversational groups, right? So we are not going to take care of the dialogue part. That has nothing to do with ChatGPT. It's not our expertise. But there are plenty of things to do before we get there, right? So when you have a robot that is discussing with three, 4 people, you need to know where the persons are, who is speaking, right? If there is some noise, you need to get rid of that noise, and then you need to somehow teach the robot to act appropriately in the conversation, right? And we are trying to do all this with machine learning as far as we can, and then there are some other things that are dealt in a different way, as Jeremy was saying. There are many engineering things that you need to do when you want actual systems to work and to address an application. So in the menu today, I will briefly discuss a few topics, and then I picked up 2 topics in which I will describe a bit more technical things. There are going to be a few equations, so it's going to be less fancy than Jeremy's talk. But yeah, I am a mathematician, so I don't know how to do things otherwise. So as I said, if you imagine that a robot has to be around this kind of mingling event and discussing with people, of course, it has to, navigate safely. That would be the first thing, right? That's a condition, a requisite. But then it also has to participate in the conversation, right? Otherwise, it's completely useless. So you need to know where people are, who is speaking to whom. Are they in groups? Are they like a single? They don't want to be chatting with someone, or they want to be chatting with someone. So you have to discuss to address all these issues. And one characteristic is that it's going to be very difficult to have tons of annotated data that are, let's say, ecologically valid, that come from this environment, because this is going to be very expensive. It poses problems in terms of privacy. So it's we want to avoid to need huge annotated data sets from the final environment, right? So we will be looking at techniques that allow us to reduce the amount of data that we need from this situation. So one first thing we're interested in is multiple object tracking or multiple person tracking. This is a video of one of the standard data sets to train and evaluate such methods. And of course, you can see that there are many issues here. The first issue is the resolution, right? You have many people in the screen. Of course, when you have a robot discussing, maybe that's not going to be an issue because people will be closer, but still you have occlusions. You need to re-identify people when they reappear again in the scene. Okay, so all these are problems that you have to deal with even when you have a robot. So this is what we are interested in. This we are also interested in audiovisual tracking. And why do we want to do that? It's because many cameras have like a limited field of view. So many, let's say, consumer robots, we are going to see part of the scene. Right? But audio is hearing everything. So if you manage to combine these 2 modalities, you can actually exploit visual localization information within the camera field of view and audio localization information that is, comes from everywhere, but only when people are speaking. Right? So you don't have, there is no good choice. You have to merge the 2 of them. And of course, you need to do that in an unsupervised way because you don't want a human annotating all these things, right? It is you cannot think about that. So another thing we're interested in is generating robot behavior. Of course, if the robot has to be in the conversation, it has to do all these gestures that acknowledge that the robot is engaged. And when it is speaking as well, it should be doing some gestures that go with the speech. Right? So we are taking a look at these topics, either with adversarial learning or with more, let's say, standard supervised learning technique. We are also interested in understanding, so this is a bit like of a slide thing, complex multi-person interactions. I had a PhD student that was really motivated for this problem. It was so motivated. She was so motivated that she convinced me somehow to record a data set of acrobatics. And of course, you cannot recognize me, but I am on some of these videos jumping around so that she could have data to train her model. All right, so that brings us to the first application or the first topic that I wanted to discuss in a bit more in depth. This is joint work with one of the PhD students in the group, show you, and then two professors, one in Grenoble, Laurent, and Simon, which is in Rennes. And here we're interested in speech enhancement. So speech enhancement, for those that might not know, it's very easy to understand. You have a speech signal that, you know, at the beginning it was clean, right? When we speak, we have clean speech. Then there is some noise that comes along from the fan, from something outside, whatever. And this is what the robot hears. And of course, if the noise is mild, whatever, probably Google ASR will get rid of the noise. But if you have strong noise, this is not going to happen. And your ASR and every downstream task is going to be affected by the fact that you have this noise. And in our case, because we don't know the kind of noise that we will be hearing, because we don't make assumptions in or too strong assumptions in the environment we are going to deploy the robots, this means that we have no idea how this noise is going to look, right? So at training time, when we are in the lab, we have, you know, data sets of clean speech data. That's fine, but we don't know how this is going to look. So we would like to have setting in which we can use clean speech data sets for training, but then the noise has to be dealt with at test time. So we are using for that probabilistic models, deep probabilistic models. So this is a quick reminder of how a VAE looks like. A variational autoencoder is basically a probabilistic model that is implemented by a deep neural network, right? So you have a latent variable Z, which is supposed to be some kind of compact representation of your observation, and this is going to be for us a clean speech, right? So VAEs make an assumption is that all the samples that you have in a sequence, the order doesn't matter, right? So basically, this is what I express here by saying that the probability of the sequence is just a product of probability. This means that I could actually, so this doesn't look like speech, basically because it's a speech signal that you can see next slide, that has been permuted over time. So this is how a VAE sees the speech signal, because it doesn't have any notion of temporal order. And of course, for sequences or data like speech that has a temporal consistency, this is the problem. This is why we have proposed these dynamical VAEs that are, let's say, temporal extensions of VAEs, if you want to think it that way, and that therefore can also model the temporal dynamics of your sequence. So if I want to be a little bit more, say, diagrammic, a VAE would be this, right? You have one latent variable and one speech, right? And now a DVAE, what it's doing is that, let us ignore this part for the time being. It is assuming that you have a sequence and that there are relationships in between the frames of this sequence, right? This is just an example. You could have autoregressive relationships in S or in Z or both. Okay, so you have many choices here, but the idea is that you would like some sort of temporal modeling of the speech signal, right? So this is what we can learn in the lab. And then you have the noise that is added to your speech signal, and this is what will be actually observed in test time. So basically your speech, the clean speech, is now a latent variable that you don't have access to. You only have access to the noise, and you have to learn the parameters of this noise model. So I will skip the math here because it's a very long process to get the variational EM algorithm, but what you need to understand is that this is pre-learned and then it's deployed, and what is learned at test time are the parameters of the noise that allow us to then infer the clean speech signal, right? So this is how we recover the speech signal from noisy bus. Now, a bit of results. Like this appears that way. So we are using this scaling variance signal distortion ratio. This is the higher the better. And we did two kind of tests. The first half of the table is I am pre-training on the speech data set, number one. And when I test, I also test in this speech clean data set. It's the same thing, right? And I am comparing a supervised method, which has clean speech and noisy speech. So basically, they have a lot of information to supervise. With our noise agnostic here, and then a noise dependent that is basically learning the noise beforehand. Sorry. And what we observe is basically we have similar or even better performance on the supervised method, which is super nice. And this is the case even when we change the clean speech data set, because in here we are making the assumption that the clean speech is going to look similar in the lab that with crossing this data set, and we had very, very nice results. If you want to hear them, I wasn't sure that we could hear them. So if you want to hear them, you can go to the webpage in the team, and you will find many sounds to click on. All right. So the second topic we wanted to discuss is more on the action side, right? So we worked a bit on speech enhancement. That's a perception of the robot, and then I wanted to present also this work, which is on the action side. And here, what we are dealing with is with a robot that has to navigate and join a group of people. So you can think that you can do that maybe with deep reinforcement learning, but you have two issues. The first issue is data. Right? If you train from scratch, that means precisely that you will have people around, and then the robot will start moving randomly, purely randomly. Right? And then people will have to stand there for hours and hours until the robot figures out that maybe it has to get close to a person. So of course, this is not the right way to do that, because people will not be standing there for hours. And we have to find a way to maybe retrain the robot so that then when we deploy it in the real life, it can transfer information from the simulation. And to do that, we are going to be decomposing the reward function into a set of features that the robot could use for the task. So for the navigation, you could think that the robot can use the distance to humans, its own speed, distance to objects, right? And weighting these different cues, it might be able to figure out how to get to this, right? So as I said, the idea here would be to train in different environments, so that then when we deploy the robot, it can say, okay, this environment looks like environment 23, so I will start from that one. So of course, when you train that, if you train each environment from scratch, it's going to take a lot. So the idea here would be to train on environment number one, and already when I'm going to train environment number two, I am going to try to use what I have learned in the first environment. And when I will train environment number three, I will try to use what I have used in the first environment, right? So I will be, even during training in the lab, I will be trying to transfer as much information as I can through the various environments. So what's proposed in the literature is that these different environments were basically different linear combinations of the features. Okay, these features would be the distance to the person, the distance to objects, or whatever is relevant for the task. And what people were assuming is that, okay, my different environments are going to be linear, right? But of course, in real life, this hypothesis doesn't hold. Like if you think about the distance to persons, when the robot is very far away, I simply don't care. Maybe when it gets a bit closer, there is some sort of linear relationship. But when it is too close, it becomes really non-linear because it's, getting to my personal space. So there are many other examples, and we decided to get rid of this linear constraint and to propose a methodology that would allow to have non-linear functions of these cubes. So this is a very nice and wishable thing. The problem is that then all the operators and algorithms that were there do not hold anymore. You have to re-demonstrate and prove everything. But after a bit of work, you manage to do that, and you're very happy. And I think I have now a few results to show. Not in the navigation task, unfortunately, or at least not with humans, because as Jeremy said before, one thing is to do your simulations, and then another thing is to implement that in a system. So now we are in the step of implementing this on a system, and hopefully in a few months we will have results in that. Right? So for now, we implemented this this task, which is you start here, you need to go there, and then you need to pick up these objects that are in the scene, let's say. And depending on the task, the value of these objects changes. Okay, so these are the different tasks, right? So this is much simpler than the robot navigation. We fully agree with that, but still it allows us to prove our point. So I'm not going to discuss fully these charts because it's a lot of information. Just that. So the orange, which is what we were proposing, outperforms the linearly constrained method. Okay, this is as expected because we are more general. So it is highly expected when you have general reward functions. We were not expecting this difference here because this is evaluated only on linear reward functions. And still we managed to find a better way to solve the task, even when there's only linear constraints. All right, so this is a bit larger than what you expected. So this is what we could do so far with the robot. It took us maybe 2 years to have a robot that basically gets to one person and just places itself to start a discussion, right? I'm saying that because maybe, we don't realize, but the first thing, students were fed up of standing in front of the robot, so we got that. That's for you to understand that, yeah, it takes a lot of time. But then when we are seeing this, what does this mean is that it is tracking these people, okay? It's understanding that here there is kind of a group, so it shouldn't go into the middle of the group. It's understanding that there are some obstacles here, and then finding a path that is socially acceptable to get and to discuss to some. So that's very easy to say, but it takes a lot of effort to make it work in a real platform, in a robust way, right? Of course, if now we place these people in another part of the room, it's going to work as well, right? All right. So, well, I think this is my conclusion in the sense that, as you understand, we avoid using data from the end user environments. This is very important for us. So here, to do that, I think the only thing that we have annotated is we have basically fine-tuned the tracker because the robot has a fisheye camera. So on the edges, the people are distorted like this. So we had to kind of fine-tune that. But that's the only thing that we have taken from this environment. The rest was done in simulation.
So let's start. Please, Karim, so we can start. So it's a pleasure to have François who is research director of ILLS.
working at Sorbonne University and associated with ISIR. It's an expert on natural language processing, linguistic translation systems. So, François.
Thank you for the invitation and also for the presentation. Okay, so just before I start talking about language models, I will just give a brief overview of the work I've been doing in the past, mostly in Paris-Saclay at Nissen. I'm just in the process of moving to the new lab, and I will be joining Nicolas' team very soon. So I have divided my activities into like 6 blocks. I'm only going to talk about one of them, but just to mention briefly the rest. So in the past years, I've been working on computational language documentation, that is building tools to help linguists that go on the field document languages that are fully documented, collecting samples, annotating samples, adding linguistic information. This is a very important process, very time-consuming, and these people have hardly any tool. So we have been trying to help them mostly using probabilistic modeling to speed up segmentation and also annotation of speech data. In blue, this is all I've been doing in terms of machine translation. So in the recent year, I've been working on retrieval augmented machine translation. Machine translation, where you also want to look at samples, at research sample in the process of translating, how you can improve your machine translation with samples through using non-autoregressive machine translation techniques. This is joint work with people at Sistran, a French IT company. I've been working also on multi-domain machine translation, again with the same group of people, where the difficulty is to build a machine translation system that work well for all domains. So we know that machine translation in the domain of law might be very different from machine translation in the domain of finance, and very different from the machine translation in other domains. So what people typically do, they would fine-tune the system for each domain. But I mean, if you're a company, you would like to have one domain that works well in all domains, maybe also adversarially in all domains. So that if somebody picks a very bad domain for you, can you do the best you can? So we have been thinking at these issues with mostly Fanning Pong during his PhD. Something that is really dear to my heart is a work on working with my text, trying to read or write in several languages at the same time. So we know that professional translators spend a lot of time either writing or reading by text. For instance, to check translation, they need to read the French and the English. I mean, Canada, you do this all the time. And of course, it is difficult, and we have very poor tools to do this. So we've been working on both interaction procedures and also models to help this process. Recently, developing a first prototype to write simultaneously in 2 languages. This is interesting, I think. I have also a large project on developing NT techniques for open science, where the goal is to translate basically all the science that we have in our archives. That is, most of it is today in English, to translate it at least partially automatically in French, so that we can also have this available in another language. And this is joint work with a group of people who have a large French project just starting this time. And then, this is what I will talk about today. I'm working on multilingual language models, mostly in the context of transferring information or annotation across language, where you have a model for language A, and you would like to transfer this model to a language for which you have very little data or no data at all. This is something that I've been doing for maybe last 10 years with all the people. And this is what I'm going to discuss a bit today, presenting our most recent work. Okay, so just before I start, a very brief overview of NLP, or the way I can introduce NLP. So NLP is mostly 2 things. So NLP is about developing techniques that will help, that will help understand language. And also perform some basic language analysis tasks, such as converting an input signal to a stream of phonemes, or segmenting this stream of phoneme, or annotating streams of words like you have here, like a sentence, and you like to annotate this sentence with grammatical categories and also with a grammatical structure, taking the form of a labeled dependency tree here, where you can mark that, for instance, piqué is the main verb of this sentence and cousin is the subject of piqué. You want to do this automatically, and maybe develop theories about how syntax works in various languages. So you will need to build models for different how you can learn these models and what this model tells you about the language. Then linguistic analysis is also about building semantic structure. So this is even more challenging because the semantic structure is not as simple as a tree. It can take the form of a labeled graph like this one, where you have also reentrancy. And also there is a task like semantic disambiguation, where you would like not only to find that you have a string of character, but you can ground this string of character maybe to an image or to a concept in the world, like what is a cousin. It can be several things. A human being in your family. It can be an insect. And there is a third meaning of cousin, the cousin d'Amérique, well known in France to denote people living in Quebec. So I use it for the time. Okay, so this is linguistic analysis, and all this is related to traditional linguistic categories, but also NLP more and more is about application. So we know that we can develop now tools that process human language to do many things. So this is an illustration of automatic speech transcription, and also in the process of transferring speech, you can see also that some words are underlined. In orange, you have proper names, nuns of people, and we know that we can do this now with a very high confidence. So this helps, for instance, index speech signal with people's names or with mention of events or facts. And I mean, with ChatGPT, I don't need to go at length about this application. We know that natural language processing has many applications that are now reaching the general public and are also increasing the expectations about the robustness and the quality and the performance of these things. So how has this? So why is this first difficult? There are many reasons why this is difficult. As I have tried to write on this slide, we have various problems that we typically view as machine learning problems, but most of them boil down to learning or to annotating an unsegmented string of something with labels or with more complex structures like trees or graphs on top of this unsegmented stream of symbols. So almost all the tasks that I have mentioned can be viewed in either of these categories. So either sequence specification or sequence labeling or sequence transduction, mapping a sequence to a sequence, or sequence parsing. And this is difficult because typically we don't observe the boundaries. We don't observe the boundaries in speech. We don't observe word boundaries in many languages. We don't observe the sentence boundaries when we try to analyze speech, for instance. So the boundaries are unobserved or ambiguous at least. We have a wide ambiguity in all the units. So words are ambiguous, morphemes are ambiguous, phonemes are ambiguous. So everything is ambiguous in language. So at any step of this analysis, we need to disambiguate what we process. There are very strong rules or structural constraints about what is possible. At least when we look at parsing or building a morphological syntactic analysis, but we don't know them, so we don't observe them. So we know that some structures are literally impossible, but it's part of the theories we need to build. The alphabets we're manipulating have an internal structure that we don't know about. So there is if you think of words, there is a structure in the lexicon. Words are related in some way. So some words are from the same family, some words derive from other words, but all this is unobserved, and we need to, when we learn our systems, we need to also learn this at the same time, the similarities between words, for instance. And there is a lot of variability in the data distribution. So there is not like one French, or there is not one English, but there are many varieties of English with both intra speakers and also geographical and also sociological variation, and according to many dimensions. I have mentioned some of them. So when we process samples of language, we need also to be cautious about this variability in the data we manipulate. As of the mid-90s, all these problems that were thought to be extremely difficult were finally approached in the same way with basically machine learning techniques. So there has been a radical shift in the domain that has been taken, that had started almost 30 years ago, where everything was looked at with the lens of classification, which was the best machine learning tools we had these days. And for a number of years, people have tried to reframe every problem, for instance, syntactic analysis, predicting a tree, as a simple classification problem or a set of classification problems. And this trend has been extremely successful. There is a very well-known paper about the unreasonable effectiveness of these techniques for for NLP. Such that, I mean, for most of the tasks that I've mentioned, we are close to solving them, at least in English. And of course, you know that these days, I mean, these techniques, these machine learning techniques are even more powerful. We've been using neural representations, so that have helped us to make a huge progress in the past 5 to 10 years. And now with transformers, we have a very extremely powerful tools to perform also sequence analysis for many tasks. So, and I'm going a bit quicker. So we know that with these large models that we can now train, we can solve not only first, these large language models, we have several ways to train them. So we can train them as pure encoders or pure decoders or encoder-decoder models. But no matter how we train them, once trained, this model will help us to perform many tasks. And in particular, people have realized that the representations that you train are extremely useful to make any kind of classification task. So once you pre-train a model, you can learn a classification that will take any email on classic into spam or non-spam with a very high probability, with a very high confidence, much better than the model that we had before neural models. And also we know that if we just look at the causal language models, so the ones that act as a pure decoder, we can turn them into multi-purpose or multitask tools via prompting. So this has been mentioned yesterday in the context of image, but I mean, we do the same in speech. And of course, you can take a lot of questions, a lot of tasks, sorry, and turn them into simple prompts so that the causal language model will be able to perform them. So one task, for instance, that is well studied in NLP is question answering. So you would like to ask a question to a model, and you can frame this as a pure language model task where you frame your question as a prompt, and then let the model generate the answer for you. So basically, any language model, once trained, can be turned into a lot of various applications. So this is fine. This is fine because these models are now well understood. We know that we can train them at scale with a huge amount of data, and that this training can be done without any annotation, which was like a bottleneck in the previous approach. We needed an annotation. Now we can train this model without annotation. So there are many new techniques to train this prompt so that we can even improve on the performance through learning or through fine-tuning. And this approach is extremely successful, at least for some languages. So for what we call high-resource languages, like English or French or German or Chinese, this has been extremely successful. However, we also know that the size of the data matters, the size of the model matters, and the size of the annotation that we have to fine-tune this model also matters. Now, I'm turning to the more interesting part of the talk. And sadly, for most, we have a lot of languages to cover. I mean, this is like a distribution of the world language. So we see that there is a huge density of languages in Africa and also in Asia. And so the current estimate is about 7,000 languages, most of them not written. The majority of them are not written. So the question is, what can we do for all these languages? I mean, we have good technology for English, okay? We have good technology for French, but what can we do for all the other languages for which we have not so much? So this is starting to be an issue in NLP. So there is a rising concern about developing solutions or tools or applications for all these languages. And so people have started to look at the resources that we had. And in fact, for most languages, we have hardly no resource. So this graph is a bit difficult to read. So this is in log scale, the size, the amount of unlabeled data that you can find. And you see that you have a small group, small cluster of languages for which you have a lot of unlabeled data, particularly Wikipedia or the web, basically. And what you can see here is that there is, if you look now at the distribution of labeled data, so the numbers are much lower. So data for which you have like a linguistic annotation that can be used to train a system, the numbers are much lower. And you can see that, in fact, you cannot see, but most of the languages lie on this axis. So that means that literally zero training data, zero label training data, even though you can find like a lot of unlabeled data. So in this paper, they perform this kind of analysis, classifying the world's language into languages for which you have a lot of resource, a few of them, and the majority of languages for which you have hardly any resource. And you can see like some top, some languages in all these classes. So the high resource language on the upper corner, English, French, Spanish, German, etc. And so here you have the number of languages. So in the high resource class, only 7 languages. And in the very low resource class, sorry, more than 2,000 languages, and with hardly any resource for them. And this is the majority of languages that are disabled. Okay, so this is the situation, and the question is, what can we do to train model when we have so little data and available? Okay, so what people have developed as a solution is to build multilingual representation. So representation that can handle more than one language, and use this multilingual representation to transfer information across languages. So basically, the goal will be to learn word embeddings, as you would do for English. So in English, you expect that words that are close neighbors are also like semantically related. In this semantic space, you now expect that in the close neighbors should also be mutual translations. So not only semantically related in the same language, but also mutual translation across languages. So to do this, the first step is to make sure that all language can be viewed in a unified way. And the solution that has been adopted by the community is to forget about the notion of a word and to just manipulate character strings. So basically, in these models, what you use as a basic unit is not a linguistic word, but just a stream of character that you will segment automatically through automatic techniques that are extremely simple, but that have the advantage to work at scale for any character set. So this is typically what a multilingual model will see. It will not see, for instance, the word less, but it will see the character string now, followed by the character string ILLS. So this is this has the advantage that some of these character string they can occur in multiple languages. So you don't need to worry about it. And it's also important that to realize that nowadays people are not simply working with character, but they're working with byte representation. So you forget about character level and you segment everything in 2 streams of bytes, because you have to handle also the multiplicity of scripts. people in the world language. You can find the Latin script, but also Chinese script, but also Japanese script, but also all the English scripts, etc. So you have a lot of script to handle, and for this, using byte level representation is much more efficient than character level representation. So once you've done this, what you can do is you can do exactly like you do for monolingual models. That is, you take huge corpora, you turn your sentences into this kind of basic units, and you train a BERT system or a causal language model as you would do monolingually. So this was already experimented with BERT, with the first version of BERT a couple of years ago, and people were really wondering, how is this possible? I mean, you take you mix sentences in Chinese with sentences in Italian and with sentences in Japanese, all of them together in the same model. You train a language model, and at the end, without doing anything more, you get representation that have the property that translations lie close in your embedding space. So this has been experimented with all the architectures of models that I mentioned, so pure encoders or encoder decoders or pure decoders. And as I will discuss, I mean, these techniques are extremely effective. They are even more effective if you have additional loss. I'm not going to discuss them to bridge the gap between languages. So if you have on top of this parallel corpora that will tell you this sentences, the translation of this sentence, and you can also add this in your loss and improve upon just using sentences. Okay, so once you've done that, there are many things you can do. So you have a huge multilingual model that looks like a monolingual model, except that it's multilingual. So what can you do with this? You can do, for instance, as I will explain, cross-lingual adaptation or cross-lingual transfer for free. You can do machine translation. So for instance, you can prompt your system with translate this into English. So it should be translated to French, sorry. And then you would have the system generate the French after the English, because the system, in fact, doesn't know French, it doesn't know English. It just knows strings of characters, and if trained well, you can expect to have this kind of behavior. What is nice is that it's hardly more difficult than monolingual training, because it's exactly the same technique, so you don't need to change anything to your model. And it helps to bring a low resource language if you can add them into your language mixture up to speed, because I mean you can use cross-lingual transfer techniques. So just to illustrate how cross-lingual transfer would work. So once you have trained your model, you can take an English text, use your model to compute the representation, fine-tune the model in English, and then predict your clusters in English. Or you can do the same in French with the same representation. So you have French, you will use the same model. Okay, you can fine-tune in French and have a spam classifier in French. Okay, but this would need to have two models. So what you can do even better. You can train your system in English and use directly French as the input. Okay, but given that you have like a joint representation space for French on English, the clustering you've learned in English will apply also to the representation of French. The only thing that you need to have in this model is that a French sentence should look like its translation in English in this embedding space. And this typically you get for free, more or less, if you use multilingual models. And of course, this is extremely useful because I mean, if you need to build a hate detection system for hundreds of languages, for which you have hardly any annotation data to detect hate speech, you can train a hate speech detector in English with high confidence. Take any sentence in any language, turn it into like an English-like representation in this embedding space, and classify it as English hate speech. And that's great because you don't need even any annotation, which is a typical situation. You don't need any annotation to perform this. So this is extremely useful, and it has been proven extremely effective for many languages. So I mean, you can look at the reference at the end of it. What I'm going to discuss a bit more at length is the work that we've been doing in that general space. So one thing that we wanted to check is the hypothesis that in this embedding space, words that are mutual translation are in fact neighbors. So for this, we looked at a very old task, word alignment. So word alignment is the task of finding one-to-one mappings in translation. So people have been looking at that task for many, many years. So one of the purpose of this task is, for instance, to learn bilingual dictionaries. So you have a sentence in English, a sentence in French, and you would like to say, okay, proposal should align with because that's the translation of proposition. Okay? So this task has been performed for many years with the probabilistic models, and these models were extremely difficult to improve upon, but they needed parallel training data so that we can train the model. So these models are known as IBM2, IBM4, because they were initially developed at IBM in the 90s. And they've been like the state of the art for almost 30 years. So what we did is we took a multilingual alignment, multilingual embedding space computed with NVERT in that case, but also with XML, R. And we simply use basic graph matching algorithm using, so we start with the full bipartite graph, okay? And you weight each arc with the similarity of the word in the embedding space. Okay, and then you can find like minimal matching in the bipartite graph, or use like a more clever algorithm to solve this problem. And in fact, just doing this, so we have results for more languages. We were able to improve about the state of the art, like in some important with a lot of with a huge gap with respect to the previous state of the art. So you have the numbers here. And since people have been developing these techniques a bit more with adding a layer of training on top of this, and the numbers for German, so before there were like 23 for the best system, so we went down to 20, 21, 20. Now the numbers are 14. Okay, so I mean there were great improvements with this technique. So this means that in fact the embeddings we compute in this multilingual space, they really do what we think they do. And the good point is that without any training, for free, we get word alignment system, not for 2 languages, but for 100 languages, because these embedding spaces, they contain 100 languages. So without any training, we could develop word alignment techniques for 100 to the square languages. So in a recent work, we have been redoing this, not for 100 languages, but for 500 languages. So this work will be presented in July at ACL. So basically, we've been working with much larger set of languages with a lot of difficulties just to collect the data, clean the data, make sure that the data is in the right language, and deal with all the character encoding and all the noise in the data that you can get. So this has been a huge effort by a group of colleagues, mostly in English group in Munich. But now we have like multilingual models for all these languages, so we can do the same. So we can have word alignments for free for not 100 to the square, but for 500 to the square pair of languages. Of course, this kind of venture is also interesting because it gives us more data to understand the way a cross-lingual transfer can work across languages, because we have data now for many languages from the same family. We have a lot of African languages, we have a lot of Asian languages, whereas before we only have mostly Indo-European language. Okay. Another work that I have done recently, I'm not going to discuss this a bit. I've been working on trying to evaluate how well this representation would allow to perform machine translation. So how well, when you use a simple prompting technique, you can in fact generate good translation systems. So we've been doing this for this Bloom large language model that has been developed as a product of a collaborative initiative last year. Mostly with the compute mostly performed at ILLS. very close to here. So again, I'm not going to develop this, but I mean, compared to the previous evaluations that were only looking at a few corpora and a few numbers, we have been trying to look at a lot of more language pairs. So here you have we are trying to look at whether this model is good to translate high resource language to high resource language. So we did this matrix with Arabic, English, Spanish, French, Chinese. Whereas, I mean, remember, most people only looked at French English, which is a very simple pair. So we looked at more pairs. We also looked at rarer languages like Indonesian or Vietnamese or Hindi and the way it translates. And we compare this with the other state-of-the-art model, with the conclusion that these techniques, in fact, they provide the ground for very good translation model, which is a surprise because, I mean, they're not trained for translation, but when you use them out of the box, you can, in fact, develop very good translation model. And in fact, it's the experiment of anybody these days. You can use ChatGPT as a translation model, and it works very well, even though it has never been trained for translation. Okay, so there are some caveats. One caveat is the content of this multilingual corpus that we use to train these multilingual systems. They are very unbalanced. And what can we do about this? I mean, typically English is the dominant language, and even Bloom, which is more balanced, has a huge unbalance towards English, where you have 30% of the data is English, whereas African languages, they have like a small, very small fraction of the data. Okay, so just to finish, because I think I'm running out of time, why can this work is a pressing question, because I mean, we don't inject any form of linguistic bias in this model, and still they learn something of the linguistic structure. So people have been trying to understand why this is the case. So they have been trying to see whether lexical overlap is necessary to have this alignment between languages. And in fact, it's not the case. One thing that breaks alignment of language is reversal. So if you take the same language and reverse it, you cannot no longer train good multilingual spaces. And we know also that vocabulary alignment helps, and that typological similarity between languages also helps. So I'm going to close with this set of open questions that I think is interesting for the statisticians. We don't know what is the impact of language distribution in the training data. So how having a few examples of one language will really help this language. We don't know the impact of model size. We know that languages are competing for the parameters in the language, but should we increase or should we not increase the model size when we add more languages? It's an open question. Our recent work with 500 language show that it's not necessary to increase the language, the model size to have improvements in performance. What is the impact of the number of languages in your model? We don't know. Which linguistic properties are important or can break the model? And this is interesting because for a linguist, we're really looking at like linguistic properties that go across languages, that are also somehow universal. And for linguists, it's really interesting to look at this universal in linguistics. And also, we don't know what is coverage. That's, I mean, I think it's the most pressing issue. If I ask you how many languages does a ChatGPT cover, we don't know. When we don't know, we can try. It will maybe do some very well in English and do some French and do poorly in Hebrew, but we don't know whether Hebrew is covered or not really at all. Okay. And then other open questions that I will stop here. So this is my conclusion. And the most important thing is that this multilingual model, they can help a lot and make us progress towards handling the low resource languages, but we still don't know why. And if we knew why, we knew better how to improve them. Okay.
Thank you, François. Let's take a couple of questions. Yeah, please. Yeah.
Thank you for the talk. It was really interesting. And you said that vocabulary alignment and logical similarity, it helps. Do you mean you represent it as features, as an input data for your models, or how we measure that it helps?
Well, I mean, for instance, in the paper, we got present next month. We had new languages in our mixture of languages, and for these languages we observed no improvement. Okay, and so we were wondering why is there no improvement with our larger model, and it's because in fact they had very close neighbors already in the training set. So that means that so this is a way we can detect this, but in fact it's difficult because we don't have a good measure of similarity between language. So we have what linguists tell us, but what we have in corpora is a result of, the human activity on the human labeling of languages. So people have, developed their Wikipedia, say, in Czech. Or you can have a Wikipedia in Mexican Spanish, for instance, and that will be a political decision. But how different is this from Castilian Spanish spoken in French? There is a very little difference. So you would say, okay, there are two languages, but in fact it's the same language or two dialects of the same language. So we have to handle the situation, or we cannot control this. So we get corpora, we have labels, but we don't know how related these labels are. So we need to look at performance and see, okay, this language helps in the mix, or this language doesn't help, or this language is helping this language. This is the kind of questions we are trying to address.
Yeah. Thank you. So, other question. So you talk about different languages, but you don't talk about genre. The different genre that the text has. And in some experiments before, we thought that in fact it was more important, genre was more important than language with this kind of models. And also, you were talking about Wikipedia. A lot of languages have Wikipedia entry, and then so you have a parallel corpus for many languages. So what's the effect of and with similar genre? So did you notice differences for languages we didn't have, for example, Wikipedia pages, and we were in completely different genre, like more spontaneous text, chat or this kind of thing, than languages which are more like standard. Based mostly on Wikipedia.
Yeah, so I mean, in the study I was mentioning, interesting. I mean, because for some languages we found that they were really far apart from the others, and one of them was because mostly what we had is a user-generated content, like tweets or stuff like that. That was really far away, both in language but also in genre. In the studies that we have been doing with that group, we try to control the genre thing by using at the most parallel corpus that we have in the Bible, where we have text for more than 1,000 languages. So using text, we can this corpus we can control for the genre and look at differences that are like within the same genre. But I agree with you that sometimes, I mean, genre differences are also very important, sometimes more than language issues. And as I said, I mean, sometimes one blurs into the other, because I mean, we know that some dialects are only used for typical kinds of interaction. That is, I mentioned code switching. So you can say code switch language. So this is good code switch language, but I mean, so text where you mix several languages when you speak is only used in typical like friend interactions and stuff like that. So you don't find them in Wikipedia. So the genre issue covers partly the language issue.
Thank you so much for the introduction. Yes, in March I started CPG, which is Chair de Professeur Junior at Listen. Before that, I was in Geneva in Swiss Bioinformatics and TESO. Actually, you mentioned that it is completely different application now. I did my my background is computer science, computational linguistics. In my master's, I did bio-NLP, not so much in my PhD, but then in my postdoc, I did bio-NLP as well. So it's basically the continuation. So I'm going to
I'm going to introduce listen for those of you who are not familiar with it. It's a multidisciplinary, interdisciplinary laboratory for digital sciences. It has, you see the entrance of it. So there are two sets of buildings, one in Belvedere, the other one in Glen. And we are in Belvedere, and actually there are 5 departments of it. One language technologies that we are in. The other is human interactions, and help me, machine learning and data science and mechanics. So in language technologies, we are 3 groups focusing on different tasks like speech recognition, as François was mentioning as well, sentiment analysis, question and answering, machine translation, and so on. And then, so here I'm going to present some of the work that is done in Listen, and then I talk about my own work here that I've done in postdoc. Okay. I don't know if you know Pierre Seckenbaum. He is a senior researcher in CNRS and Listen. He has been, he was the leader of Listen, the leader of language technologies for 7 years. So this is one work that they had with the students on normalization. So I don't know how many of you are familiar with name entity recognition. So in name entity recognition, we have the text, and we want to know which entities exist in the text. So for example, diseases, organisms, and different entities. But then when we extract these entities, sometimes they have different meanings. They have similar surface, but they have different meanings, right? So we need to disambiguate them. For example, flu. We don't know when we extract it. We don't know whether it is stomach flu or influenza, right? So we want to get more information with normalization, okay? Or entity linking. So this task, the very easy way of dealing with it is rule-based, basically looking at which, okay, before that, we usually use knowledge bases and dictionaries, vocabularies to solve this task. For example, I don't know how many of you are familiar with UMLS or MESH. So there is and they have hierarchies of entities, and they show the relationship of these entities, these concepts. So we use these knowledge bases. And the very simple way of doing it is looking at the words that appear on the text and appear in the knowledge bases, okay? So when we have many words overlapping, then, for example, we choose that one. That's a very simple way of rule-based. There are also machine learning ways of doing that. We consider it text classification. And in text classification, we, for example, look at the representation of the text and the representation of all the concepts in the knowledge base. And then, for example, we use cosine similarity or any similarity-based measure to compute the similarity of these two and assign that concept to the text. So here, what they did, that they created a new concept. They created the concept embeddings and used the concept embeddings for the normalization that they did. And they basically use the biotopes. So the different entities here you see, for example, the habitat is contaminated retail chicken meat, and other entities, phenotypes, and so on, microorganisms, and basically they want to know which concept in the knowledge base this text refers to. Okay, so this is the ontology ID that they assigned. The other task that they considered was syntax in relation extraction. Syntax, what we can use, for example, the noun phrases, verb phrases, and the dependency parsing that we have from the text, and combining it with the basically adding it to the representations and into the models to improve the extraction of the relations. So, for example, the relation here between the caffeine and checkpoint kinase ATM. Yeah. So basically, adding the relationship between the syntactic relationship between these mentions or entities to the model to improve the relation extraction. The other work was, so basically improving the word embeddings or representation. François mentioned about the representations of the text. So here they use the two knowledge bases, Mesh and SNOMED, and created using the node to vec the representation of the concepts and concatenated them to the concept and concatenated them to the representations that they get from the, for example, the model that they use. So I don't know, yeah, it's here I think they use ILLS, not very, but. So in a medical and clinical text, as François mentioned, we use BERT and transformer models. They don't look at the tokens, just the tokens. So they have subtokens. For example, here, the subtokens of app and the rest of it. And then the models are trained on these subtokens. So in biomedical literature, because using these subtokens, sometimes we have out of vocabulary, and so we don't get a very good representation of them. And so here the idea is to use the character embeddings, character representations to improve the embeddings and basically in any task that we use after that, any applications that we use in these embeddings, for example, name entity recognition, relation extraction, to improve the task. So, okay, you are familiar with the adverse drug events, for example, I don't know, cough or fever or these type of adverse events or adverse effects. So extracting them, it's important, but it is also important what is the context, right? So it helps when we know whether the message or whether the sentence that they appear, it refers to the adverse event or not, right? So for example, headache. In one context, it can be an adverse event of, for example, COVID, and in other contexts, it can be just a migraine or something like that, right? So here, the idea is to classify the sentences, whether they have the adverse event or not. And because it is on German and they didn't have enough data, so the idea is to use to train the models on English and with a few shots of German and classify the sentences in German. So I'm also presenting some of the work by Aurélie Nevan. So this is the temporal information in clinical or in any text, and there can be some temporal events. For example, an exam can be done in a certain date, or for example, a hospitalization happens after an exam or something like that, right? So there are relations between the entities. So here, the idea is to find these temporal relations from the clinical context. Okay. So, you know, in clinical, for clinical tasks, there are not many clinical texts annotated. Or if they exist, they are confidential because they have disease information, the patient information, and so on. So people don't want to make them available. So here, the idea is to generate some synthetic data and examine whether this helps in the name entity recognition task or not. So here they used GPT-2 to generate text in two different forms. It is in French in two different forms, text and the text with the annotations. And they find that it is useful. So here I'm going to talk about a little bit on my own work. So as I mentioned, there are name entities in different domains. So here is a clinical domain with different entities. Beneath the entities for the other applications, finding the relations and so on. This is the clinical domain that you have the information about the reaction. So it's important to extract these entities. For example, starting material, reagent catalyst, and so on. So here we use the BERT model, which is the transformer model. So in these models, you train them first. The training is in two phases. One, you train it on unlabeled data. It can be on general data, or it can be on specific data. And then you fine tune it. You basically continue training or like initialize with the previous ways, and then fine tune it on a specific task. So here we use the BERT. We trained it on it, and we basically use the simple voting strategy between the models and extracted the entities. We showed that it improves using compared to individuals, using the individual models. So, and also on the clinical data, these are the clinical cases where certain the patient describes a certain disease, and then there is a diagnosis after that, or a treatment proposal or something like that. And it is in French. So yeah, here you see some entities like anatomy, pathology, so on. So we trained the different transformer models, such as BERT-based multilingual case, as also talked about it, and Camembert BERT, which is French, and BERT, trained on French documents, and we got good results. The other task is wet lab entities. So these are wet lab protocols, and So with different type of entities, yeah, reagents and so on. So you can also have some numbers and yeah, here we also use different models to extract entities. The other task is house misinformation. So many times, even us, we search some condition or some treatment on the web, right? So for example, if this tea is good for headache or something like that. So here the purpose is, the aim of this study is to see how we can find the most reliable data and reliable, relevant data on the web. So here you see an example is a typical sponge bath, a good way to reduce fever in children. So you can get an answer that it's not required, it's not good, or it is it reduces the fever. So we want to see which one is we should rely on. So we treat it based on different aspects. One, whether the data, the document or the document that we want to find, it's relevant or not. And if it is relevant, does it have the information that helps us decide this treatment is useful or not? And then whether the source is reliable or not. So we consider different models for it. Usefulness ranking. We can use BM25. So basically to find whether the document is relevant or not. For supportiveness, it is somehow relevant to claim checking. So I don't know if you're familiar with the checking, if claim checking or not. So you have a claim and you want to see whether the document has information to say that this is a validated claim or no. For example, the document refutes the claim. So basically we treat it as this, and then the credibility, we want to see, for example, the document, the source is credible or not. We know that, for example, the governmental sources probably, most probably are more reliable. And based on some surface information from the website, from the document, we can get some features and combine them together to see whether, the document that we have, whether it has good information regarding the treatment or not. So these projects, on these studies were supported by different projects. So some of them at Leiden and a couple of them in Hessel. Different publications.
Yes, thank you, Nora. Our next speaker is Frédéric Béchet. He is professor at the University Aix-Marseille. He is currently director of ILLS, and he's joined ILLS at the beginning of next year, January, if we manage to finish all the administrative work in between. So he's also an expert in natural language processing. So we're very happy to have you here with us, Frédéric. Please.
Okay. Thank you, Mario. So thank you very much for the invitation, and very glad to be here and to meet I think my future colleague in Montreal. So I'm going to talk. So title of my talk is Natural and Understanding from Classification to Generation and Back. So you see there's some overlap with what Francois presented before, but repetition is not a problem when you teach. You know, so we see the common part and the differences. Just to start. Oops.
It goes the other way. Is it down?
Oh, yes. Sorry.
It's not natural.
Okay. So just a little bit of context on what I was saying. So I'm at University of Aix-Marseille and at CNRS. So I'm the director of LIS, which is a big lab, which have a lot of university and people on different sites, which have a lot of also themes. And I work more specifically in the talent team, which is NLP team, which have a specificities to mix people from linguistic, machine learning, and cognitive science all together. And what you see there is a team meeting, a work meeting at in Marseille. And this is the view I have from my office. If you want to visit us, it's the campus is right in the campus in the calendar of Marseille. You are very welcome. So what I'm going to talk about this morning is so I'm going to focus on a specific part of NLP, which is natural language understanding. So I'm going to try to define exactly what it is, and then I'm going to show why we moved in a way from classification to generation and what issues came with this shift, specifically on the evaluation side. And then I will finish with some ongoing work and research direction. So NLP, is anything which can go from generation, from any kind of data to text. Analysis is going from text to any kind of other kind of data, or going from text to text. And when you deal with understanding, you deal with the fact that natural languages are both implicit and ambiguous. So if you don't want to live in a world where cops kill people with knives, where whales fly in the sky, and where there's an Olympic sport which involves dead bodies, it's better that you do explicit and disambiguation while you process text. So it's exactly what we're going to do here. We're going to try to make language explicit and remove ambiguity. So how can you check that your model has understood, what text, what it was processing? There's two ways that you can check that. There's one way which is through a formal model, and the other way which is through a task. So to present them very briefly. So from a formal model is what Francois was talking about earlier. You have a theory about language. So it can be a syntactic theory, semantic theory, discursive, whatever you're interested in. And then your goal is to discover the underlying structure of this language thanks to this theory. And then you are going to produce an ambiguous analysis. So this is a very, very simple theory about this sentence. I saw the man on the hill with a telescope, and these are the different unambiguous interpretation you can have of this sentence. So that's fine. If you have a theory, then you can perform understanding. Another way to perform understanding is through tasks. So you don't consider understanding as a goal by itself. You consider understanding as a way to achieve your task. So, for example, if you do question answering, you have several possible answers. You have to choose the right one. That's a classification task. Same thing with sentiment analysis. But a lot of these tasks are generation tasks. So the three main generation tasks we deal with in NLP is translation, summarization, dialogue. Okay, you need to generate text at and we see that these are very, very important tasks, of course, and we see how they influenced the rest of the other tasks that were before, just like classification. So one thing which is very, very crucial, because we're doing empirical research, we need to evaluate our models. And this is the key, and without evaluation, we don't do anything. So we need to evaluate our. When you are performing classification tasks or linguistic analysis, as Francois was saying, basically we do classification. Okay, we have a gold standard, which is supposed to be unambiguous, because as I said, understanding is removing ambiguity. So you have one gold annotation, and then you compare your prediction to this gold annotation. So maybe it's not pure gold, but you do what best you can, to have something which is as pure gold as possible. But when you deal with generation tasks, it's much more complicated. First of all, you say, okay, the main way to evaluate, for example, a translation system is to ask a human translator. Is it correct?
translation or not. That's fine, but of course, that's firstly subjective, and then you can't put that into your training process. It's expensive. So if you want to have an automatic evaluation, you are going to compare your prediction, so your text which is generated, with a kind of ground truth through a lot of, there's a lot of metrics which are being proposed, like bleu, rouge. So basically just measure the overlap between your ground truth and your prediction. This is the generative process. The problem, of course, is that there's not only one way to translate, summarize, or to perform dialogue with the user. So you are going to compare something which is, unlike via way here, not only one solution, but you are going to compare one prediction with one ground truth, but many others were also possible. So you can diversify a bit your ground truth and have several possibilities, but still, you won't cover, of course, the whole space of possible generated text for you. So I'm going to present now in a very fast way, but why? Because classification seems to be a bit kind of right way to evaluate classification tasks. Why? Despite all the problem with evaluating generation, we move to generation. Going to go very fast because François also spoke about that. So let's say that before the DNN era, basically what a pipeline architecture. So you do a task, and the output of your task is being put over the next task, and so on and so forth. So you can do sentence segmentation, word segmentation, part of speed tagging, named entity recognition, blah, blah. Okay, so this was fine, but this had major issues. One of the main issues, which is obvious, is that we're dealing here like every task is independent. And we know it's not true. When we process human process language, all these tasks are interdependent. So it's suboptimal to try to cut the system in different tasks. And then there's the snowball effect. If you make a mistake in task one, you will never recover in the following tasks. So this was not very satisfactory, but it was simple and kind of efficient. But when DNN came, we obtained a new way to think of this pipeline and to break it. And so how we did that? So we said, okay, we need one approach, which can unify all processes. This would be very nice. And then we need to have a unified representation for all tasks if we want to perform them all at the same time. And in fact, the model which were developed thanks to deep neural network were really fit to these two needs. The first one, for example, is learning representation work. Pre-training, learn, generic word sentence representation, thanks, for example, to masking tasks. So, like the big LLMs, François was mentioning, that's unsupervised learning. That's great. And this very rich representation. So yesterday we were talking about image representation obtained in an unsupervised way. That's the same thing. We obtain something so rich that after the fine-tuning to a given task is small. You don't need that much data. And fine-tuning can be done thanks to this pre-trained model only with a limited amount of supervised learning. And then you can do multitask. You can perform all the tasks at the same time. So the first, evolution or revolution we had in the last few years, well, the first one, but in the recent times, was BERT, BERT, the Swiss Army knife of NLP, which was the architecture which can be used to do everything with this simple architecture of pre-training fine-tuning. So this is very nice. And one thing which one of the consequence of this architecture is that the traditional pipeline disappeared. And so the need to have explicit representation at each level of a pipeline, like, for example, part of speech, named entity, even word, disappeared. you know, as input, you don't have words, you have sequences of characters. The words appeared in the network later on. Same thing with part of speech, named entity, even syntax. All these things the explicit representation disappear. So for the linguistic analysis, we are not really needed anymore into a pipeline which was broken and disappeared. But you could still find them, for example, in probing, trying to check what this model really learned. So you could use linguistic analysis as a way to analyze, you know, and probe what was learned by these models. So this was the first move. Second evolution, was to go from encoder to encoder-decoder, okay, sequence to sequence. And then you could use the same kind of technique that was used for translation, for example, to perform a lot of different tasks. In fact, you can put any task into a framework of translation or sequence to sequence. Why? Well, if you consider that a linguistic structure can be linearized, thanks, for example, to a specific encoding, like I don't know, you can linearize any kind of graph in a string, you know, like Penman representation or one. Then producing a syntactic parse, you know, of a sentence now can be just considered as translating a sequence of word in any language into a sequence of symbol, which is the linearized version of your graph, okay, of your parse, for example, in this case. So you can have a direct prediction, okay, thanks to a seg-to-seg translation model. So the great thing here is that, okay, again, there's no pipeline. There's a unified architecture for any kind of linguistic stacks. The only thing is that the output format, you know, of your model is can be changed, you know, and if you have enough data, of course, to train the seg-to-seg model. And the most important thing, I think, to my point of view, is that now you can add semantic to the labels. When you do classification, there's no semantic attached to the label. A label is just, you know, a symbol, you know, which if you have two different symbols, they correspond to two different indexes. There's nothing which link them together. When you do seg-to-seg, you know, all the symbols will be linked together thanks to the word they are encoded with. Okay, so you could really, for example, if you have a named entity from one tag set and another one from another tag set which share some words, if you are doing classification, then it's two different labels, so it's two different classes. If you do a seg-to-seg, then they will share some common representation thanks to the words they are in common. Okay? Of course, there's some caveat as well. You know, the most known one is the fact that you have hallucination. Okay, so the system can diverge and produce something which is completely out of bound, and then you have no security. Okay? You don't have the security of a formal semantic model. You just output a sequence. Okay, so this is, for example, you know, we work on that. So this is a joint work with Orange, you know, my colleagues at Orange, and so we work on how to linearize a graph which represents, you know, spoken language understanding in a kind of a dialogue context, and how we use, you know, a seg-to-seg model to produce that and see the differences we observe compared to classification. Okay, so then came prompt-based model. Up to now, you know, so you had seg-to-seg, but you needed to have a specific training data for each task because you needed to have the right input sequence and the right output sequence. In prompt-based model, as you know, you reformat any NLP task, you know, as a question, okay, for which the output sequence will be the answer. So it can be, you know, give me the next word, you know, this next word prediction models, but it can be anything. If you increase the context, then you can use that, you know, to fulfill any kind of linguistic task. So, for example, you can say, okay, give me the subject of this word, give me the object, give me in this co-reference, give me what is mentioned is this co-reference chain for this word. So you can transform any kind of linguistic task as a prompt-based task. And of course, you can do any kind of task. So in this case, you can use, of course, as well as sec-to-sec model for that. And so your input sequence is context with question, and your output is the answer. So this is even more generic than translating text into a linearized graph. This is really translating language to language. Okay, each task being a specific kind of prompt and answer. So where are we now? You know, famous quote, you know, that's to a man with a hammer, everything looks like an A. So now everything is moved toward this paradigm. So if you look at current benchmark data sets, so for example, there's one which was out in 2022, like supernatural instructions, then you have 1,600 tasks. So what are these tasks? It's anything you can imagine, but what could involve language. So for example, give me the shortest word in this sentence, blah, 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 blah. And then the output is the shortest word of a sentence. Or doing some kind of reasoning, you know, if person X is in blah, 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 and person Y, then, and then you instance that with, in the prompt with, say, X is Mary, Bob, Y is Bob. Give me the result of the inference. So you have like that, you know, you can automatically generate a lot of different tasks, and you can use that to train and to evaluate your model. How do you evaluate all of them? Because you have so many different tasks. Well, one approximate metric is okay. So that's really a generative metrics for evaluating. So you have impressive results, okay? But one thing, you know, that's been bothering, you know, some of us at the moment is that, okay, when you look at all this evaluation, do we really evaluate the capability of understanding of our models, or are we not just evaluating, you know, the objective function that we put in our machine learning model in order to learn representation? And for that, you know, what we think that at the moment we're in kind of a situation where we are a bit lost in evaluation. So this slide was made by my colleague, you know, Philippe Langlais in Montreal, and it kind of summarized a bit our state of mind at the moment when we look at all these tasks, you know, which have been every week, you know, you have a new benchmark with thousands of tasks, and when we don't know exactly what's been evaluated. Okay, so what are the issues that we think still remain in current time? So one of them is, which is not new, you know, is the biases and low complexity of the benchmark data. So I've been working quite a lot on these topics, you know, since trying to have a critical view of on the benchmark, because most of the time scientific paper, specifically in spoken language understanding, where there's very few corpora, people just use the corpora without really thinking of what they contain, you know, and then they produce analysis and results, which most of the time are not really significant of anything. So it's important to have some critical thinking when you perform evaluation. Another problem is that most of the benchmark data have cheap or free annotation. Of course, that's the reason for that. You know, we need it's good to have free annotation because we can have a lot of data. But if it can be really okay for training a model, it might not be really okay to evaluate a system. So, for example, here I work quite a lot also at Google App on summarization task. You know, and you have a very famous data set which is called ILLS. And in ILLS, you know, so you have news. And you have a summary, but in fact, it's not a summary. It's the headline. So it's the headline you have when you have
paper. And then after you have the article which follow the headline. But most of the time, the headline is not really a summary of what's going to happen. In a lot of time, you have, well, it's not the case here because this is the example they give in the paper, but we look at the data and we studied quite a lot. In a lot of cases, you have information in the summary which are never being repeated in the document. So these are okay, for training models against. No, that's great because they managed to train models. But are they really adequate corpora to evaluate models? I'm not so sure. This is another example. So this is called GEM. So GEM is a new benchmark environment for testing natural language generation task. And so all that each line is a system. Okay. And you have all the metrics which are used to evaluate the system. So you can see that you have either, so they're not reported here. You have either human annotation, or you have all this generative process metrics like rouge, bleu, BERT score, or some kind of statistics on library size, background distribution, and so on. So there are nothing which are really about the task of understanding. It's more things which are correlated to it. And again, it's good for training. It's not maybe not so good for evaluating. Other issue, for example, is the fact that we deal with multiple answers. So this is, for example, in supernatural instruction, a task. Okay, so task is you have two analogies. That relate objects to the associated rule, given in form A, B, and C. A, B relates object A to B. Your task is to bubble. So, for example, if you say that the sink is in the kitchen, where is the sofa? If you say that the microwave is in the kitchen, where is the bookshelf? And when you look at the ground truth in this corpora, for example, the answer here is parlor. Why not? But why not somewhere else? So far, not just in parlors. And the same thing with bookshelves. So again, this is a major problem for this evaluation to have only one ground truth. So I'm going to go much further. So this is also the issue of overestimating the system performance, and this is also superglue, which is also another benchmark in natural language study, where you can see that humans are just ranked 8. On the leaderboard, although the references are made by humans. There's some analysis we did also when you see that the quality of, for example, each question generation, you think that the generated questions are really, really good, but when you look at really the link between question and answer is not so good. So, okay, there's a lot of things. So I'm going to finish by just saying that, but we feel that we need to, of course, generative models are great. So the title of my talk was, we go back to classification, of course not, but we need to have better and more realistic benchmark. We need to have a classification process to go from the spectra of human evaluation to training loss. We need something in the middle which really evaluate what we're interested in. In this case, it was understanding. And for evaluation, so evaluation is the key, as I said. And so the current work we work on is how to control hallucination, how to provide explanation and to users. And so we have current project with Orange and Edis. Thank you. Thank you.
Yeah. So what do you think of using language models as evaluation functions for other general evaluators?
Yeah, I think it's why not? It's for me. It's exactly like this table. So it's for comparing system is great. Okay, no problem with that. You can compare system with that. Now the new trend also is to make the ground truth with ChatGPT. Because you have several benchmarks now where the label, the ground truth, is produced by ChatGPT, and they even claim that it's better than humans. Okay, but what I feel is that if you want to compare system, rouge, bleu, BERT score, models, evaluating models, that's fine. But at the end of the day, you will have no idea how good your system is from a linguistic point of view. Is it really solving, what you were thinking
your model was doing, when it was doing reasoning, when it was doing, understanding. And so what I feel is that at some point we have to go back to some kind of formal models, because language is not just a natural phenomena. Language is also a cultural construction. So we have rules, we have, and to me, as yesterday I was saying that, okay, when direction of research was how to integrate physical constraints into deep learning models. For me, it's the same, how to integrate, linguistic constraints, things we know about language into this model in order to better understand and control what they are doing.
It works. All right, so here's the outline. So I think we're probably tight on time, so I'll go as quickly as I can. So apologies if I don't talk too much on the details, but I'll make the slides available and you can read them afterwards, or ask me questions afterwards. All right, so I'll start with the presentation, then some recent research, focusing on a few points, and then I guess the most important part, the potential collaborations. Okay, so in terms of a personal presentation, so I'm mostly interested in machine learning and very interested in domain adaptation, incremental learning, weak supervision, computer vision, pattern recognition, and information fusion. My main areas of application, so video analytics, surveillance, effective computing, and I do some analysis of medical images. So it's not my main area. So today I'll be really focusing on the two first type of applications, and in particular, video-based applications, and I guess highlighting and hopefully highlighting the possibilities or some possibilities that we can have when we have a lot of data, but that is weakly labeled or even unlabeled. So the type of applications. So I've had a lot of work on detection tracking, and in particular that combo. So I'm very interested in the ability to join or to have a common model that does what they call detection and embedding, so that I can do detection, the same model. Something's rolling here. Anyways, having a same model that is able to detect and also track or recognize. I also work on this. So this is an old diagram, but it's very clear. So what they call a re-identification. So being able to recognize the same person or identify the same person appearing over a network of cameras. That ends up being a very challenging problem as well for many reasons. This is below. I also do a lot more work now on multimodal recognition. So being able to leverage different modalities. So here you have examples with RGB and infrared. And there are a few examples here of things we've worked on that I'll get into. I guess some of the big applications I'm working on are this first chair with one of my colleagues called, his name is Marco Pedersoli, so he's presenting tomorrow. He'll be here tomorrow to present. And that one is about designing or developing deep neural networks that can, I guess, leverage multiple sensors, low-cost sensors, and be able to do things like detect individuals, count the number of people, track them in a building. And it's not for surveillance, it's for building control. And here's some of the main type of things we'd like to do in that chair. So it's a chair with a company called Distec Controls, and it's the title here is in French, but it's about building automation and bordering on IoT. Right? So they're interested a lot in tracking people, their locations, They're interested in being able to count the number of people, detect events, mostly or primarily to control, the environment in terms of climate. Another chair that I'm involved in, well, in this case, there's Alessandro Caric and Marco Pedersoli as well that are participating in this chair. And it's about predicting the effective state of individuals in the context of e-health, and it's mostly for behavioral change intervention. But I would say that I'm generally interested in expression recognition, and mostly for the moment with face and voice. So being able to detect expressions of, for example, it could be pains. We have applications of pain. Being able to recognize those expressions based on videos. Okay, and here are some of the key things we're working on. So audio-visual fusion, rapid adaptation. This is the big one, spatial temporal localization. So that's mostly for analyzing videos and being able to help interpret videos. Okay, so what are the common threads in these research? So they involve videos, okay, and for the most part, we're dealing with situations where there are domain shifts, sometimes very dramatic domain shifts. For example, going from infrared to RGB is considered a big domain shift. Typically, we're dealing with situations where there's a lot of variability in the objects or people we're trying to recognize, or behaviors we're trying to recognize. And also we're dealing with situations where typically the state of the art in literature involves these huge models with a lot of parameters, and if you want to get state-of-the-art performance, traditionally you need a lot of labeled data. Maybe with the self-supervised learning, it's coming along and people are, getting along with less data, and also dealing with complexity. All right. So as I was saying, I'll focus mostly on video analytics, surveillance, and effective computing, e-health. And one of the key things that, one of the important things is that obviously in video, we have extra information because we have, video clips, tracklets, so we can leverage that information. And that will help us, that helps us as well, as we'll see later, be able to do domain adaptation. But some of the key ingredients in my solutions are typically weekly supervised learning, often based on video tags now, or domain adaptation. All right, so I don't think I'll go into this. This is like I like this picture, and it's a very pattern recognition view. I've had discussions with colleagues about definitions of what weak supervision is, and et cetera, et cetera. But so I won't get into that debate. That's not the point. But and I think everyone knows what we're talking about when we're talking about weak supervision. And mostly we're talking about techniques that involve active learning, for example, semi-supervised, in situations where we have a small amount of the data that's labeled and a large amount that's not. In situations where we have coarse annotations, for example, a class or tag for an image or a video, often we're talking about multiple instance learning, but some people call this weakly supervised. And I won't debate anyone on that. And then also there are situations where the annotations are noisy. So that's kind of a big picture, as I see it at least, of weak supervision. Here's an example in face recognition of a very common setting that I think everyone knows, unsupervised domain adaptation. So typically you have a source data set that is labeled, and often you pre-train your model on that, and then you want to adapt your model with a target data set that's completely unlabeled, and you're using during optimization a combination of those two information. So that's this is a nice picture that I mean, I have my own picture like this, but this is much better. I just found it. It's new, and this is an image that gives a high level view of different settings. So you could replace, for example, you know, this is a supervised case where right at the top, where there's no alignment, and then you go into different types of alignments. You could replace alignment with adaptation if you want. So I won't go over this. I think probably, as I was saying, the slides will be available if you want to look at them more closely. It's there. But there are a lot of different settings and a lot of very interesting ones, and sometimes confusing in literature. But all this to say, there are a lot of tools available, and these are some of the main, let's say, ingredients in my solutions. Right? Okay, so we're getting into the second part on recent research. So this is work that dates back a few years, but I think it's had a lot of traction. So it's the idea of, so we're going back to this doing unsupervised domain adaptation, but now in the similarity space. And we're considering the fact that we have access to videos. And you know, a lot of papers do image-based, purely image-based, which in my mind limits you a bit, because actually it's a video application. Right? People are dealing with videos. So here's an image of a system that you could use for video person re-ID, for example. And you'll notice here that you have a video clip, and there's a representation that's created. There's a representation that's created at the output for each image. And then there's aggregation, and you're matching it with aggregations of other people that were detected prior to that point. So what's nice about this is that, well, we don't have labels for the target data, but we can still infer that quite easily that the video you captured for one person is from the same person, assuming your detector works well and you can keep tracking. And so from there, you can extract something called within class information on the right side, and between class. So the within class is basically comparing images from the same tracklet clip, and then between class is between different clips. They're different people. And with that, you can put together a similarity distribution. So the big part of this work is using that information instead of the feature level information directly to do domain adaptation. So here you have, you know, here it's it limits. It's like a distance measure, of course, and the occurrence of different pairings. And what we see is you have the distribution in orange of between class, and in blue the distribution of within class pairings. So with that, we applied a very common measure called MMD and then we put together a loss where we're essentially working in the similarity space, and we use that to align our distributions. Okay, and here we have an example of a situation where we're computing the MMD loss within class, okay, on the blue parts, and also between class on the orange parts. Okay, so this is a picture of the model in training mode. And so on the left side, you have the different types of inputs. You have the model that you're trying to train. Here it's a CNN. Could be different things. And then you have the supervised part. So this is completely standard. That is, relies only on the supervised data. And at the bottom, you have the unsupervised, or the newer parts, where you're relying on the labeled data and unlabeled data. And from that, the part in green in the right corner on the bottom is really what we're proposing. So by adding that, well, I won't go into the details, but there was a good, you know, this paper dates from a few years. So at the time, performance was really nice and gave good results. So it was encouraging. There have been some since then, some parts that extended on this work where we used this type of domain adaptation in really a video-based re-ID method. And in this case, so it's a newer paper. If you look at the bottom of the slide, you'll have the papers related, and some of them are ours, of course. This one is a model, and Christian was on this work too, where we try and essentially we try and characterize the shift across different cameras, because in domain adaptation you have different cameras, and so we try and use that information. And also there's something to do with contrast loss and weighting. So I don't want to go into details, but there's an extension to that work. Also, more recently, we've been working on something that's given a lot of impact. And here again, I don't want to give a lot of details, but it boils down to just doing an end-to-end training of an embedding model with a linear classifier at the output. But here again, we're using the similarity space, and using the space allows us to wrap it all together and use a very simple linear classifier to do an end-to-end training. And the results on that are very encouraging as well. So they're very good. And okay, so this is one type of research. Of course, I've done as well stuff in multi-target domain adaptation. Here, there's an example of and the whole idea of multi-target domain adaptation is to be able to actually have multiple targets encoded into one model, right? So if you were trying to apply domain adaptation in practice, you wouldn't want to have like one model for each domain. That wouldn't make too much sense, and it would probably be a showstopper. So what people do is either they just put everything together and train one backbone. That's probably the most common thing. But with this kind of solution, you lose your discrimination power. One solution that has worked well for us, and this is probably the most basic version of it, is that we use some sort of knowledge distillation where we adapt. In training, we adapt several backbones, and then we have different schemes to distill to one model. Right? And that usually performs much better. I don't want you to look at the table. I think it's better to look here. So what we have here are very, very light CNNs that are popular in re-ID, and that could run really quickly, right? And so the red bar is us, and it stays up, whereas the blue bar is using blending. Sorry, it's not very clear, but this is blending, and this is our approach. And so what we discovered is that when we get really into using smaller models, as you would want to if you're doing person re-ID, you know, because it's an application where you have a lot of data and possibly a lot of cameras. So in this case, with these sets, our model with the knowledge distillation keeps up its performance, and a lot better than something like blending. Okay. And by the way, these are models, these OSNet things are models that are quite small and that don't really have that much capacity compared to, like, you know, a ResNet 50 or something. Here, I won't get into this, but there's a variant that we have that involves object detection. And here, because of the complexity of detectors at the time, we went with more of a progressive approach, but essentially it's based on knowledge distillation. And the diagram here is very nice. If you look at it later, you know, it presents the different ways you can do multi-target domain adaptation. And this is the distillation one that we just saw. And with that one, we were actually not able at the time to train our models. It was just too complex. The student was very frustrated. And of course, frustration drives innovation. We came up with this other model that is more based on progressive learning. So that was great. And it works well, but it's more like you're training one after the other, right? Another related topic is, doing re-identification using visible and infrared data. So in that case, you're trying to match, it could be people or objects, for example, cars, across different cameras. And the cameras can be co-located or not. If they're not co-located, it becomes a very, very complex problem because the domain shifts are quite large. So one of the solutions that's worked for us is, I guess, a solution that works for, or a solution that corresponds to this paradigm called learning underprivileged information. And so essentially what we do is we leverage some privileged information. I'll define what that is in a second. And we define intermediate domains. And the idea is, instead of doing a domain adaptation across two different things that are very different, that could ultimately negatively impact performance, the idea is to define intermediate steps. And hopefully you're bringing your source and target information closer together during training. And so, yeah, I won't get into this, but there's a paper that we're working on actually more recently than this. And so basically it corresponds to generating data or images, sorry, generating images that correspond to intermediate information in between RGB and IR. Okay. And this is the model. I don't think you want to look at the detail, but essentially in this model, you have a detector, that's a generator, okay? And that could be different things, right? You have a generator that's connected with the backbone, that's all the part ingredient. And the idea is to use the information at different layers of the backbone, and you feed that back into a generator. And the idea is to generate images based on here on RGB that start resembling the infrared domain. And so again, the idea is as training goes on, you're reducing the gap between the target and source domain. So here again, it's an idea that this one really works well. So it's not well presented here necessarily. It's hard to look at, but you have in the first row with results, you have the standard case where, let's say, your gallery's visual and your query's visual. So we're doing pairwise matching, infrared, and then a mix. You can see there's quite a degradation in that case. But using the approach that we're proposing, we add the Z, but that's the intermediate domain, and we're just adding one intermediate. We could loop back and do this whole sequence of intermediate domains. And the result that counts is the final row down here, and the results are quite a lot higher. So, okay, so it's good so far. Yeah. Okay. All right. So different type of application. So this one is more related to that chair that I described. But more related to that research chair that I was describing. So this is about it's affective computing. So it's expression recognition or emotion recognition, and it's based primarily on. So you have videos, okay, and it's based mostly on faces detected in the video and also voice that you're extracting. So there's a visual part and an audio part. So this is an image of a system that was proposed. This was in a journal recently, but it's basically the new part. So you have the video coming in, and you have one stream that is really the visual part, and you could have one or more backbones, and you do feature level fusion, and then you could do the same thing with audio. And this is a whole question of how you align it that I'm not describing, but then you have the blue part that's more like a very cheap fusion thing based on attention. And the question we had was more to do with controlling attention. So we could have stuck a visual transformer here, and I think it would have worked probably much heavier, but this is like a very bare bones thing. And what we wanted to do is be able to control situations where we don't have the voice or the face in a reliable way. So here you have two different types of solutions, two examples, and each one has two solutions. So you have, if you look at the clip of the person, so they go from neutral to, I guess, being happy somewhat. And then you have valence and arousal. And then you have, beside that, some sort of attention score produced by the model. So it's an indicator of where the model is focusing. So, for example, this is cross attention. This is joint cross attention, which is a newer model. And it gives you an indication of what modality it's focusing on as well. Oh, sorry, it's not the valence arousal, it's audio video. So it's voice and face, let's say. Okay. And this one is more revealing. So you have a lady that looks like she's singing. This is like a YouTube video of some sort. And clearly in the middle, we're losing, her face isn't really helpful anymore, right? Because she's turned the other way. And I mean, I guess both models have their virtues. Actually, both models are ours, but we can see that actually where the audio part starts turning on, becoming more important with our model. And then the facial part has less importance. So that's a very important functionality. As well, attention is very important in this kind of application because you don't want to be over focusing on, for example, this lady's face when she's looking the other way. Okay, I think we'll just skip that. Okay, well, what I want to add is that, okay, we get good results. It's a very, very challenging thing, but, and probably by now, what we're proposing is being beat by the literature even 6 months later, so, but still, we got good results with Ricola and Aquawild. Okay, another application. And this one is about object localization. So I'll start with object localization, but in a second, we go into video, or a video version of this. So it's a situation where we're trying to localize or produce this bounding box around one of the objects or the most important object in the image. During training, we only have class or image class information, right? So in this case, we know it's a car during training. But then during inference, we should be able to produce activation maps. And these activation maps allow us to put a bounding box around them, tell you where the object is. So probably a lot of you know about CAMs. It's a very well-known technique for producing activation maps. Essentially, it involves extracting class activation maps and using information from global average pooling to produce activation maps per class. And so one of the big problems with CAM methods, even the newer ones, is that in reality, because of the pooling and the different layers in the CNN. So this is a technique that's made for CNNs. So because of the pooling, essentially at the end, what you get is a very low resolution map. So these are examples of maps that you get at the end. If you look at the left side, you know, the input images are these ones, and at the end you get this really kind of blobby, low res thing, right? So what people typically do is they interpolate, and well, the interpolation brings it back to the size of the original image, but not necessarily in a good way. So in this paper on FCAM, or before doing this paper on FCAM, we tried to characterize the impact of downscaling on accuracy. So this is for the BIRDS data set. And so the accuracy clearly goes down, you know, with the downscale factor. And what we proposed is something called FCAM. So this is for full resolution, okay? And essentially we're replacing interpolation with some sort of trained decoder. So this image has both situations built into one. So you have this image of a bus at the bottom right. You're feeding it to your CNN, it's pooling, global average pooling, and you produce this low resolution CAM. You interpolate and gives you something that doesn't look too good. Okay, so that on that left side you get one chain. What we're doing is more on the right side. So based on this CAM, we get information to train a decoder, okay, or to do parametric upscaling. And then we produce, we're able to produce these kind of high resolution CAMs that are very close to the ground truth. Okay. So I guess the important part is that we're adding some sort of decoder, okay, at the end. And there's a technique for, you know, a pixel-wise cross-entropy method based on pixel samples from the low-res CAM. So I have some images. I don't know if I don't really want to go into detail right now unless somebody insists, but here you have the original image, the encoder, and you produce your label. So you assume that this is pre-trained. And then you have the decoder on the right side. And essentially you're using the low-res CAM to guide selection of pseudo labels or pixels used to train. You interpolate, and then from there you select samples that are foreground, background, and then you use that inside this term, the H term right here, that's pixel-wise cross-secting. Okay, and then after several iterations, we're able to train this decoder and get pretty good results. So here are some results that, so you have results for CAM on its own for 3 different backbones, 3 different CNNs. And then when we add FCAM on top of that, because if you remember, if you noticed that essentially you could use any CAM method here. So it's something that's built on top of anything, right? This could be any CAM method inside, and on top we add FCAM. And so we have here the regular CAM, and with FCAM on top, and there's, you know, so there's always a good improvement to the regular case. So here we have GradCam, GradCam++, and then we add on top FCAM. Oops, accuracy. So it gives better localization. I'll skip this, but trust me, the results are better. There's also a variant of this that I guess for histology. That well, if you're interested, there's a link to the paper. Now, if we get into the video part, so the objective was to be able to exploit, like if we had a video and you know, consecutive frames, would we be able to exploit spatial temporal information to do better sampling? Because one of the big problems with FCAM is if you make a mistake with your sampling, right? Let's say you sample a foreground that should be a background and vice versa. So that's a big problem. So we were wondering, okay, with video and for video applications, can we improve that? So this is what we did. Skip this. So essentially, in this case, we have actually less, probably even less annotation in the sense that all we have for our training is a video tag. So like one label for the video, and we also assume that it could be a video. So let's say we assume that we're looking at a video of a car, and maybe at some point it's occluded by a tree, you know, so it's in a sense not perfect. So we'd be feeding it a video sequence, and then we'd have our CNN plus, you know, our CAM method built on, and then we'd be localizing on each frame. So it could be pretty quick if you're looking for localization on individual frames. Well, I won't go into the state of the art, but state of the art is pretty, you know, there are a lot of problems. The methods tend to be very complex, let's say, and require a lot of optimization. So essentially, we're proposing two things. So the first thing will be something called TCAM. But in general, the methods that we're proposing are based on CAM, and CAM can be very discriminant, you know, in some ways. So compared to the video-based approaches, our method can be pretty fast and straightforward. And even compared to still images, so now we get the advantage. So you can compare it like in terms of a video method or a still image method, and there's a good advantage in each case. So, okay, so the main idea. So we're looking to leverage small variations. This is for, if you notice here, this TCAM, so temporal CAM. So we're trying to put ourselves in situations where we're leveraging very short videos, okay, or very small time frames, and we want to exploit the variations on a very small time scale in videos. We want to build it on top of FCAM, and essentially the approach will be very simple. The first one is simply aggregating CAMs. So that, what, your minute? Okay, so then we get, okay, on va accélérer. Okay, so the big lines is that, so we're adding essentially this in our model. I'll just go to the main parts. So we're adding this kind of CAM temp thing in the middle, and all it does, this is very simple, all it does is it extracts the max on pixels from different CAMs. So here you see the sequence of airplane images. They're consecutive. We present them to the backbone, and then we get a CAM for each one, and then we just kind of maximize the pixels. So that's a very simple technique. But even that, once we integrate it right here in our model, so instead of looking sampling from individual CAMs, sampling from this TCAM thing, even that gives us a big improvement that we'll see later. Here, I don't know what's going on with the image, but oh, okay, sorry about that. This is the better technique, but a bit more complex. So it's called ColoCam. And the main idea is that if you're looking at a sequence of images, for example, of horse, essentially we're using information on color, okay, and we're essentially matching pixels from different consecutive images, right, based on color. And we're using that information to do a better sampling. Okay, so I can explain it later if somebody's interested. So there's some details there, but it's very interesting. But here are the results, and we focus really on the bottom part. So you have these CAM methods, and layer CAM's quite good. I think it's 2021 or 2022. And then we have TCAM and ColoCam. And what we're seeing here is that by making these small changes, we get really quite a big improvement on localization accuracy. Okay, and I'll skip all this, but for those of you who are interested enough to look at the slides, you'll see that even the visual results are quite impressive. It gives really good localization. And it doesn't really improve the complexity that much compared to something like FCAN. Okay. Here's a characterization of the optimal number of frames. Okay, and I'll go straight away, if you permit, to potential areas of collaboration. So one of the objectives of us coming here is to, meet French researchers and students. And so I put together a list of areas that could be great for collaboration. I break them down this way. The first main area is being able to rapidly adapt deep learning models. So to be able to deploy them. There are different things in emotion recognition that I'll describe in the next slides. Weakly supervised methods, and in particular, this could be a good area. Weakly supervised spatial and temporal localization for interpretation. And that could be really useful in a lot of applications, including emotion recognition. And also an area that could be very interesting is this joint detection embedding. So being able to work on models that have one, backbone that is able to do detection, produce detections, but also feature representations for each box and do it in a good way. Okay, so in terms of rapid adaptation, well, I'm interested in all these things. So, and I see a potential positive side to any one of these things. So weakly supervised domain adaptation, domain generalization, multi-source, multi-target, like we just saw, cross-modality adaptation. Moving on, also, this is very important for me right now, being able to work on source-free, and I think Jose is going to talk about test time. That's very important. So being able to take a model where you don't have the source data, and for privacy reasons or efficiency, you want to be able to adapt it very quickly on your target data. Continual domain adaptation. And then there's this thing called gradual domain adaptations. That brings us back to that paper where I was talking about earlier, where we're trying to reduce the gap between source and target. So these are techniques that I guess a lot of the papers are very new. And the objective is not to try and do the domain adaptation in one shot. It's being able to define a path from source to target through a series of intermediate domains that will give you a better outcome. So these would be great topics. And let's see. There's also working on distillation. So in the emotion recognition problem, we're working quite a bit now on something called privileged knowledge distillation. And the idea is to, so here we have a situation where, for example, it could be audio, video, and biosensors and text that you have during training, and you train models with them, and maybe several backbones, and then you're able to distill them to a single source that would be very light, and maybe it only takes in face and it gives you similar performance. So it's there's also getting back to test time adaptation. You know, being able to really quickly adapt models, preferably like in emotion recognition on these short neutral videos. And that raises all sorts of problems because the neutral video doesn't have all the expressive elements in it. So, this is actually very important because typically if they deploy something, there's going to be a lot of variability depending on the person. And you want to be able to, if you have any information, try and integrate them and adapt your model. And finally, spatial temporal localization. So being able to identify, for example, in emotion recognition, the parts of the face or the parts of the voice, and where these emotions happen or expressions. And those play a big role in analysis of systems and interpretation of a person's emotion. I think that's it. I also do stuff on image processing, but we won't go there. That's it. And I also want to say that while I do have some collaborators, I have obviously a lot of great colleagues. Two of them are here that participated And I have also companies that, so more recently I'm working with Ubisoft, and but normally I have people at work companies that work with me in video, e-health, mostly centers. And now the more recent thing is gaming. And so this is tied to the chair, building automation. And also, strangely enough, I don't know anything about 5G, but somehow I do stuff with Ericsson. So
Thank you.
So at the back, think of being the last one. Everybody's leaving out.
No. It's a real pleasure to have Jose Dos. He's associate professor at ILLS, and he's also associated to Libya. It's Eric ILLS, and he's very much working in image processing at large, machine learning, computer vision, and in particular, so learning with limited supervision, limited data. So,
yeah, thanks, Pablo. So yeah, I'm from ETS, working on these fields that Pablo also said. Today I'm going to talk about something which is very close to what Christiana was showing yesterday. So actually, I have to say Christiana was one of my postdoc advisors. I have to say that because you're going to see a lot of overlapping, that's why. I'm going to tackle the same problem. So I like what he said about how we can do more with less, but I'm going to tackle that from a different perspective, especially from the methodology. So, nowadays we have a lot of data. We can have many nice models. We can have, transformers, any kind of convolutional neural network. If we have enough data, that we can get actually very good performance. Okay, I'm gonna put on this side. We can have very good performance, for almost any single task. Okay, that's right. The problem is that in the medical field, just getting all this data is very time consuming. So imagine that you're a doctor, you have to sit there, you have to draw this manually. You might spend days just doing that, for a single brain. That's very time consuming, and that's very costly. Okay, so we cannot afford to have like thousands of images, labeled for training a segmentation network. The problem is not only that, is that I think I forgot to put the example. It also that requires expertise of the people there, right? I can ask you, for example, where is the car here? I think most of you will see where the car is here. But if I ask you what is here, the white matter. Okay, maybe not everybody knows what the white matter is here. So it requires some sort of expertise that not everybody has. Okay, so that makes the task more difficult. So what we can do to actually evade this problem, what we can do to try to train segmentation networks with a less amount of label data. Christian was showing yesterday we can actually show, or we can use semi-supervised learning. We can use some sort of unsupervised domain adaptation depending on the domain sheet. But we're going to focus today, it's in these two different topics. One is fusion learning, okay? And one is weakly supervised learning, okay? So we start with the first one. What weakly supervised learning means. So let's say we can have, for example, images, and instead of giving the full annotation, so we are going to give all the information for all the pixels in the image. We can give, for example, what we call image tags. So we can say here, you have a person, there is a bike, or here, there is a tumor. Okay, I'm not going to tell you where the tumor is, but I'm going to tell you somehow in the image there is a tumor. So there is some sort of uncertainty in this information I'm going to give you. We can also give bounding boxes. So with that, you can reduce, I would say, the search space on the image, but still there is no clear definition where the tumor boundaries are. Okay. We might give also some scribbles. So let's say instead of sitting there with the mouse trying to delineate this properly, you can just draw some scribbles, or you can use some points, right? So all this is some sort of different informations we can give to the model, okay, in a weakly supervised manner. So we introduce some sort of uncertainty, okay, in the way we are guiding the network, okay, to learn where the object can be. If we think about the medical domain, it's a domain, application domain we are working a lot. We may have, for example, this information. Let's say we know from the textbook knowledge, from the practice, that typically, if there is no pathology, the health of the population typically lies between two different bounds. So everybody, we can go to the scan, we can get the heart volume, and ideally should be lies between these two bounds. Okay, so we can use this information during the training as a prior to guide the segmentation network. But for example, we can have this. Let's say you have a cohort with the segmentation of the liver. Then you may have a different cohort, for the segmentation of the spleen. So you may have different set of data with different annotations, all right? So what you can do, you can actually leverage, which is the relation between both, or between all these different data. So for example, if you have, that the size of the liver is 1, maybe statistically, the size of the spleen is 1.2, okay? And this information can be used also during training, okay? So the key point of my main thing for this talk is how we can actually go from these weak annotations to pixel-wise segmentation, okay? How we can leverage all this information that we have in a very coarse manner to produce precise pixel-wise classification. That's going to be one of the parts of this talk. So there are a few techniques. For example, if you recall the talk from Todd yesterday, she was talking about interpretability, and it was showing also this today with these class activation maps. One trend is that you can use these class activation maps as an initial point to use as pseudo labels. So you can just do a threshold, you can put this in the class activation map, and you can use the result for training segmentation network. Okay, but these are some limitations. What we are doing is we are working from a constraint optimization perspective. Okay, so what does actually mean? Okay, it's a fancy word, but what does that actually mean in practice? Let's say you are going to optimize a task, okay, a task A, subject to different constraints, okay, to different restrictions. So let's try to illustrate what that means. Okay, let's see. I want to go from this point to this point. So which path I can take? You can answer if you want. I mean, you know the answer. So, so for example, I can get this path. I can get this path, right? But can I get this path also? I can. Can I get this one? So which is the best route? Typically, people now say, from here to here. Yeah. So exactly. So the real question is, which is the best route based, okay, such that is the shortest one. And that's going to be my constraint. So I want to optimize going from point A to point B in such a way that I'm going to satisfy a given constraint. But if I now, okay, if you have kids and your kids are my kids, they're going to be okay with this. I'm hungry, I want to eat something. So in this case, or maybe my constraint is going to be, which is the best route, knowing that I want to go to an atom to buy some food, and then go to point B. So in this case, it's going to be the path or the route green. So just to show that in this case, we want to optimize the same problem, but depending on the constraint we have, we may have different solutions. That's the same for, for example, segmentation networks. If we go more in the formal definition and formal details, we can formalize this as follows. So we have, for example, let's say we know we want to do a segmentation task. We want to segment again the heart, and we know that, we might know some size a priori. So what we want to do is we want to minimize the cross entropy for those pixels for which we know the labels. So imagine you give some squares. So for those pixels, we know the labels that correspond in such a way that the sum of the segmentation, if you go through the softmax for that class, is going to be equal to my prior, to the size I know a priori. Okay, and this information could be very, very, very powerful. So I'm going to show you later. So that's the way we can formulate this problem. If you think about, let's say, classical optimization perspective, this can be solved with very popular method, like, for example, Lagrange. Okay, the thing is that if you apply this for neural networks, you might be doing an interplay between being gradient descent here to find the parameters of the network and gradient ascent for the Lagrange. Okay, and we found in practice, if you replace this by simple penalties, actually that works. Okay, it's working. I would say from a optimization perspective, this is not ideal. This has many limitations compared to standard prior problems. But in practice, it's working very well, okay? So basically, you go from this problem, where you basically make that the sum of the softmax is equal to a value, to a given prior, and you want to convert this to a penalty like that, okay? And that means each time you do a segmentation, okay? You get the sum of the softmax. If this is different from your a priori, you are going to get some penalty. And this penalty is controlled by this habit parameter. So it's going to balance the importance is this penalty, okay? So that's for the case of the size. Okay, let's say now you have any kind of function, okay, function g that depends, okay, take as input the softmax parameter, or softmax probabilities, and you want that this function is going to be equal to your constraint, okay? So you can define formally this parameter like this. So you replace the function you want to use here. I will show you later. We can show many, I would say, more complex functions than just the size, but the function you define as your prior, you can put it here, and then you define your penalty like that. And you train the model, okay, based on this standard, for example, the cross-entropy function, plus a regularizer that is going to help on the segmentation process. And then this can be modeled with different things. You can put a linear penalty, which is working typically it's working fine. You can use quadratic penalties, any kind of polynomial penalty, or you can even use a KI. Yeah, I mean, with all these tools, you can actually enforce this constraint in training. The problem is that when you think about the size, for example, if you want to impose a quality constraint, it means that you need to know which is the exact size. Okay, and your error, mistake you are going to make in the prediction of the prior could be penalized or could penalize you during the segmentation process. So what we can use instead of doing equality constraint, we can relax that towards some sort of inequality constraints that gives you more flexibility. So in this case, the idea is that, let's say, you know that the population typically is, you segment the hard typically is between these two bounds. So you have a minimum bound, or like a lower bound, and an upper bound. And the idea is that each time you get a segmentation result that is out of the bounds, you are going to further penalize the network in such a way that it's going through your bounds. It's going through the priori you are imposing during training. Okay, that's the illustration, okay? The way it works is that, let's say you think about the hard segmentation, okay? I think Christian was showing something about this yesterday. So you have the endocardium, epicardium, and here you have the right ventricle. So here what you know is that you have an image tag. So you know for each slide, here there is no cavity, okay, or here is cavity. So what you can do is, hey, if I don't have any cavity, if I don't have any target on the object of interest, why should I get any segmentation result? So I'm going to impose a constraint in that case that tells me that if there is no object of interest, the sum of the softmax should be 0. Why I want to have like a 1 value or something like that? So in that case, everything is going to be to 0. But if I have some, let's say, targeted vectors in the image, I can impose the sense information. So I can say, do whatever you want to do with the segmentation result. What I want is that the sum of the softmax, the size, is between these two bounds. Okay. So the way we can formalize that is very similar. The only thing that now we have two different constraints. So we can split this into two different terms. Okay, and that's going to give you something like this. So you have still the cross entropy. So it's a supervised loss on those pixels that we know the labels. And then for the constraint is something so simple as that. So you have a quadratic penalty. So that means if the volume, the sum of the softmax, is smaller than your upper bound, you impose this penalty. So it's okay. I'm not happy with this. I'm not satisfied. Push to have something that satisfies the constraint. If the volume is higher, is larger than my upper bound, you impose this constraint. Okay? And if it's in between the bounds, so I'm happy. If I'm happy, why should I change? In that case, I don't do anything. I let that, letting go, and I just leave only this. I let this term to control the training. So I have these two terms. If you think like an intuition, because something I show to many students in my classes, okay, typically they think they understand this with this kind of two figures. So you have here your bounds, okay? In this case, the constraint is satisfied because it lies between the two different bounds. So you do nothing. If the constraint is violated, you are here, you push. The gradient is pushing you towards here. So in the case you have a linear constraint, it's pushing always in the same with the same weight. Okay, if you have like a quadratic constraint, the farther you are, the more it's pushing. Okay, so that's the intuition of this work that we did like 4 years ago almost. What I want to show, forget about all these numbers. The only thing I want to show you here today is that this is a typical example of full supervision. So in this case, you say all these pixels belong to the background, all these pixels belong to the foreground. So you take all this, it's fully supervised setting, you train the network, and you get this value. Okay, whatever, a given value, okay? Now, if you give only the information for those pixels in green, okay, in some cases you might have very few, like 2, 3, 4 pixels, and you include this size constraint, you include this information, this a priori information about the size, you can get something which is very close to full supervision, okay? So it's actually working, okay? Of course, you will say, yeah, Jose, it's fine, but it's a very simple object, okay? It's right, it's okay, but we are doing research, so it's a first step towards, trying to reach the gap to full supervision and weekly supervision. Okay. this idea can be extended to different problems, okay? So the first one was the case for weakly supervised segmentation. Christian talked a little bit about that yesterday. What happens when you have a domain shift, right? So what happens when you, for example, train your network, for example, in the hospital here in Paris, is working very nice, and then we say, okay, Jose, we are collaborating. Say, Maria, we start to work together, and she said, okay, we have very good model. It's working here in my data, test it in Montreal. Okay, I get this model, I bring it to Montreal, it's not gonna work. Okay, there is a domain shift, it's not gonna work, so distribution changes. And then what we can do, we can say, okay, I can talk to my collaborators, okay, please spend 2 years doing the annotations again, because the model we did in Paris doesn't work here, okay, and this doesn't work. So what we can do is, we can actually try to adapt this model in an unsupervised way. That means we use the data that we use to train the model in Paris, for example, and by using only those images we want to segment in Montreal, we can adapt the model. So we don't need any label for the target domain. Okay, it's something also similar to what Eric was shown before, but different application domain. So what we can do here, okay, and the next thing about all this is that I will do a connection at the end of the talk with all this. So the thing is that at the first step, we can use a standard segmentation loss for training your model. So you can use cross entropy, you can use DATAIA, you can use whatever, okay, I don't care. So you can train your model based on your source data, right here, okay? The second step, what we can do is, typically in a supervised domain adaptation, when you adapt between different domains, you need to use all the data, right? The data from the source and from the target. Here, when we talk about source frame, let's say for some, I don't know, privacy issues, you know, people from Paris, maybe they don't want to share data, okay? In that case, we need to update the model only using data from Montreal, and that's even more challenging. So what we can do here, okay, we can have like during the adaptation, we can have like an entropy term, okay, that is gonna minimize the entropy. That means it's gonna force the predictions in the target domain to be confident. So you think about the prediction of the label space, the prediction space, you're gonna try to push samples far away from the decision boundary. Okay, so in that you can actually make like a better decision. And then we have a second term that is going to try to impose this constraint. Okay, before we use a penalty term, now we can use a clear. So we are going to have an a priori, which is in this case is predicted by an auxiliary network. So we train a network to predict the size, which is because it's simple to predict the size and to actually predict the boundaries. So we are going to use a network to predict the size for that given image. And with this information, we are going to put that, okay, this is the sum of the softmax I showed you before. I'm going to say, hey, do whatever you want to do, pushing all these guys far from the decision boundary, but I want that the distributions are very similar, okay? And with that, actually, is actually giving very good results. I'm not very fan of the tables, so if you want to look at the results, you can check out the papers. I prefer more to give insights about all this. But we can do way more than that, okay? There was lesson 17 when we started to work on that. I have to say that many works, I mean, we're not the only ones doing that. We have seen more works trying to, especially impose some sort of size awareness. That's cool. I mean, it's working pretty much, okay? But we can do way more than that. I mean, we can, for example, use shapes. We can use more information for constraining these segmentation networks. For example, we can use these kind of shape descriptors. We can use the shape moments. We can use some central moments. So you take that. We can actually, for example, use a centroid. Let's say you want to segment some tubular structure, like a spinal cord or the vertebra, something like that. You know that from the center, typically the distribution around the boundaries should follow some, some pattern. So you can use this information to constrain your network. You can use also the length. Let's say, for example, you want to segment, for example, ultrasound images. Right, you have very noisy, very pickle. You write in the images, so it's going to give you very crispy segmentation results. So you can actually try to use that, okay, to ensure that you can have something smoother. Right, so this information can be used for that. Okay, so that's for weekly supervised. There are many more things we can do with that, but I wanted to stop just to give you a small insight what I'm doing in weekly. So what we are doing in weekly supervised segmentation. Now we have also a very interesting topic, which is few shot. Okay. There will be many definitions for few shot. Okay, it's not meta learning. Meta learning is a way to solve the few shot problems. I would say, from my perspective, few shot is an extreme case on semi-supervised segmentation, or semi-supervised learning, where you don't have unlabeled data first, and the second thing, you have very, very few labeled data. So in some cases, you can have only 1 or 5 samples to adapt for the new class. Okay, so the idea is that you somehow train on the base classes. So you may have like ImageNet, you can have like a large label data, okay, in the base classes. And the idea is that you train the network, following some criteria, following some processing. And then during inference, you want to do something like this. Hey, I'm going to give you 5 or X label images. I'm going to give you only 1 label image for the class of interest. And I want that you are able to detect this. Something like kids do, right? I mean, kids, you can just show them 1 picture. And with that picture, they can actually generalize for many more, right? You can show an image of a dog, and they can recognize almost any kind of dog, right? Neural networks typically cannot. They need to see all the different faces, or different profiles, or the size of the colors. So the idea is that we can infer this kind of way of working during training. So again, you train the best classes, and with only few samples for the target class, you will adapt the network to be able to classify those. Okay. The thing is that, you know, when we started, you know, in this domain, there are always hypes. Okay. Sometimes the hypes are good. Sometimes they are not good. I mean, sometimes there is hype because something is very good. I think this hype wasn't very good. Okay, personally, there are many opinions on that. So I think most of you will know meta learning. Okay. So meta learning is a way to try to solve the future problem. So the idea is that you create synthetic episodic training. So you create synthetic episodes. That means the same structure you are going to see during testing, you need to give during training. For example, if you are going to use 5 shots to adapt for a new task, you need to create tasks of 5 level samples during training. Okay, and that changes. The problem is that when you are doing that, you actually the model actually overfits to that task. Okay, for example, there's not only that we solved that, there are many papers that they were actually observing these findings. So if you have like a domain shift, or even more than that, let's say you train a meta learning based method like mammal, reptile, you know, these famous meta learning methods in 1-shot setting. That means you are going to show only 1 image, okay, only 1 label image to classify a new class. If you test it, you say, now, okay, I was very lucky. I got now 5 images for doing testing, and you give 5 images, it doesn't scale, it doesn't work. That's something which is, from my point of view, is something, it's actually limitation. Why, if you have more data, you cannot actually use that during testing, okay? Also, there is some domain shift, these methods do not work, okay? So there was like a wave of new methods coming, say, okay, why don't we get a step back, okay? We rethink the problem, and we try to propose or to come up with something more simple. Actually, there were many works showing that if you remove all this meta learning thing, you know, whatever, you can use a basic training, you know, based on cross entropy on all the data set. And with simple transactive inference, for example, you can actually get very good results. And we're going to show you, for example, how you can do this. So the first one we're doing this, it's called TIM, okay? It's transactive information maximization. So the first step, you can just train the model in the standard way, right? You get all the image, the base data set, you train the model with standard cross entropy. Now the point is that what happens when you do the inference? So the adaptation, you can minimize this term. So again, think that you get n samples, okay? Few samples are labeled, and you want to segment what we call query sample or test samples. So the idea is that for the supersets, for those samples that contain labels, you want to minimize the standard, right? That's the way we use classification losses for doing, you know, for training networks. And then in the second step, okay, in the second term, we use all these things here, okay? What this actually means. So on those samples that we want to test, we don't have any labels, okay, we call that. So we want to test on those samples. We minimize, okay, the channel entropy. So we are trying to make, again, all points very far from the decision boundary. The problem is that if you only minimize those, or you only minimize this term, you can actually get something like that, which is like a nice solution, right? All the points are pushed towards the same class. You still minimize the entropy, right? So you are happy with this term, but you are not giving any, let's say, reasonable solution. Like this is the classifier, all goes in this way, okay? But this is not the case. This is not what you want. So this is where the second term is coming to the rescue, right? So this term, you maximize the marginal entropy, which is equivalent to pushing towards uniform solutions. And by doing that, actually, so you minimize that to push all that away from the decision boundaries, And with this term, you maximize the entropy. That means you are trying to get the distribution of different classes uniformly, okay, on the distribution space. So here you have what could be maximizing the entropy. So you see that more or less all the same number of samples are lying on the different classes. Okay, with that, again, I'm showing this table just to show you one thing. All these in white are all these meta-learning based methods. Okay, and in green, you have methods that are very simple. They train on the standard cross entropy. They adapt very quickly with very simple solutions with adaptation. And actually, you see that the performance gap is something like almost 20% compared to all these meta-learning methods. So again, my message here is that if you want to use meta-learning, that's fine. I mean, of course, you are free to do whatever you want to do, but there is evidence that points that this is not the best solution. Okay, and there are many observations why it's not the best thing. Actually, doing something very simple, it works. More than that, the thing is that if you use some solution like this one, you can get any model trained, with any different or any kind of different strategy. You can adapt it very quickly. So it's model agnostic. But all the other methods, you need to use the same architecture, sometimes very convoluted, complex models to actually use those methods during the inference. So now you can say, I mean, if you are thinking that, you might be saying, okay, Jose, that's really cool. Again, that's very nice results. But for doing that, okay, you need to have many samples at the same time. So if you want to impose a distribution like this, you cannot do this with only one sample, right? I mean, you need at least n samples, n being the number of classes, right? So this might not be realistic for the case of classification, because maybe you want to do you want to classify only one image. In that case, you cannot impose any. Ideally, you cannot impose any distribution on that. There are tricks for doing that, but basically you cannot do anything like that. But the good news is that in segmentation, you actually can. And because you have one image, and that image contains many pixels. And segmentation is a pixel-wise classification task, right? So you can actually impose distribution on the whole image, and that's natural. It's something which doesn't require multiple images to do that. That's one thing, okay? But the problem is that we can have almost very similar. Actually, we made an kind of extension or new work based on this TIM method. The thing is that we have similar terms. So we have here the cross entropy for the support images. So again, we have the image with the corresponding label that you don't see here, but this is the card here. So it's the information you give to the model. You say, okay, now I want to segment a card based on this label. So you minimize the cross entropy on this guy. You still minimize the entropy. That's for the image you want to segment. So you don't know anything about this guy before the inference, right? So you only know that a card looks like this. So now you minimize the entropy for those guys, okay? And now the difference is that in segmentation, you cannot impose a uniform distribution. It doesn't make sense. But you cannot say, hey, half of my image is card, half of my image is the background. It doesn't make any sense. So what we can do, actually, we can compute a kind of initial prior, okay, which is based on initial prediction for the network, to say, whatever you give me, I want this follows this specific prior, okay? And this we are doing that during inference. So we do the inference, we minimize the entropy, we maximize this term, okay? And when we are doing that, we update the parameters for redoing again the inference. So we do this multiple times during inference, and the model can adapt very quickly for the task. Okay, so these are key to impose these proportions. So that's more or less, some of my work, or the work we're doing in our lab, okay, with some. So the great colleagues I have there. What I want to show you, I don't know if I should have started with this, but I wanted to finish with that, is that all these works can be unified in the same view. So if you start from an information perspective, you can see that all these works, feeling that, I mean, there are small differences, small tweaks there, but all of them can be unified from this multi-information perspective. So when you think of the mutual information, you have here the entropy for the level backgrounds. Here you have the posteriors. And then you have all this. Okay, so when you maximize the entropy, this can be some sort of equivalent to a constant which depends on the number of classes. So a KL between your marginal, right? And a prior. Okay, this prior could be uniform. So if it's uniform, we have this work. You can now say, I don't want the uniform anymore. I can compute this prior based on something, an auxiliary network, on the initial predictions, on a given value. So you can replace this. These are the works I was showing. And more than that, you can actually relax this assumption, the KL term, to impose this constraint, and you can use some inequality constraints, L1 penalty, L2 penalty, etc. And then you have few works that also fit in this term. So actually, at the end of the day, from this tool, okay, we can actually leverage out of information to make a really nice works. And there are more than that. So this is what I showed today. So we have supervised segmentation, featured learning, and supervised domain adaptation. But we have been using, again, different versions of this mutant information, for example, for generalized featured segmentation. So in this case, what means is that you want to adapt in segmentation for a new class with very few samples, maybe 1 to 5 samples. But this tells you that you don't want to forget what you learned. Right? You want to go to new classes. I would say I want to segment a car that I don't know, it's another class for me, but I don't want to forget what I learned in the past. Okay, because so far until now, the fusion segmentation methods, they were very good to adapt. They were very good to forget. So we want to avoid that. So you can use an Infomax principle. You know, we have more things, but we can start from this principle to actually adapt to a new task without forgetting what we learned in the past. We have been using that also with for mixed supervised segmentation, something what actually is a work that I was doing with Christian that he was showing yesterday. So in the case of having unsupervised, semi-supervised data sets, so you have few labeled data, a lot of unlabeled data, you can have few labeled data, and then you can have a lot of weakly supervised data. Okay, so when you have this situation, you have like mixed supervision, you can actually leverage some sort of mutual information in there. And you can do also generalized class discovery. So it means you have like a data set, okay, with labels. So you know, let's say you have class 1, 2, 3, 4, 5 with labels. And now I'm going to give you a lot of data which is unlabeled, that contains classes 1, 2, 3, 4, 5, but also classes 6, 7, 8, 9, 10, or maybe 6, 7, 8, 9. Okay, so that means you are going to have new classes that you never saw before, and you don't even know they exist. Okay, so again, you can start from this principle to derive a nice formulation you can actually not solve, but you can actually progress on this field. Okay. And again, this is supposed to be, some talk for collaboration. Unfortunately, I know most of the people here. So anyway, so I do more works more than this weekly supervised few shots. So I'm working also, I wouldn't say a lot, but a few works in unsupervised vision segmentation. So for example, let's say you want to segment anything that is abnormal on the brain. Okay. So having to do this label, for out of variability, out of things that maybe can come in the future and you never know. Maybe it's better to address this from let's say, or what is abnormal, I'm going to identify. Okay, so we actually works on unsupervised anomaly segmentation. We have also in calibration. I think Tal was working about that yesterday. So it's very important to have a very powerful model that gives you, for example, 99% of accuracy. But I think more important is that when it fails, it knows it fails. Now, when it tells you, okay, this is a card. This is not a card. This is a computer. So if you fail, it's fine. But just tell it. I don't know. Okay. And the problem is that current methods that they are using, for example, percent entropy, dice in the case of segmentation, they are very bad for this. So that's one interesting topic I'm working on the last 2-3 years. I'm also working actually this with Christian also in data harmonization. So same problem. We have data from one data center. We have data from a different center. There is a lot of domain shift. Okay, how we can adapt these models or these, from different centers. So why instead of using this unsupervised domain adaptation, whatever, why we cannot harmonize data? So why we cannot try to make the data uniform, very uniform? So we have started this topic in the last months with a very nice, very good student, and we have already succeeded to polish something on this. And I think it's a trending topic nowadays. I'm also working on foundation models. So how we can leverage a lot of information, not only from the visual domain, but also from language vision model, language vision domains. So the idea is that you have a lot of data, which is the case. We have, for example, especially in the medical field, we have many open challenges. That, for example, one challenge, you may have 100 images for liver segmentation. A second one, you might have like 40 images for abdominal data. You have liver, spleen, kidney, etc. So you may have a lot of variability on that. why not we can put all this together and try to make something better, right? This is kind of sort of, it's not ChatGPT, but it's something that the spirit I would say is the same. We have all this data, we put it together, and we try to make something which is more robust. So it's something that we'll see if it goes through Mikai, because so far we were very lucky with this one. But anyway, the idea is that we have this foundation model, so we have different centers, different data with different labels. We can somehow mix all this together to create a foundation model. And then we try to adapt this in a very, very quick way. So here the questions, I think Maria was showing something about that. I think Nicolas shows something in the other way around. So the question here is that, well, there are many questions. One question is what we should adapt. We adapt the input. So we're doing prompt learning as Maria is doing. We go to the output and we try to adapt, for example, the last layer of the classifier, or we try to put something on top of that to be able to adapt also quickly. So I think it's an open question yet, and I don't have the answer. I have my intuition. I know where I want to go, but I don't think it's a good way. Time will tell. But this is something we are exploring now. And this is something that it's ongoing work, which this is more a language vision model. So let's say, I think maybe most of you know CLIP. So CLIP basically you have this language image model. So this is trained with a lot of pairs of image and data. So you have an image and you say this is an image of a car. This is a picture of a person. This is a dog. So you have these text image pairs, and you train this in a contrastive way, such that the feature representation for both cases, text and image, they're very close in the feature space. Okay. So what we observe is that, let's say when you go through the medical domain, again, I feel that for us, for the medical domain, we have specificities that make that we cannot use directly what we have in the computer vision side and apply this directly to the medical domain. We need to somehow, adapt all these tools to our needs. Okay. And one of the things is that we thought, why not, instead of trying to use this categorical data, for example, you use, I don't know, cataracta or, you use glaucoma. So instead of using the label you have for the image, you don't use any kind of domain expertise. You use a description of what that means. So for example, instead of saying, okay, this tumor, you can say, okay, I see an edema which is going through there. I see infiltration. So you use this kind of domain knowledge to train your language vision foundation model. And I don't want to give any hints about that because it's still ongoing work. And actually, one nice thing is that if you get clean model, so here you have the diseases. Here you have some kind of, I would say, findings from those diseases. There is not much correlation sometimes. So even you see here, this correlated with this, but there's no disease which correlates with that. So if you include this domain knowledge, you can actually see that all of these indicators actually correlate with some of the disease. And we asked our retina experts, and they say that actually this, or ophthalmologists, and they said actually this is true. And there's correlation to, for example, severe deer, okay, for example, with Venus bleeding. So that I think is an interesting finding. So the take-home message is that, myself, for example, Christian, even Eric in a different domain, we are working a lot in this, lack of label data. I think it's a crime because, we have a lot of data, we can train very powerful models, but at the same time, it's a very good opportunity for us. Right? What can we do, as Christian said, to do more with less? I think I like this speech. So there are many interesting challenges that we can use in research. I think that despite, we are afraid, ChatGPT, where we are going to segment anything. I think at some point we are afraid of that, but I think we still have, time to enjoy doing what we are doing nowadays. Again, for us, for people working in the medical domain, I think this prior domain knowledge, I think is a mind gold. I think we can use all of that, to leverage all the discrimination performance, to leverage all these models in the medical domain, again, because, identifying cars is not the same as identifying tumors, right? So I think all this knowledge that we can get from the medical domain can be very useful for us in this field. If we talk about the constraint, size constraint, a lot that I showed you before, there are still a few constraints that have been explored in the past, okay? If you think, for example, we have the size, we have all these shapes. I think we didn't talk about that. He has also a few works trying to enforce different discrete perspectives. Something like, let's say you have an image, you have a hole, right? Typically, you shouldn't have a hole in the heart. You are alive. You shouldn't have any hole there. So you have some words to try to say, okay, you are being wrong in that way. Don't do that. Okay. So there are many constraints and interesting things to try to do in this topic. And of course, there's room for improvement in any of these domains. A few shot, unsupervised. I don't think we are close to solve any of these tasks, especially if you want to transfer all this to the clinical research or clinical domain. Of course, I recall it was funny because one company contacted me for my work in unsupervised lesion segmentation. I think we got something like 60%, 65% of that, which was really state of the art, compared to the VAE methods of that. And they told me, okay, I like that, but we expect to have 100% accuracy. Okay, no way we can achieve that. So it's fine because, there are still many opportunities. As I showed you before, this goes beyond weekly supervised or semi-supervised. There are many, many different topics. From the talks I have seen so far, I think there's a lot of synergy between many researchers, and I think we should leverage all these opportunities. So many thanks to all my collaborators for these works. I mean, I've been working with Eric in the past, Marco also for these specific works. It's actually with Ismail and Christian, they were my postdoc advisors. That's why we think we're still friends because of that. Pablo also, we have been working out in the past, and all these great PhD and postdoc students. And I was expecting to find more students here. So I made this with DALI. So I wanted to say, this is the prompt test that I engaged. So an image with the text I'm firing with a realistic beer holding a beer, and this is what I got. So that's why we are still far from, something which can be usable really, special decision-making systems. So that's all for my side. Thanks for staying still here. I think it's great. Sorry, taking it.
Okay, good morning, everybody. It's a great pleasure to introduce Marco Pelerosli. He's associate professor to the École d'Ingénierie Supérieure, ETS. He has been working for a while on problems related to optimization in machine learning, also in computer vision at large. So he's associated with Lydia, with the computer vision laboratory at ETS, and with ILLS. And Marcos, a real pleasure to have you here. Thank you for coming, and please go ahead.
So thank you everyone for being here. I'm very happy to present today about this. So I will start directly with a brief introduction about myself and my research. So when I talk about my research, I talk about three different concepts. One is data exploration, one is efficient data, and efficient learning. Efficient data means trying to exploit better the training data for learning. For example, using data augmentation or techniques to fully exploit the data. Efficient learning means instead trying to reduce the computational cost of learning. There are many techniques with neural networks, for instance, pruning neural networks or conditional computation, many different techniques. And these two are often used for what I call data exploration, that is, again, meaningful ways to explore data, because sometimes data is, for instance, very large. Think about, I work a lot on vision, that's why I put here this big eye, computer vision. And imagine that we have a long video and it will be difficult to really analyze every frame of this video. So what we can do is try to learn which part of the video is interesting for the task that I want to accomplish. So this is not only learning to accomplish a certain task, but also learn how to explore, how to analyze only the meaningful part of our data. About myself, I'm professor at ETS since 2017. I'm co-chairing with Eric Ranger, my colleague, an industrial chair in building automation with deep learning. I'm, as Pablo said, a member of LIDIA and also the International Lab on Learning Systems. I work also on effective computing, and I have collaboration with several companies in Montreal and also other countries. But now I will start with my talk, and it's about learning and optimization. I have to say I'm not an expert in optimization, but today I want to talk about bi-level optimization and how it's used in several problems. But I will start with a common equation that is used for learning. So we have a loss L, and this loss depends on a model that we call F. This model receives data X, training samples, and this model has parameters W. And what we want to do is to minimize a loss L. And to minimize this loss, we know the ground truth, we know the labels Y. And so we want to find the parameters W that minimize this loss. And this is a standard learning. But this is not really what we want for learning, because if we really optimize this, what we are doing is overfitting on our training data. So what we really want to do is we need to add something. So some model selection, for instance, in the sense that when we define a model F, this model has some hyperparameters theta. For instance, if we talk about neural networks, how many layers of a neural network, how many neurons per neural network. So in this case, our optimization is not anymore a simple minimization, but is a double minimization, in the sense we have the first equation as before, where we find W star that minimizes our loss. But we have a second minimization that is on a validation data. So we need validation data, and on this validation data, we find the hyperparameters theta that will minimize our loss on the validation data. And with that, we can find the hyperparameters that are optimal for this model. So in this sense, we are not only minimizing a loss function, but we try to generalize, because we try to find model parameters that are optimal on new data. Same thing also with the regularization. We want to add some regularization parameterized with omega. And also in this case, we want to find the parameters of this regularization such that will minimize our objective, our loss on validation data, so on data that we haven't seen. And in this case, it's slightly different than before, because our hyperparameters do not appear on the first equation. But we will see a bit more about this later. And finally, we can also think about this kind of problems for latent variable estimation. Imagine that we have again our bottom equation where we want to minimize the loss, but this time Y, the labels, are not fully known. For instance, there is noise or are weak labels. In this case, what we can do is again have another optimization, a nested optimization, where that is the upper one, where we try to find the labels that minimize our loss on a validation set. And so what we will do is to optimize iteratively these two equations. So finally, what I want to say is that all of these problems that are very important, that are essential for learning, are problems of bi-level optimization. So are problems where we have two minimizations that are nested, where there is the first one that is often called leader, where we want to minimize the parameters of our model, our neural network. But we have also a second minimization that is called follower, that depends on the leader. And this minimization is for some hyperparameters, latent variables that we call theta. And this one depends on the optimal parameters of the model. So what we do in practice for this kind of bi-level optimization, it's an iterative procedure where we first optimize the bottom, the leader equation. We find the optimal W star. And once we have the optimal W star, we find, with that W star, we find the optimal theta, so theta star. And there we repeat this iteratively with the new parameters of theta. We optimize W and so on and so forth until convergence. But it's clear that this iterative process is very expensive, because the bottom equation is neural network training, full training. So it means that for really doing this, we will have to retrain our network many, many times. So in practice, what people do, it's approximation of this, and we will see some cases. And in this way, we find a kind of trade-off between the quality of the expected solution and speed. So this, for the rest of the talk, I will give you a few examples of research that I did with this kind of problems. More in detail, I will talk about bi-level optimization for model selection. More in detail, so model selection can be many different things, like type of convolution, number of layers of a neural network, and so on. But in this case, I will talk about pooling configuration. So where to place a pooling in a neural network, in a convolutional neural network. So when to reduce the image resolution, the feature map resolution in a neural network. And I will show some interesting results. Then second, about regularization, and I will talk about determination, automatic determination, how to automatically find the right determination for a given task. And finally, about learning with latent variables, I will talk about temporal localization in videos. So I will start with the first one. And so what this is a paper that we recently submitted and got accepted to PML 2023. It's a small and new conference, but it seems quite nice to me because I got good reviews. I got like 4 reviews where they were really analyzing and understanding the paper.
So the reviews read the paper. This is already.
Yeah. And I think maybe
it's quite surprising.
Maybe that's the way to go, to try to go to smaller conferences, but with experts in the field. And yeah, I was quite happy about that. And so what's the task in this case? Again, the same equations, but in this case, what we want to find is a pooling configuration on a convolutional neural network. So what does it mean? It means that, imagine here, this is a representation of a convolutional neural network. Here will be the input image, and then we have convolutional layers, and at a certain point, we apply some pooling, and we reduce the size of the feature map until we reach the final classification in the end. But what's the best? Is it to go down in pulling from the beginning and analyze the image at coarse resolution, or analyze the image at high resolution first and then go down. So this kind of problem is again model selection, which configuration is good, and it hasn't been analyzed in detail so far. So what we did first, is to benchmark with a simple network, a ResNet 20 on CIFAR10, and we consider all possible pooling configurations for this. In this case, it's a small network, so there weren't too many. There were 36. So we trained 36 different models, and for each one, we estimated the final accuracy on a test, on validation. And the interesting thing is that the default pooling configuration that it's obtained when you use like PyTorch, for instance, was obtaining 90.5 accuracy, while the best configuration was giving 92. So it means that even for a data set like CIFAR10 that is commonly used, the pooling configuration is not fully optimized. So we thought that that can be interesting to try to find ways to optimize the pooling configuration without the need to go through all the configuration like in a brute force approach. Something interesting that we saw with this this kind of task, it's a challenge in the sense that, first of all, the task is non-differentiable because the pooling location are discrete configurations, so it's not so easy to use gradient-based approaches, for instance. And also common approaches for this kind of methods that can be considered like a network architecture search is to use weight sharing. So to have a model that will consider all the possible configurations, but here there is an additional problem that if we have a model that is trained independently and obtain a certain accuracy and another one obtain another accuracy, if we train the two models together, there is interference. So it means that one configuration is damaging the other one because they share the same parameters, but they're trying to do different things. So, and we will try to deal with that. About previous work on this, I will go quickly. One approach is to try to relax the problem and make
Very
it.
quick question.
Yes.
The combination of the two, do you average or what do you do with the parameters?
Here,
Yeah.
it's really at training time. Well, there are different ways. For instance, in this case, we relax the problem and all the possible configurations are used at the same time. So you can think about it as a weighted average. And there are other approaches that I will talk more in detail later that we sample. We sample each configuration, but using the same parameters. So first thing, in case of darts, that it's a commonly used approach for neural architecture search. We have this supernet that contains all the pooling configurations, because if you think about pooling, the parameters of the model are the same. It's just where you place the pooling. And here you can see we have a models with layers versus resolution. And for each layer, you can think about it as you have a probability of selecting one of the resolutions. So, for instance, imagine in this case, we select in the beginning high resolution, and then we go down to lower resolution until the end. But what was interesting to see is that this kind of approach, while it's commonly used for many different problems, doesn't really work for finding the pooling configuration. And apart from this, also, it's it's memory hungry because it needs to contain all the configuration at the same time. So we have a softmax of all the different configuration, like high resolution image, mid resolution image, and low resolution image. Of course, there will be one resolution that is dominant, but also the others are kept in memory. And so it's not really feasible for a big neural network, and it doesn't really work. Another approach is single path, one shot. In this case, it means that every time we want to use this model, we sample one path. This is a path over layers and resolution. For instance, this is a common path where you start high resolution, middle, and low resolution, and you train with this path. Then you take another mini batch and you train with another path, and so on. In this way, you train again the supernet, but the advantage is that you consume less memory because you sample one path at a time, and you use uniform sampling to avoid biases, in the sense that every configuration will have the same probability to be used. And this approach works, but still doesn't obtain very good results. And so what we propose is a balanced mixture of supernets, which means that instead of having a single model, so here we have, again, our architectures, and here we have 4 models, for instance. And what we do over training is try to associate each model to some of this architecture. So it's a kind of matching problem. And if we do this well, at the end of the training, we will be able to associate each configuration to one model. In this way, the problem of inference, the problem that some models are hurting other models, will be reduced, because we will have multiple models, and some models will be associated to some configurations, and other models to other configurations. When I talk about this model theta, I mean parameters. So instead of having only one set of parameters, we will have 4 sets of parameters. So here, what we do in practice with this approach, we have configurations. So this is the different pooling configurations, and we have, in this case, again, 4 models. And for the configuration, we will sample uniformly, again, to avoid any bias to a specific configuration. And once we sample a configuration, then we will have a set of probability to be associated to one of the 4 models. And of course, in the beginning, these probabilities will be uniform, but over time, we sample from this sample of a model, we will we will apply this sample to our model, and we will obtain a loss. We will use this loss to optimize the parameter W, but we will use this model also on validation to estimate the accuracy of that model. And this accuracy will be used as estimation of which model is the good one. So we will use this accuracy normalized as a way to estimate which model is the good one. And we will make sure that all these models, when we marginalize over configuration, this model will have always the same uniform probability, so that every model will be used on average the same amount of time. In this way, we obtain a way to use multiple models and each model will be associated to certain configurations. Here you can see some results. For instance, here we have what would happen with, again, 4 models and our 36 configurations. And in the beginning, the model is initialized uniformly, but then over time, each model will specialize to certain configurations. And at the end, you'll see that, for instance, certain configuration will be associated to model 3, other configurations to model 1, and when we go to consider the performance of this, we can see here we have the ground truth performance, so the performance of each model trained independently, and on this axis we have the evaluation accuracy. So the accuracy of our balanced mixture on a training on the validation set. And so we want to see what is the correlation between the evaluation of our model that is using only either 1, 2, 4, or 8 models versus the real quality of the solution. And here we can show results, and we can see that if we increase the number of models up to a certain point, the correlation of the model of our balanced mixture with the ground truth gets better and better. So 4 models normally it's the best one. 8 models start to it's similar, but performance gets reduced a little bit. And here's some results. So first of all, we compare these balanced mixtures with the commonly used methods like DARS, like expose, and others. And we see that for this specific task, our method is the only one that gets close to the best accuracy. It doesn't get the best accuracy, but it gets close enough. And with a computational cost that is much lower than if we have to evaluate independently all the configurations. And we evaluate this also in other data sets on ImageNet and also on Food 101. ImageNet results are not so impressive. What we saw is that with a model, a mixture with 2 models, we were able to obtain same results as the default configuration. And we think it's because the ResNet model was actually optimized on ImageNet, so we couldn't really find a pooling configuration that is better than the default. But for instance, on a different data set like Food 101, we were able to improve over the default configuration. Default was 84, and we went to 84.6, quite a bit. And that was the first paper that I wanted to talk about. I will go quickly also to the second one about automatic data augmentation. This was a paper that was published in WACRI 2021. In this case, what we want to do, again, we have the same task where we have a bi-level optimization. And in this case, what we want to do is to find a transformation. That's why we talk about data augmentation, because we want to transform the input with a transformation theta with the parameters, transformation t with parameters theta. And again, it's this one, it's also a little bit more challenging than the previous one, because you see that while the previous one, the parameters theta were appearing in the first and the second equation, here the parameters theta are appearing only in the lower equation. So it means that while the other one we could optimize the 2 independently, here when we want to optimize this data, so finding the optimal data, we don't see directly data, but we know that W star depends on this data. So what we need to do is first optimize W star, and this W star, I didn't write it explicitly, but this W star, of course, depends on this data. And so after optimizing W star, we can find the optimal data. And then with the optimal data, we'll repeat again and again until obtaining the final optimal data star. And in this case, data are transformations. So imagine that we have an image and we can apply different distortions, and we want to find which one is the optimal one for training a neural network.
So tell is just a geometric transformation of some kind?
Yeah, I mean, it could be also color transformation. We tried with a few, but yeah, we can think about it as a geometric transformation. So some previous work, other people tried to do the same. For instance, a famous one is automatique, where they also optimize this bi-level objective by sampling policies, where a policy is a set of transformation of the input image. The problem with automatique is that it's really slow, because what they are actually doing is really starting with a certain policy, a certain set of transformation, training the entire network with this transformation, and then estimating the gradient of the loss on the validation set, and then repeating. So it's really, there is no approximation of the bi-level optimization, which is good because it can lead to very good results, but it's also very slow. I don't remember exactly, but they were using thousands of GPUs to really get results with automatique. Then the same authors came out with a randomatique that is much simpler, because instead of optimizing with reinforcement learning policy, what they were doing is just finding the magnitude of the transformation. So transformations were fixed, but they were finding how much those transformations were useful for the task. And this is faster, because it's finally it's a validation. So you try with different magnitudes and you find the optimal one. And it's a strong baseline, but it's suboptimal. So what we proposed instead was to, instead of explicitly giving transformations, we train a neural network that generates these transformations. The problem is that with the neural networks, normally means that these data are not a set of few discrete transformations, but it's parameters. And with a network, normally we have many parameters. So while the previous approaches were normally limited to a reduced set of parameters to learn, in our case, we have parameters that are much more. And so approaches, we know that when we have many parameters, we cannot really use optimization without gradient, because it doesn't scale. And so in this case, we need to use gradient. And so what we do in practice, you can see it here, the double loop of the bi-level optimization. We have an image, we have what we call the augmentation network parameterized with data, and we have some noise vector that defines which kind of transformation we want to use, adding some stochasticity to the transformation. We get the augmented image, we have a classification network, and we train this as normal. But we have also the outer loop in blue, where we use the same classification network without augmentation to get a validation loss. And now we want to join the two. And how we join the two? Through the network parameters, because these network parameters are the same for the validation and for the training. So what we do is finding the augmentation network parameters such that the classification network on the validation loss is minimized. And so if we do that, what we need is the gradient of theta of the loss on the validation set. But this is not easy to compute, and we need we apply two kind of approximation. The first is, instead of computing the real W star, if you remember, the W star means to really train the entire neural network. Instead of train the full neural network, we apply only one iteration of gradient. So it's an approximation, it's not optimal, but we'll show that works. And the second one, we approximate the gradient of theta. So I will show it more in detail with a visual representation. So what we do in practice during optimization is this kind of iterations. We need to compute the optimal W star. And here I show the real bi-level optimization. So we have iterations of gradient on W until we converge to Wn. So we train a model given a certain theta1 set of transformations. And once we train this model, we can compute the new theta. So theta2 will be theta1 minus gradient of the loss on the validation. And for doing this, we need to go through the entire step of gradient that we use for computing W star. So you see that one single iteration of this is training the entire model, go back with gradient descent on the entire training loop. And this is not only computationally very expensive, but we will need to keep in memory all these iterations. So it's not really feasible. And we do this multiple times until convergence. So this is not really feasible. First approximation that we did, as I said, is instead of computing the real gradient of theta on the validation loss, we compute the gradient only on one step of our training. So we can still train the entire model, but then we compute an approximation of the gradient. And second approximation, it's also, as I said, instead of computing the optimal W star, we compute only an approximation of W star with one step of the gradient. And this is feasible to run. Of course, it's not optimal, but at least for our problem works. Here we show some results. I won't go into detail about these results, but we were able to perform better than some predefined transformation and also some validated transformations on the validation loss. When we got to bigger models, like instead of ResNet, while on ResNet we were pretty close to AutoAugment, with bigger models, we were a bit farther from those models. We don't know exactly the reason, but it's still much faster than the other models. Let me see. I will go very quickly to the last one, and it's again using bi-level optimization, but this time for learning latent variables. We had a few papers on that, and we apply it also for weakly supervised object detection, but I won't have time to do that. In this case, as I said in the beginning, what we want to do is to find the labels, the like removing noise or finding the optimal labels for our task. And for this, we need again this variable optimization. But what we can do to simplify a bit the problem, instead of really doing it on a validation set, we can do it on the same data. So we don't use anymore the validation set. And in this case, the advantage is that we will have the same variable again on the two, on the lower equation, but also on the upper equation. So it gets easier to optimize this, because in this case, we can just iterate between the two and we have the same variable. We won't need to use gradient on the update of W as in the previous approach. What we want to do exactly is to find the emotions on videos. Like you can see here, there is a video, and we want to classify which emotion is on this video, but to get a good classification, we need to also know in which part of the video we have the emotion. Like you can see in this case, there is a part of the video that clearly shows the happy face, but other parts that can be misleading. So we, in this case, then Y is a variable that tells us how important is a certain frame, temporal frame, for our task. And a simple way to deal with that is with what we call softmax pooling, in the sense that instead of using a representation of a frame F, we use a weighted representation. So we have this Y that tells us what's the importance of a given frame. So the final representation will be a weighted sum of the representation of each frame of the video. And this weight, it's again very simple. It's just a softmax on the scoring function of a given image. And this scoring is again a neural network. And this is so a softmax parameterized with temperature, so that we can, if the temperature is very high, we get something very similar to average pooling. If the temperature is close to zero, we get something similar to max pooling. So in this sense, we generalize the compromise between average pooling, where every frame has the same importance, and the max pooling, where we consider only one frame. The problem with this kind of approach is that it works quite well, but again, it's a computational issue, a memory issue, because if we train with long videos, they won't fit into memory. Yeah. So how to deal with that? The previous approaches, they were using something very simple, uniform sampling. So instead of training on the entire video, you just sample randomly one frame, but that's not optimal. So what we could do instead, it's what we call this important sampling. That will go a bit more in detail. So here you see the uniform sampling means that we have a function that we want to optimize, the score of our neural network, and the pooling will be uniform. So it means that we give the same importance to every frame, and also the sampling will be uniform. And this is what they were doing before. And as I said, the advantage is that as we sample, we use less memory. In expectation, it's still the same objective because it's Monte Carlo sampling, but we don't. There is no way to give more importance to the important frame of a video. So the straightforward way will be to, instead of using a uniform pooling, we use a pooling that gives more importance to certain frames. In this case, so again, the same advantages of the previous one, but the main disadvantage is that as we sample still uniformly, we have high variance, because if we sample the location where the function is not important, this sample wouldn't tell us anything useful. So to improve that, what we do is, instead of using a weighted sum of the function, we move this weight into the sampling. So instead of sampling uniformly, we sample with a multinomial that is proportional to the importance of a given frame. In this way, we get the advantage of still sampling and still reducing the amount of memory. But this time the pooling is uniform. We give the same importance to every frame, but we sample proportional to the importance of the frame. So same results, but faster and better. I won't go into many details, but what we do in practice is to approximate the weighted sum of our function with sampling of the function at location S, where S is sampled with this multinomial. And sorry, you can see here more in detail, same thing. So we have an approximation of the importance of our video, and this approximation we sample with this importance. We use the sample to update our model, but we use the sample also to update our importance function. In this way, we were able to obtain something like this. You can see here, for instance, for emotion and also for action recognition. Instead of using uniform sampling, we use a sampling that is proportional to the estimated importance of the sample. So you can see that the sampler will focus on the important part of the video. And this has two advantages. One is that it will train slightly faster, but it will give also better results compared to uniform sampling. And we compare also with a standard baseline based on reinforced, and we were able to obtain better results. And we compare also with different baselines. So to wrap up, what I presented today is what I wanted to show is that in learning, we don't need only to fit the data, but also to generalize, to select the model, and to also, in some cases, learning missing or noisy data. And we can cast all these problems as bi-level optimization. So in this sense, what the title of this talk was is that learning is a bi-level optimization problem. So often when we teach, we say that learning is minimizing a function, but it's a bit more. But we can cast this as minimizing a bi-level optimization problem. To finish up, so I'm looking for collaborations. Here I talked quite a bit about bi-level optimization. I would like to understand a bit more what are the consequences of the approximation that we did, because we applied some approximation, but and we see that results are decent, but we would like to understand a bit more. And also, I like to work on these sampling-based approaches, because we know for training models, we have large data, and it's much more efficient to sample from this data instead of really using all this data all the time iteratively. And finally, I didn't talk about this, but I'm also starting to work on large language models and transformer. Especially, I I'm started to work on reduce the quadratic constraints. We know that transformers work very well, but they require quadratic cost, and also try to find a good connection between these models for text and vision. Yeah, that's it. If you have any question.
Thank you, Marco. So the next speaker is Emily Chusenu. She's not, she was here on Monday, but today she needs to take a train. So she requests us to be able to join by Teams. So now we're setting up the presentation. Emily, can you hear us?
Yes, very well. Can you hear me?
Okay, great. Excellent. Yeah, perfect. Yeah.
Great. And I also share my slides. So it's
Emily is a research scientist from India. She's working here at Central Supélec together with CVN, which is the computer vision team working on, in particular, on medical images here in Central Supélec. And so Emily was working for a while on optimization, on image processing, as of course now, so as everybody, she's also doing machine learning. So yeah, we are happy to have you here, Emily.
Thank you. So can you see well my slide? It's fine?
Yes, yes,
okay,
perfect.
Wonderful. Yeah. Okay, so first I would like to thank the organizer of this super nice workshop between DATAIA and ILLS. So indeed, I could not make it today, but I got the chance to discuss with many of you on Wednesday. So today I will present some joint work we did with Professor Ismail Benayed from Mila when he was visiting our lab CVN during his sabbatical year. And at the end of my talk, I will also mention briefly some like other topics we are working on in my group to solicitate potential collaboration with you. So the title of my talk is Primal Dual Minimum Description Length for Practical Few-Shot Learning. So actually this work was presented last year in NeurIPS. So I will first introduce the problem. What is this few-shot classification problem? I mean, it's original formulation, and then I will introduce the formulation we are considering in this work, which aims at being more realistic. So what we propose, this is a formulation of a new cost function and also a novel inference strategy for the learning, and then some results. So let me first briefly introduce you. Maybe you already know the few-shot classification problem. So I take the easy example of animal class classification of images. And I mean, in standard supervised learning for this kind of task, we would have some training data with some images of the different class, and we would just learn from this training labeled data to identify the different classes from images from these classes. But what happened is few-shot is a bit different, because our test data contains some classes that were not present in the training set. So this is really the main challenge in few-shot. So in this example, in the training data, we had these animals, cat, dolphin, etc., Labrador. From this training data, basically what we could do, for example, is to train a feature extractor. But at test time, what is happening is that we have new classes appearing. Of course, the idea is that the task is not so different. We are still classifying some animals, but some animals that were not in the training sets. For example, giraffe, ladybugs, etc. In the context of few-shot, we have two important quantities, which is here K, which is a number of new classes, and the number of shots. Indeed, we are doing, so this is not unsupervised, this is weakly supervised, in the sense that for these new classes, these new K classes, we have access to some labeled examples. So of course, this number of new labeled examples, there would be very few compared to our big training set. And this is what we call shots. So basically, we could have 5, 10 shots, and even we could try to go to 1 shot or 0 shot would correspond to the unsupervised classification problem. So this is what we are calling the support set. This is our like a mini new training set. And then from this support set, what would be the goal is to classify what is called the query set. So we have some images. The class of these images are within the support set, and the goal is to identify these classes. So as I recall, none of these classes have been seen during the training. It's called transductive few-shot task because we would like to address all the query set at once, meaning that we do not want a method that at each image redo some kind of training clustering. We would like to have all the aggregated support and query set and to make a decision on all the full query set in one pass. So this is what our method will do. So this is a standard few-shot setting. Typical strategy that we will adopt here is that because the tasks are not so different, as I said, we are still classifying images of animals. We can benefit from this similarity to adopt a feature-like approach, where we will use a training set to train a feature extractor, and at test time to reuse this feature extractor to do the classification on our new classes in some kind of clustering way. So let me go to the more realistic scenario of few-shot. So this was a scenario I already described, and as we saw, the classes that were in the support set were exactly the same as those in the query set. And also in typical few-shot approaches, this is assumed that the tasks are balanced. It means that we have a balancing in the support set. It is very balanced. And also, the distribution of the classes in the query set follows the distribution of these classes in the support set. But actually, what is happening in practice is more something like that, meaning that in the support set, we have some few label images from new classes, but in the query set, we do not have necessarily all the classes of the support set present. Basically, in the support, we would just propose this mini training set, propose these new classes, usually a bit more classes, which is what we call K, large K. And in the query set, we only have KF, so K effective classes that appear in the query set. And usually this number is actually much smaller than the one that was available in the support set. And we still would like to take advantage of this larger K in the support set. And the second point is because of this difference, but not only that, the task is in balance, meaning that the distribution of classes in the support is not necessarily the same than in the query set. Basically, we don't want to make any assumption on what is happening here. This is just how it is. This is just what are the classes and what are the distribution. So what is our proposition is to formulate this problem to account for these two challenges. So this is basically the overview of the approach. So as I recall, we have this F5, which is our feature extractor. The feature extractor, this is trained on this big training set. And in the context of few-shot, we freeze actually this feature extractor, meaning that in our method, we will not retrain the feature extractor. This is how it is. It's a feature extractor adapted to, for example, classify natural images. Okay. So what the method is doing actually, it will take as an input the query set, which is a list of unlabeled images, and the support set, which is a list of labeled images. And the goal is to predict the class of the query set. Okay, so how do we do that? So first, let me introduce some notations, the query set or some images. So we have Q images XN, and for the support set for each image, we have also associated a label. And we assume that in total, we have large N samples. So from Q plus 1 to N, we are in the support set. And in top of that, we also have access to what we call the feature vector, which is for each input image. We can just pass it through our feature extractor to compute this N. So this is what we propose as a cost function. So what we will do is that we will estimate jointly the label. So this is a soft encoded label. So for each images of our test set, we estimate some labels, and we will also perform some kind of clustering type task, meaning that jointly we will learn for each of the K class what we call some class prototype, which represents some kind of average of the extracted feature within a given class. So this is kind of the center of each cluster. Okay, so we have many terms in this cost function, so let me explain a bit. So the first term corresponds to really the clustering problem. We have some features. We would like to spread them into different classes with the number of classes. Okay, but to this we add some two extra terms. So the first term aims at imposing this idea that actually we do not want to have a classifier that search for the maximum number of classes present in the data set, but we would like to penalize the classification to have only like a minimum representation of the test set, and actually to penalize basically here from 3 clusters, we would prefer only 2. So to reduce the number of effective classes that are found in the data set. Okay, so this is what we are doing with this term. And here in terms of notation, U at K corresponds to the proportion of appearance of class K, which is not necessarily equal to 1 over Q, because as I said, we do not consider necessarily a balance classification task. We have the second term. So the second term, actually, the idea is just to impose in a soft way the constraints that we are addressing classification with soft labels. So we have some simplex constraints on this label, and we address this using this anthropic barrier. I will go back a bit later now on the interpretation of this term, but just before that, I would like just to remember you that we are in the few-shot setting. This is not totally unsupervised. So of course, we have some supervision constraint, meaning that for the samples that are in the support set, we actually know the labels of the class. We know the true labels. So of course, we will freeze this label, and this is done under some constraints that I'm not expliciting here for sake of shortness. So let me try to give a bit of more statistical interpretation of all these terms. So actually what we showed is that the first term actually exactly corresponds to the negative log likelihood of what we would obtain if we did probabilistic k-means using a Gaussian model. But actually this is interesting, because if we look at this term, which is our data fitting term in our objective, we could also rewrite this term using Bayes' rule as follows. So actually, we could show that we showed in the paper that this term decomposes into 2 terms, and actually in these 2 terms we see these blue terms here that has a totally counter effect of the one of our penalization. And remember that it was minus lambda sum of UK log UK. And actually, this term is the cause of what is well known in k-means, that k-means tends to promote a very balanced very balanced clustering, which is it leads to some kind of bias, but this is not what we want. In our case, we don't want to have something balanced. We really want to authorize some unbalanced classes. So basically, the idea is that our penalty function is actually trying to compensate this term, which simply give us the intuition that we could simply take lambda as the number of elements in the support. Okay, so at the end of the day, we need to solve this minimization problem. Actually, it's quite difficult because especially with respect to variable u here, so matrix U, it's just a concatenation of all the U and K. These variables appear here, and also here, through in a complicated manner because U hat is the sum of U over N. So we don't have any closed form for the minimization step with respect to variable U. So what we propose is to use the dual formulation of this entropy term, which is, and this is what we obtain. So we have an auxiliary variable, which is a dual Lagrangian variable V. And now we need to minimize this function with respect to 3 quantities, still with respect to our constraints. So what we propose in our work is that, so what we show is that first, each minimization with respect to each of the variables is closed form. We show some convergence guarantee for alternating minimization algorithm. The advantage is that we do not have any like hyperparameter to set in, especially no complicated step size in the algorithm. And also we had this good intuition for setting lambda, as I said. And we also have a very low complexity of the algorithm. So let me go to the results. So we did different scenarios on the mini-ImageNet and tier ImageNet data sets. As you can see, so K is a number of classes in the support. So here this is 20, here this is much more, 160. And the number of shots, I remember that this is a number of this extra training data that you have in the new classes. So we go from 5 to 20. Of course, 5 shots is much more challenging, and we can see that the metric are a bit decreasing. The metric here is the accuracy, the larger the better. And what we show is that we are actually extremely competitive, especially when we are from 10 shot, 20 shot. And we are what was interesting is that we were also, we got very good result compared to the state of the art in the scenarios that we were actually interested in. That is, K is very large, but the number of effective classes in our test set is only 5, meaning that our method is able to decipher that among these 160 classes, there are only 5 that appear, and it's not completely lost around this large amount of classes. So this is a bit also the goal of this plot. We change the number of effective classes, and we can see that our methods stay competitive, whatever the number of classes. And actually, it's even more competitive when we have very few effective classes. And this is really the role of the penalty term based on entropy that we introduce in our formulation. It really penalizes the number of classes. Okay, so that's it for this contribution. Just want to mention that we have also shared our code in this GitHub, and of course we thank DATAIA, especially for supporting the visit of our PhD student Ségolène Martin to Montreal, which was of course super useful to really finalize and do this great collaborative work. Just a few words about, like more general about our research group. So as it was said, so I'm an in-real researcher in this OPIS team, which is optimization for healthcare. In English, optimisation image et santé. which is part of INRIA Saclay. And of course, we really would like to pursue and, if possible, intensify your collaboration with Mila and ILLS. Just a list of some of our expertise that you might find interesting. And in any case, do not hesitate to contact us. We work a lot on continuous optimization in high dimension, for example, based on fixed point theory, proximity operators, majorized minimize algorithm. We have also some very interesting recent work on Bayesian inference in high dimension, especially with application to Bayesian neural networks training, which can be used to have uncertainty quantification in deep learning. We have also some researchers working on optimization of graphs, for example, through graph representation learning or optimization for sparse graph models. And it's a bit clear in this work, we really want to have understandable interpretability in our machine learning, deep learning approaches, and especially we're working on deep unrolling / plug and play approaches for the resolution of inverse problem in imaging. And also we have an expertise in the showing the robustness of neural networks. And finally, of course, any biomedical.
Right. So it's a great pleasure to have with us Mark Coates. Mark Coates is a professor at McGill University, at the Electrical Engineering Department. He has been working on topics related to statistical signal processing, communication networks, and particular learning on graph. This is what he's going to talk about today. He's also the co-director of ILLS and joint member also with the Networks Research Laboratory. So Mark, please, it's our pleasure to have you here. Go ahead.
Thank you very much. Good morning, everyone. So I'll start by putting on my hat as co-director of ILLS, which I like the pronunciation of ILLS. The acronym for us is ILLS. ILLS is not great. So ILLS is better. So on that front, I'd like to thank the DATAIA. They've been fabulous hosts. I think it's really gone well so far. And Pablo for doing the organization of this workshop. What we had in mind, I think, and what's been successful is this is really an opportunity for us to advertise. And in fact, my talk is going to be more of an advertisement of what I do rather than delving into a particular topic in detail or a problem in detail. I think we've seen that that's been successful over the past few days and hopefully today as well. The real goal is to start some more lengthy and profitable collaborations between us. That's been happening, and I've already had the luck of having an intern come, and also I have a PhD student, co-supervised PhD student, starting September. And I think this is what we're really trying to foster. Where are the intersections of our interests? How can we start collaborations? And so keep that in mind. I have PhD students who are keen to come to France. So if there's people who are keen to come for visits in Montreal, we'd love to have you spend some time with us where we can really discuss research ideas in detail. Okay, so co-director hat off and then back to researcher hat. I'm going to be talking about learning on graphs. So this is really the research that I've been doing primarily over the past 5 years or so. Well, I've been working on networks and graphs for 20 years, but really focused on graphs the last 5 years or so. This is a depiction of my journey. From a weather perspective, I'm an idiot. So I grew up 50 meters from this beach. On the top left there, from Adelaide, Australia, this is Semaphore Beach. So lots of time in the sun, enjoying swimming. Yeah, it's terrible. So you can come and visit me in Adelaide as well. And then my journey has been to Cambridge for a few years for the PhD. I spent a couple of years at Rice University in Houston, and then up to McGill and Montreal, where I've been for the past 20 years or so. And the three sort of pillars of my research that you see in the triangle there are Bayesian analysis and time series. So I cut my teeth doing time frequency analysis in Cambridge, and there the lab I was in was Bayesian through and through. That was, I was indoctrinated from a young age, and I find myself just when I encounter a problem, I often just naturally think about it in a way that's a Bayesian formulation of the problem. It makes a lot of sense to me. And so that background in time series was what I was doing initially. I was looking at some slow wave potentials from monkey brains, bat chirps. These are sort of interesting signals from a time frequency analysis point of view. Time frequency naturally led to wavelets. And then when I went to Rice, wavelets, it was the time where network traffic analysis was becoming very interesting for the community, and the multifractal nature of network traffic was a good fit for wavelets for estimation purposes and modeling and so forth. From modeling network traffic to starting to look at network problems was a natural transition. So I started looking at network monitoring, sensor networks and so forth. That, when you start talking about, let's look at signals that are on time series that are on networks, doing inference about networks, that naturally leads to a focus on graphs, representing the networks as graphs and doing the modeling there. So this is sort of the journey and the topics that I've had over the years. And then just focusing a little bit more on what does my lab do now, or what has it done over the past 4 or 5 years. There's been a big emphasis on, well, I've done the transition. I'm a sort of reluctant neural network person, but even I accepted it, well, temporarily anyway. So, and I have discussions and arguments that some of the neural networks in the graph domain, at least, well, we saw a nice presentation that you can think about them as graph signal processing convolution filters on a graph. It's maybe a nicer way to think about it, or graph kernels. These are other ways to think about graph neural networks. But published papers, graph neural networks, is a good way to phrase things. And on that sort of topic, we've done a lot of work on sort of using Bayesian graph neural networks. I'll talk about some of the applications, a couple of the applications that we've done, but multi-instance learning, multi-label learning, active learning, attack detection, these types of topics. Going a little bit away from the graph, so I still have quite a few activities that are not so focused on graphs. So the time series is still a constant interest for me. I guess almost 10 years ago now, I went and worked for a hedge fund. So quantitative finance analysis is still a persistent, it's more of a hobby now. Occasionally I do some consulting for companies, but I do like multivariate time series and thinking about the relationships between them. And that ties into graphs too, because you can think about the dependencies between the time series as being an underlying graph that you can think about inferring while you're doing the dependency structure. And spatiotemporal forecasting, that really sits between time series and graphs. If we think about doing forecasting, say, of traffic on a network of streets, this type of thing. Right down the bottom, some generative categorical model work recently. That's tied into graphs. We were thinking about, can we represent a graph as a sequence, and then a sequence, and for the moment, sort of focusing just on the categorical aspect, but then potentially using that in terms of generative models for graphs. And the last thing here is, I think we've seen this topic, is how do you assess the actual performance of these categorical models? We're finding that it's extremely hard to know. So the negative log likelihood is what often gets used here as or a task-specific distance. But if you really want to ask the question in the types of high-dimensional spaces that we're commonly talking about for the sequences that we're generating, the performance assessment tools are really pretty unreliable. You're getting some fairly dodgy numbers. And then in terms of some of the latest applications that I've been doing, and I'll talk about a couple of these today. So recommender systems, electronic design, automation, so thinking about the design of circuits, EDA work. And then recently we've been very interested in SAT problems, which is again related to sort of circuit design issues. Okay, so a couple of questions of why do I do these things? As I mentioned, when I the true answer for why Bayes is, when I was young, I was taught Bayes is best. I can't get away from that. But I think sort of genuine and serious answers along those lines is there is prior knowledge that we can incorporate in a lot of cases. And I'm particularly interested in active learning as a nice topic that we continually revisit, learning from less data, handling missing data or noisy data in an elegant way. And certainly one nice thing is being able to derive some confidence intervals, and from those confidence intervals being able to provide prediction intervals for whatever you're doing in forecasting. And this is some of our results for spatiotemporal forecasting. So I think it's important to be able to provide not just the point estimate. If you can provide, okay, this is the range where this value is likely to occur, and 95% of the time you get that range correct, and you can make that range as tight as possible and still have the coverage. That's an important thing to aspire for, and particularly if there's any kind of decision-making being done based on your result. Often the bounds there can be just as important as any particular point estimate. So that's the sort of answer to why Bayes. Why graphs? I think graphs because we have evidence of relationships, whether it's physical relationships in terms of a communication network, that's very obvious. Circuits, the relationship of a graph is very obvious too. It's a physical thing. Knowledge graphs, we see that there's a clear way to represent knowledge there. And then for, say, recommender systems, again, there's a graph there. And the key question becomes, how can we use information we have about the nature of the graph, as well as other measurements, in order to improve our inference and do a better job. So these are, why do I focus on Bayes and why do I focus on graphs? And that leads to the first topic that I wanted to talk about, which was work we did started a few years ago and have continued to work on it, is Bayesian, the topic of Bayesian graph neural networks. So a key idea, or the problem that we wanted to focus on there, was a lot of the work at that time was really treating the graph as a ground truth entity. So there was processing done on the graph, but every single edge was the absolute truth. And when we looked at a lot of these data sets, the graphs that were provided were being estimated themselves, or approximations based on models. So there was a lot of noise in the structure of those graphs, and it didn't seem like a particularly nice way to treat it. So one thing you can say is, well, okay, there's some true graph, and then there's edges that have been deleted that shouldn't have been. There's edges that have been added that shouldn't have been. And you'd like to somehow infer what was from the observed graph that you get, what is the true graph. Another way of looking at it is to say there's maybe a probabilistic model of a graph or a random variable, and you're seeing a realization of, so this is, the observed graph is a particular realization of a probabilistic graph. And again, you don't want to pin all your hopes on whatever you happen to observe. You'd rather consider, oh, it could have actually been this interaction. Again, recommender systems, if you think about which movies did I watch recently, well, me picking to watch, what have I watched recently? It's hard to think. But if I watched movies with my kids today, and we go back to the day, whether I picked to watch one of the Ratatouille movies or the Up movie, the particular decision on a day, it could have been one or the other, right? It's not, this is the realization. So this is the idea of, can we think about when we do a graph processing, that there's uncertainty in the graph as well. But the structure of the Bayesian, and I think this is probably one of the only equations, it looks messy, but it's in multiple colors, so you can think about each color at a time. So the structure of the Bayesian graph neural network here is to say, we have some graph model parameters. So the nasty thing, you can say nasty thing, about this type of approach is we are introducing a model for the graph. We have to have some kind of model. I'll talk in a minute or two how we can maybe get away from that model a little bit. and use fairly simple models or models that don't make too many assumptions. But we have a model for the graph, a prior model for the graph, and some parameters associated with that model. And then there's some sort of probability distribution of drawing a graph given those parameters. And then associated with any particular realization, we have weights in a graph neural network for that particular graph. And then finally, what we're interested in is the posterior of some target variable z's. Here we might be talking about there's a label associated with each node in the graph. We get some of the labels, a small percentage of the labels. We want to infer the labels for the other nodes in the graph where we don't have any information. In the case of recommender systems, we're sort of doing a ranking of missing links. So not so much as a link prediction task, recommender systems, we're saying which link is most likely to exist. Then we get an ordering of the likelihood of each link. So then what we do, then we have this sort of complicated, if we want to do the Bayesian inference, we have this fairly complicated integral, most of which is intractable. We have to think about ways to do approximations. So starting off here, we have these, we're going to make the graph model parameters conditioned on the observed graph. And then we have the graph model. In this initial work, we did an assortative mixed membership stochastic block model, so one particular choice of a model. This leads to when we want to do the inference of what is the actual graph conditioned on an observed graph, it means we're doing fairly complicated MCMC. So that's the complex part of this learning procedure. The weights, we were into a Bayesian neural network type framework. Here we do the cheat of, or the approximation, the variational approximation of dropout being equivalent to the representation of the weights. And then finally you have some sort of observation. What is the likelihood of an observation given a set of weights, given the graph, given the attributes associated with each node. And so this is the whole learning process that we then strive to do. Right. So I mentioned before that using these types of very strict models can be undesirable. This is an example of a different approach where we're really letting the observed data do the talking in terms of our inference of a graph. The structure here is really just of the prior model for the graph is very simple. It's just saying that we are not going to allow, we're assigning higher a likelihood associated with the observed edges, and we're not going to allow any disconnected graphs. So the likelihood model is very, very simple in this case, and we can do a non-parametric estimation of the graph. The key thing that this slide is trying to emphasize, and where this Bayesian approach is really useful, if I have a lot of labels and a very dense graph, the Bayesian stuff is just computational overhead and a waste of time. And you've got a lot of information, you've got lots of labels, you've got lots of edges, there's a lot of information diffusion happening anyway. But what we often have is very sparse graphs. So this is core, it's a citation graph, and relatively sparse here. You can see on the left the true observed graph. Can you see the yellow dots at the back? I'm not sure. Yeah. So there are some dots there, but there aren't too many, right? So papers aren't citing that many other papers. The recommender system graphs that we have are even far sparser than this in terms of the number of edges relative to the number of nodes. So if you use this observed graph to try to diffuse information through the network and share your representations, then you don't get very far. If you do inference using the procedure that I've just talked about, then you get this more of a weighted graph, a probabilistic representation that we can see is obeying the structure. So these are grouped into different topics for different sort of sections and communities for Cora. So we see that we have the block structure that we anticipate, but it's a lot more dense. And if we do diffusion over this graph in terms of the neural network, we're going to get much better spread of information, sharing of information through the network. And so when we have sparse graphs, few labels, this is really the key advantage of this approach. All right, so that's, it's nice to have these techniques and see that they work on some of these sort of toy examples, citation networks. Interesting to play around with, but no one really cares at the end of the day. I think it's good to see if you can translate some of your ideas into a more practical context, and that's where we have been doing the work on recommender systems, a bunch of work with a company to see can we do some improvements using these graph ideas for their recommender system. And essentially what we're building here is two graphs. So we can think about the bipartite graph of users interacting with items. So every time I click on, we're particularly interested in an app store. This is the recommender system that we're, is our final destination. But if I click on a particular app or if I purchase an app, these types of things, these can be considered my interactions in a bipartite graph. I can then build a user-user graph by thinking if Pablo and I both downloaded the same app, then there's a connection between us. I can construct a graph that way. Similarly for the items. So if the items are, if one user downloads two apps, then there can be an edge between those two items. So we can construct an item graph and a user graph. And now what we're going to, and these are sort of neural networks that are going to aggregate the information across the graphs and end up with representations, embeddings of users, embeddings of items, where we just take the dot product between those final embeddings using a Bayesian, the pairwise ranking loss in order to decide what is the best ranking. So the information, and we split this into two because we expect the item embeddings to be different from the user embeddings. We want the way that information percolates through the item graph to be different from the way it percolates through the user graph as well. So there's a separation of these two. So this is an example of, and it maybe brings to light some of the later considerations. So initial work, getting this thing to work and doing it on the relatively small scale test data. But the company, it's Huawei, that I'm working with here, there's 500 million users, active users per month. There's more than 200,000 apps that they're dealing with. We're talking about a very large graph and a very large system that has to respond to queries very quickly. So once you build this type of system, you then have to start considering how can I do inference quickly? How can I do responses to queries quickly? All of these sorts of practical issues make for some interesting research topics down the line. And so this sort of architecture or variant of it has been tested in their app store for a 10-day online A/B test. And we did see a nice, it was very pleasing, the company was very pleased. There was a 10% improvement in the click-through rate and the conversion rate once you incorporated the graph information and made use of different uses. Where does the Bayesian stuff come into this? So has to come in somewhere just because of my predilections. It's they probably would have been happy if I stopped there, but actually this sort of was liked as well. So the graph, as I mentioned, is extremely sparse. Diversity is a big problem. So we tend to, there's 200,000 apps, but we tend to recommend, a standard recommender system will just recommend the same 10 to everyone. It's a good way to get better accuracy. There's maybe 100 popular apps. And it's something you want to do in terms of exploitation, but if you really want to expose a user to some apps and share the love, then you really need to expand beyond those very popular apps. The other issue that's very important in a recommender system is the cold start user issue. If you come into the system and initially you haven't interacted with very many items at all, it's hard to know what your particular interests are. And so using the Bayesian graph neural networks to make the graph connectivity much richer really does help improve the information diffusion, and we see much better performance for those cold start users. And it also works to improve the diversity because you're forming edges that didn't actually exist and weren't observed, but they were reasonable edges to say these could have happened. And then you reach sort of further across to find out about more interesting topics.
So you're trying to minimize the sparsity then? You're trying to improve on the sparsity?
You're trying to improve on the sparsity, yeah. So, you know, ideally, I guess if you could say all of these particular apps are very close to each other in their nature, and a person might be interested in all of them, then having access, having potential connections to all of those leads to better connections through the network. And in terms of me learning for a cold start user, me learning what is of interest, I then have user-user connections to a much broader set of users, and I'll have an understanding of what a cold start user might be interested in a better way. Right, so this was one example, and a very sort of practical example of where we made use of the recommender system. And I am showing work here up until sort of 2020, but over the past 3 years, we've been pushing forward on a lot of the subsequent questions that have arisen because of this. There's lots of interesting issues that you have to explore to do with how variable are people's interests, can you track how they change over time, these types of questions. I wanted to give a quick other example of where the Bayesian neural network can slot in. So this was an application to multiple instance learning. So here we're looking at the task of assigning labels to bags or sets of instances rather than individual instances. And there's sort of two main ways of doing this. One is an instance-based approach where we would label individual instances and do some sort of pooling operation. Another way is to learn a mapping from the bag descriptor to a label. So the depiction here, a bunch of different indicators, and then can I enter the room with this bag or not? So this is an example where I guess we see, you know, which particular key or combination of keys do we need? And the interesting questions are where we need more than one key to get into the room. So the the sort of goal is to, again, we're interested in a Bayesian approach. Can we approximate the posterior of the unknown labels if we have a set of bags that we don't know the labels, conditioned on all the training labels and the bag features? Given my predilections, a graph is going to come in somewhere. And so we can consider two graphs. We can consider a graph between the instances within a bag. There are sort of dependencies.
That's the thing happens exactly yesterday. More or less at the same time,
sort of...
but nobody understood what. It's remember?
Yeah.
I think they mostly reinitiate, but then the last. So.
There was a disconnection.
Yeah.
The graph.
That graph got broken.
Sorry.
No problem. I think I can continue talking without necessarily having slides anyway. So the critical idea that here was to recognize that in a lot of instances, you could have a graph between the bags as well. So there might, in some cases, there might be side information that you can make use of to say these particular bags should have correlations or structure or be similar in some way. We can use that side information to build a graph. In other cases, we found that it was useful just to simultaneously try to infer a graph while you're doing this task of label classification as well. So the structure of what we're doing here becomes applying a set-based learning algorithm, some kind of deep set algorithm for an individual bag. They can have a different number of instances within each bag, and then a graph neural network for the bags. So we're inferring a graph between those different bags and at the same time assigning labels to each entity, each bag within that graph. And it turned out again that this is an example where the Bayesian approach, doing the Bayesian graph neural network, proved advantageous as well, because we end up with getting it's useful to be doing an averaging over multiple possible graphs rather than focusing on a particular single estimate. All right, so an example of this, what we asked ourselves was, if we were given demographic data from the US, so the US Census per county, so each individual county, we have some census information for a small set of voters in that particular county. And then some voting results scattered around the country. Can we predict how the rest of the country will vote? So all the other counties that we don't have information. Good luck. Yeah. So the instances here within a bag are the sampled voters for each county where we have some census information about those individuals. So you have a bag full of, I know that this person has these particular census characteristics. Let's say 100 individuals in each county. The features are the census data, and then the labels of the bags are going to be the ones where we know the election outcome or have good confidence in the election outcome. And then the task is to infer the rest. This is the type of result that we get. So one way you can approach it is just to do a deep set algorithm. If we ignore sort of any relationship between the bags and just look at each bag as a set of instances, learn a representation for that set, do a prediction based on the representation of the set. And what we're focusing on here is probably a harder part of the prediction process. So if you look, this is the ground truth down here. And so we see blues are Democrat, red is Republican, the usual sort of representation. We see what we'd expect on the coastal region and the cities. That's where it tends to be Democratic outcome. Then sort of heartland is more the Republican. And then there's this interesting region that tends to, in the ground truth, is a bit of a mix. There's sort of these are often the sort of battleground states where the outcome can have a lot of impact on what the overall election result is. And we see deep sets just has problems. It has problems learning altogether. It's not very confident in its output. It certainly doesn't get anything close to the ground truth. If we do the graph neural network without incorporating any of the Bayes, we do a lot better in this region in terms of capturing more of what's going on. So essentially what we're doing here is the graph, we're helping the inference along by saying there should be relationships between geographically close counties. That's our sort of input prior information graph.
So can you do sort of a feature resolution as to what is affecting what?
Yeah, we didn't look at this, but you certainly could investigate that if which are those sort of key features within it. It would be an interesting thing to explore further. And then finally, we see the Bayesian is managing to capture the mix of, and essentially what it's doing there is when you don't use the Bayesian approach, there are cities that are voting Democrat. There are the neighboring sort of county regions that are voting the Republican. If I do connections in a graph by saying, oh, they're close to each other, then the city gets overwhelmed by the neighbors and just becomes red, right? The Bayesian approach learns to kill some of those edges. So when it sees that there's a discrepancy too much of a discrepancy between the census data of individuals within a city and the neighboring regions have very different census data, it will kill off those edges in the graphs that it's sampling. And then we manage to capture a better representation of the mix of Republican and Democrat voters in this region. The last example that I wanted to talk about was EDA workflow. I'm not sure how many people are familiar with EDA. We've got sort of, we're more of a learning audience, but I come from a sort of electrical, computer engineering background. So this is, if I'd stayed in Adelaide, this is sort of what my PhD would have been on. So I almost went down this path. I was almost a VLSI person. Then I ended up being sucked more into the signal processing learning world. The EDA workflow essentially goes like this. We have a VDHL description of the circuit that we'd like to build. And then this is sort of building up a model of the digital circuit in terms of how are the signals flowing between different registers, what are the logical operations that are being performed on those signals. And so when we have this VDHL, often the next step is to convert that into what's called a net list. So the net list is representing what are the individual logical operations and what are the connections between those operations. When we see this, when I see this, it's, oh, this is a graph. Right? So this is where again, graphs can be crude approximations of things, and there might be more interesting ways to represent this and better capturing structure. But certainly as a crude sort of first approximation, a graph is not a bad idea. And then the standard approach to doing the whole workflow process is to take this VDHL description, the net list, and then start the physical design process. In physical design, you need to do the floor planning, the placement, the clock tree synthesis, the routing, etc. So where are the wires going? And what I've got depicted down here is what we're sort of interested in this work is the congestion is a really important performance factor for electronic circuits. So it's essentially saying, if you focus on a little cell circuit, how many wires need to route through that particular cell, compared to the routing connectivity or capacity that it has. And if that density gets too high, the circuit will not, it introduces problems with robustness and problems with heat concentration and lots of issues. So the usual process is this exercise takes a long time. So this can be a couple of days to do this whole exercise. We measure congestion and then we do again. So the learning sort of approach says, well, given a graph up here, could we maybe do a prediction of the congestion before we start doing all of this process? And then we can perhaps iterate up here on the net list before we start doing the physical layout and the physical design process. And so this is essentially what we're talking about here. So as I mentioned, we map the net list into these individual cells, then we do the cell placement through the physical design. Usually for the vast majority of EDA tools, they're then doing the congestion prediction after the cell placement, and then a feedback signal in terms of optimizing the placement. The problems with that is placement iteration, as I mentioned, very computationally expensive. And then it's also a problem in that the congestion can't necessarily be fixed here, right? So once you've settled on a particular net list and locked yourself into that, and design your cells, doesn't really matter where you put them and how you shuffle them around. You've already made the problem, you've already locked into the problem that's being closed. So this is here, can we use this a graph neural network approach? We've got structure here that we can perhaps infer to say, what is the congestion going to be, and can we fix things here? So the interesting thing, the big challenge there is, I mentioned sort of structural embedding. So we have a particular structure, and we'd like to, from that structure, to map to congestion. We need to get an embedding of the structure, a representation of the structure, the local structure in the graph, in order for us to do this mapping. The vast majority of structural embedding techniques don't work well across different graphs. So if I give you a training set, a whole bunch of circuits and net lists based on those circuits, and you build a graph, and then you build a structural representation, structural embedding, and then you try to apply it to a new circuit, well, you've got problems because the representation is all off. It's not going to be correct. And you need to then think about doing performance alignment. So do alignment of the graphs. So how do I do move labels around for the particular nodes so that there's some degree of consistency so that the embeddings make sense and my predictions will make sense. We need to avoid that. Our approach is to use the pointwise mutual information matrices. So the advantage here, X is a sort of a structural embedding that we capture somehow. And then if we focus on multiplying that structural embedding, so the structural embedding, we have a matrix for each individual cell, essentially, or node in this case. If we multiply that by its transpose, then if we factorize this, we've got the nice setup that the factorization is going to be rotation invariant. So the label ordering of our particular graph is not going to matter anymore. We get the consistency property that we need. Residual question is, how do we actually get these initial representations? What we use is an infinite version of deep walk. If anyone's interested in that, we can talk more. So this is the type of sort of setup that we have in the end. There's a net list coming in, representation of this using, we do some graph partitioning. So this is another thing that I'm interested in, is how do we scale. Certainly for very large circuits, we need to scale these techniques. They're still complex. The graph neural network model, and then finally a congestion prediction coming out of them. The results are okay, and they're pretty good. So certainly we see here sort of the ground truth on the left and the prediction on the right. We're picking up some of the congestion in this portion. We see that we've missed some of the congestion here. In terms of sort of a numerical quantification, so some of the traditional metrics that get used in terms of, if you want to say, take a net list and then just use some of the old-fashioned metrics, really the correlation that you observe with the congestion is pretty poor. The congestion net is a sort of competitor baseline algorithm, but it involves a lot of cell construction before you can do it. So it's not getting at the right stage. And we see that we can outperform congestion net even without going to any sort of cell construction or any cell placement at all. All right, and I'll close off just with some open questions and areas of exploration. I'm very interested in scalability questions. So this is a big issue. As soon as you go Bayesian or quasi-Bayesian, there's problems with the scalability of the approaches. Graphs, the graph, even, let's forget about Bayesian, the graph, complex graph representations. When we're talking about 500 million node graphs, or the circuits are not much smaller, they're in the millions of nodes. A lot of these approaches the complex approaches really struggle. And we end up doing hacky things like partitioning, graph partitioning. It's not, it sort of works, but around the edges, it's pretty nasty and it doesn't feel very good. You feel sort of sick doing it. We're very interested at the moment in continual learning and multitask and streaming learning. So again, in the recommender system context, you have every single day there's interactions from people. You need to constantly update your model. You need to retrain your model. How do you do that in a continual way? How do you bring in multiple different sources of information, interactions by that same set of users, different tasks, etc. So these, we're doing quite a bit of work on various types of streaming learning, continual learning. And then finally, the large language models question intrigues me, just because certainly I'm being challenged and people thinking about, you can describe a lot of these graphs as in a sort of language terms. We think about recommender system. Mark watched this particular movie today, tomorrow. What is Mark going to watch tomorrow? If I represent a graph using that, or if I say a protein interaction graph, again, I can describe the actual interactions and perhaps in a richer way than the graphs. And so the question about which graphs can be reformulated, tasks can be learned in this way. Is there a cost-benefit trade-off? Where is it going to be successful? I think there's some very interesting questions, even for us to just defend ourselves and say, ChatGPT can't do that. This is, we need what we're doing. Currently, the SAT problems are a lot of interest, the satisfiability problems, graph representations of that. And finally, these categorical sequence and graph generative models, how do we evaluate them, is the last topic of interest for me. So I'll stop there and take any questions. These are the various people who've contributed, the main contributors. There's often lots of peripheral contributors, but the main contributors for the work I've described.
Thank you for this one. Any questions? Yes.
Yes, well, have you explored in terms of scalability problem, have you explored like hierarchical solution to build up like a pyramid or some hierarchy that you can exploit or whose, relationships you can exploit?
Yeah, it's certainly a direction we're looking at and continually put. I have one PhD student who's totally obsessed by that topic, and he is very much searching for a way to incorporate that successfully. At the moment, we're sort of struggling to get things to work effectively, but it seems like a very natural thing to do. And if you have some good ideas, then I'd more than welcome them. But yeah, it does seem that there should be ways to exploit the hierarchical structure of the graph in a better way than we're doing it.
Yes.
And about scalability in a graph neural network, what's the computational cost? Is in the order of linear with the number of nodes, quadratic? Or?
Yeah, so most of the techniques are either quadratic or even cubic. It depends whether you so there's sort of naturally if you're considering all possible combinations between nodes, so possible edges, which some of the more advanced techniques and the Bayesian technique like to do, then there's naturally an n squared. If we're just focusing on the edges that exist, then it's often order n, and so we can reduce the complexity. If we're going into spectral techniques and doing eigendecompositions and so forth, which another flavor do, then we can sort of into the n cubed space, and yeah, we have this. The techniques I like are in n squared, and I'd like them to slide back here to an elegant way to get them back to something n or n and a bit. Right?
Other questions? I do have a short question. I was wondering, at some point you put continual. So how sensitive, how easy is to readapt if the statistics are not stationary? For example, yesterday we have a lot of discussions about few-shot learning where you train your model for one task and then you get a few shots. We also have a talk this morning of Emily. And we have very little information, but you need to readapt somehow, at least your classifier to this new task. You don't change everything, you just change partially your network because you don't have enough data to retrain everything. So suppose here that you have something that evolves over time, and you need to readapt every time that. How sensitive is this? How easy is to keep track of those?
Yeah, it's not particularly easy at all, and we're having, I think we've had multiple stabs at it, and we're sort of slowly getting better in terms of, but yeah, trying to balance between adapting. So particularly in the recommender system context, you want people's tastes change, or if we're thinking about products, my hamster died, I no longer buy hamster products. You want to be recommending new things. But for a lot of people, you want to remember what their long-term interests are and keep remembering those things. And so you definitely want to, we've seen if you don't train on the latest on that day, your performance caves dramatically. So you really need to be updating it every single day. The number of data points you get per day are too big for you to do complete retraining of your model. Exactly. So you have to decide, how am I going to retrain it? How am I going to balance from what happened before? Then it really becomes, one interesting approach is to try to identify which users are evolving rapidly and which users are not. And so can I focus on particular parts of the graph that need more adaptation and other parts that can stay static and I don't have to update them. So that's the sort of approach we're doing at the moment, is to try to do a heterogeneous learning in terms of the graph.
The next talk is going to be given by Laurent Audrey. He's professor at Université Paris-Saclay, also with the Center Borrelli. So he has been working on time series, machine learning, pattern recognition, statistical signal processing at large. This is in principle, was another seminar was planned at that time, but we wanted to have Laurent. So we're very happy that you agreed to be part of the workshop. So please go ahead. Yeah.
Okay, so thank you for the invite. So I'm going to speak about graph signal processing, which is kind of a mix between two communities, the one from the graph processing and the one from signal processing. And in the lab, we've been using this kind of techniques to deal with multivariate physiological signals that we have from different medical protocols in the lab. Okay, so
it's not working.
Okay. Okay. Yes, it's okay.
Is a role no.
Yes. Okay.
Yes.
So actually, the Centre Borrelli, it's ENS Paris-Saclay, very close from here, and it's the fusion of two labs. One lab who was originally the mathematics lab, doing applied mathematics, image processing, and a lot of different topics. But although another lab, which is actually a neuroscience lab. And now, since 2020, we are only one lab, and we have in the lab mathematicians, engineers, computer scientists, but neurologists, anesthesiologists, ophthalmologists, etc. We are all working together on several research topics. So one of the scientific questions that we have is how to quantify the human behavior. And it's something that we started like 10 years ago with very close collaboration between a lot of different specialties. And what we want to do is to build some pipeline, we call them pipeline, which are actually platforms where we can record the data directly in the hospitals or in the doctor consultations. We want to build a pipeline that is able to record the data, and then we try to develop all the algorithm that will process the data for different type of tasks, such as, for instance, you can help the medical doctor to put a diagnosis on their patients. We can do individual comparison of different subjects. We can do longitudinal follow-up, etc. We have lots of tasks like that, and we try to have to be able to have a global idea of everything that goes on these pipelines. So this goes with a very deep connection between the clinical environment and the lab as well. And so why are we interested in graph signal processing in the lab? Because we have a lot of data that are recorded in the hospitals that is multivariate, and we don't really know how to process this data by using some kind of structure that exists between the different dimensions of the signals. So you have one example here. It was a project made with an anesthesiologist. We studied the EEG data during general anesthesia. So here we have a different type. We have different sensors, and the idea was to say, okay, we are not going to individually use the different sensors. It would be nice to have a framework when we could take into account the structure of the data. The structure, it can be very easy. You can say that it's only the distance between the sensors. But for instance, when you use that on real patients during real surgery, the sensors can move, and the structure might not be exactly, might not correspond exactly to a spatial, just something that is related to distance. So the idea is, how can we learn this type of structure, and how can we use that to process the signals? There's another project in the lab, which is the study of, it's like motion capture, if you want. So we have a lot of sensors that are put on subjects during different type of movements. It's on a big platform that we have to record movements. And the idea, once again, is to say, okay, if you want to study the movement and the way that the subject is performing one specific movement, intuitively, there's something very strong, which is the skeleton. And how can we incorporate this information into what we want to do for the time series in this subject? And we discuss the interpolation part, because there's a lot of missing data in this type of protocols. So this is actually, yes, a very wide topic of research. The idea is to, well, what we are going to say is that we know that if we have a multivariate signals, the different dimension, there's a structures, there's a relationship. I'm not speaking especially about correlation, I'm just saying a structure. It can be several things. It can be something correct, well, with correlation. So you can have this kind of relationship, but it can be the spatial proximity of the sensors. It can be some interaction that you want to model. So we will keep in mind that the graph for us that will be used to model this interaction. We don't see that as correlations. It's more like relationships between the different dimensions. And to that end, there's a field of research that is quite new. Well, it was a lot of there's a lot of work since many decades, but the brand GSP it's something quite new. And the idea is to say, okay, we are going to model this interaction, this relationship into a graph structure, and use the graph to process the data. So here, when I will, if I have one sample of my multivariate data composed of several dimensions, that will be, this is something that I will assume that it's carried by the graph. So first, I'm going to discuss a bit of some notation, some concept, and some what are the pillars of the GSP field, and then I will show two applications: one of graph learning and one on interpolation of missing sample. So what is a graph? Probably you all know that. We could consider a graph with a finite set of nodes. We have edges, and we suppose that we are going to have some weights on the different edges. And these weights, they encode the strengths of the relationship between the different dimensions. One very important operator for the graph, which is actually the basis of graph signal processing, is the Laplacian matrix. So this formula gives you the equation for the Laplacian is linked to diffusion and graph. There's a lot of literature on that. We will just take the weight matrix that in which you have all the weights of your graph. You compute the degree matrix which is the diagonal matrix with a number of connections for each node, and then you can compute the Laplacian of the graph. In our case, it will be a symmetric positive definite matrix, since we assume that all the weights are positive and that the graph is undirected and that has only one connected component. So by construction of this Laplacian matrix, it's a quadratic positive definite form. So you will have this formula. We'll see that it's important because it will allows us to perform the eigen decomposition of the Laplacian matrix, which will be the basis for the graph Fourier transform. And if you see the constant vector, you can see that it's an eigenvector for this matrix, which is associated to the eigenvalue equal to 0. And as a matter of fact, if you have several eigenvalues that are equal to 0, it's exactly the number of eigenvalue equal to 0 corresponds to the number of connected components in your graph. So now you have the graph, and what is a graph signals? A graph signal, well, there's several definitions. It's something that is carried on the graph. So you will assume that on each of the node, you will have something. Depending on the domain of what is lying on the node, you will consider different type of data. the easy way of the easiest way of seeing that is just to say that on each node you will have a scalar value. Then you have one graph signals. It's exactly what is represented here. It's just one graph signals. You can consider that on one node you don't have only one scalar value, but you have a time signal. You have a time series. But it can be more complicated than that. You can have a multivariate time series on each node, etc., etc. So you can consider data that will be you can handle very complex data with this notion of graph signals. In most illustration that I will show you, I will consider the easiest case, which is that on each node you have one scalar value. So if you consider a multivariate time series, actually, if each sample of this multivariate time series is one graph signals. So a multivariate time series can be seen as a collection of several graph signals, because each sample is a graph signals like that. So if you look at this example, so you have n nodes here. So each node corresponds to one dimension of your multivariate time series. Then you put, so here you can label the different dimension here. Then you will have some H that will model the link and the interaction between the dimensions. You can add some weights that will model the strength of this link. And then if you have one multivariate sample of your time series, you take your multivariate time series at one specific time, then it will define one graph signal like that, where each value is carried on one node. And the idea is to process this type of data with tools from the GSP framework. So there are several ways to visualize one graph signals. So this is one way. You put just a line that is proportional to the value which is carried on the node. But what I will use in the presentation is this one. So you have a color bar, and you can figure out the value that is carried by this node only by reading the color bar. It's the easiest way to visualize a graph signal. So the graph signal processing has been used in several domains. It has been used for sensor network a lot. So people working on energy consumption, meteorology, population, etc. So they can use sometimes the real network as an underlying graph for the data. You can have interaction networks on the social network, for instance. You will model the communication between the different nodes. There's a lot of work on finance as well, and working on dependencies between different actors on the market. It has been used for image processing as well, especially images that are defined on irregular domain. So, for instance, if you work on 3D images that are recorded on the ball, like with a lot of sensors. It can be used for motion capture, etc., etc. And what can you do with graph signal processing? Actually, there's a lot of things that you can do. The main principle of this new community was to say that everything that you could do with standard signal processing, you can adapt that to graph signal processing. So you will see that the vocabulary that we will use we'll use notion as Fourier, as stationarity, entropy, so all the names that you know from signal processing, you can adapt them to this new framework. And it has been used for several tasks that are usually done by standard signal processing. So you can sample, for instance, you can use graph signal processing to help you if you want to choose a few dimensions and to reconstruct the whole data with that. You can use this framework. So it consists in choosing the most relevant nodes and dimensions to reconstruct the whole data. You can learn the data structure from the graph structure from the data. This is something that I will discuss later. You can do denoising, filtering. You can extend all these notions. So you can remove noise. You can remove outliers for this graph structured data. You can do interpolation. So you can. This is something that I will describe too. And of course, you can classify the data. You can detect events. You can predict, etc. And the idea is to say that the graph is going to help you to improve the performance on multivariate time series. So the fundamental tools of graph signal processing is the graph Fourier transform. The idea is to say that you will compute the eigen decomposition of the Laplacian matrix, and this will give you something that's, well, we call that the Fourier transform because we see some analogy between the standard Fourier transform that we define, for instance, for time series, with this one that we define for graph signals. The idea is that the different eigenvalues that we get here, we will interpret them as frequencies. I will show you later why you can draw this parallel. And then each of the eigenvalues is linked to an eigenvector, which is associated to these frequencies. And the idea is that by computing that, you compute some kind of adaptive new basis when you can project your data. It's exactly the same as standard frequencies and AVE, like your standard complex exponential at different frequency as a basis. The only difference here is that it's going to adapt this new basis is going to be adapted to the graph where the data is lying. So what is the graph Fourier transform of graph signals? You will just project the graph signals into this new basis that is computed from the eigen decomposition of the Laplacian matrix. So in order to understand a bit what is behind that, so here you have a graph. So I have put one graph signal on it, but what is interesting for the graph Fourier transform is only the graph information. And here you can see the different eigenvalues of the eigen decomposition of the Laplacian matrix of this graph. The idea is that we are going to interpret frequency just like we do in standard signal processing. We will say that if you look at low frequencies, they will correspond to phenomena that are kind of global on the graph, so that are very smooth on the graph. And on the contrary, if you look at high frequency on the graph, these tend to correspond to local phenomena. I will show you some example a bit later. So here you can see, for instance, so we know that if we do the eigen decomposition of the Laplacian matrix, the first eigenvector, we know it's a constant eigenvector. But if you look at the second eigenvector, so it's like the smallest the one that corresponds to the smallest eigenvalue that is not equal to 0, you can see you can display this eigenvector as the graph signals. And you can see here that what is encoded in this second eigenvector, if you look here you have small values, so you have negative value, and here you have a large value. So if you project your graph signals on this second eigenvector, what you will capture is like the opposition between this part of the graph and this part of the graph. And most of the time, when you look at the first eigenvector, you can interpret what kind of spatial phenomenon they will encode. And so here you have the opposition between this part and this part. And if you look at the third eigenvector, it's the opposition between this part of the graph and this part of the graph, and etc. etc. When you will look at the graph Fourier transform of your signals, you will be able to study the different spatial relationship that are present in your signals. So most of the time, this interpretation, you can do that for the first few eigenvectors. Most of the time, the second eigenvector is like some symmetries. You can see some anti-symmetries, etc. But once you go to the larger frequency, it's more difficult to interpret. Why is it important to have this graph signal representation? So here you have one graph signal, and you have is spectral representation. So the idea is that you will most often you will realize that exactly well, it's like an analogy with what happens with standard signal processing. There's some sparsity that is induced when you transform the signals into the Fourier domain. And you have something like that as well when you transform your graph signals into with the graph Fourier transform. You can see here that not all the frequency are activated on this signal. And this will be a very important property as well. You can see here something else that is something very common in signal processing as well, is that there's not much of the large frequency. So most of the content here is present in the low frequency. So you can see that there's a link to be made between the low band properties that are often assumed for denoising, etc. when you work on temporal signals, and the one that you can use here for spatial graph signals. So yes, we will see one property that is very important when you work on graph signals. Is the first one is the band limitedness. So meaning that most of the time when you will have a graph signals and you will compute its graph Fourier transform, you will have this sparsity constraint, meaning that the support of the graph Fourier transform is smaller than the number of possible frequency. And this is why you can do a parallel with standard signal processing. Not that the sparsity in the frequency domain, it is the basis of basically all the work that has been done in signal processing for denoising, for sampling, etc. You have a lot of things that you can now apply to something that is not temporal, but that is spatial. So here you can see, so you have the spectral representation of the original signals. What I do here is I remove all the frequency that are not very present in the spectrum, and this will change the graph signals in the same way as something that you will do by filtering signals or denoise a signal. You will remove some of the frequency bands, and you do the inverse transform. It's exactly the same principle that you can use here for filtering the graph signal. The other very important notion for GSP is the notion of smoothness. So the smoothness of the graph signals, it's exactly the term that we saw earlier here, and this term will tell you whether a graph signal is smooth according to the graph or not. What does it mean actually? The smoothness is a term. It's small. When will the smoothness be small? It will be small when if you compare the signal at dimension I and dimension j, when those are very different and are very connected with the graph, then you will tend to have a small smoothness. So actually, you want to have this term as small as possible, because you want that the dimensions that are very close according to the graph have similar value, and this will give you a property that is very important when you do graph signal processing. So here you can see two signals. One is smooth and one is not smooth and the other one is smooth. You see here that there are nodes that are connected that have very different values, meaning that they are not smooth. On the contrary, this signal is more smooth. And this actually is something that will give us an interpretation of the frequency. because if you apply the smoothness term of the different eigenvectors for your Laplacian matrix, you realize that the eigenvalue is exactly the smoothness associated to the eigenvector. So actually, when you will have eigenvector that will be less and less smooth when when the frequency becomes larger. And this is how you can draw the parallel between what you know on signal. You will see that a smooth signal is low band, and that is not smooth signal is high band. You have exactly the same here. And of course, if you have the smoothest signal is the one that is constant, and then of course the smoothness is equal to 0. And so with that, you see that with the band limitedness, with the smoothness, etc., you can have some kind of interpretation of the spatial aspect of your graph signals. So you can use the smoothness and the low frequency approximation for denoising, for instance, for interpolation, and you can use the notion of sparsity of band and band limitedness to perform tasks such as sampling, etc., etc. So I will show you two examples of how this notion can be applied to perform tasks on graph signal processing. So I will show first the graph learning. So how can you learn a graph from data, from multivariate time series? And we will see that this graph learning will actually be based on the two notions that we have seen, the band limitedness and the smoothness. And it's something that we use for EEG and brain data. And the second one is the graph signal interpolation that we are actually based on the non-smooth assumption, because yes, we will see that the smoothness assumption is not good if you want to do that for 3D movement analysis. So as far as the graph learning problem is, what we want to do is that we suppose that we have a multivariate time series that can be seen as a collection of several graph signals, and we want to learn a good graph. What is a good graph? So of course it's an impose problem. We don't know. Here you can see you have one graph signal and there are two graphs. How can you say which one is the best? So the idea is that we will put the assumption that we saw earlier. We want to find a graph where all the signals are smooth and band limited. And we'll use this assumption to learn a graph that is coherent with the data. So as input, we take a multivariate time series, which are seen as several graph signals. And what we want to output is the Laplacian matrix of the graph. And we will see that we use another variable that is interesting for us. It's the GFT, or the graph Fourier transform of these signals on the graph. So the optimization problem that we solve is a bit complex. So I'm not going into detail, but I will just show you the different terms that we have. So first, the first term here is to say that you want that the spectral representation of your signal on the graph, you want that if you compute the inverse graph Fourier transform according to the matrix of eigenvector that has been estimated, you want that to be close from your original data. It's a data term, if you want. It's something that will say that the spectral approximation of your signal should be correct. You have a second term here, and it's not really visible here, but if you reformulate it, it's exactly the smoothness term. So it's something that will say, I want my graph signal to be smooth on the graph that I will learn. And the last one is a constraint that we apply on the spectral representation of the signals. And here we'll use a sparsity term. So we will say, okay, so this is a data term, this is a smoothness term, and the band limitedness. So we want you want the graph to force your signal to be band limited and smooth. Then you have a lot of constraints that makes this problem very difficult to solve is that, of course, you need to learn the Laplacian matrix. So there's a lot of constraints. You want it to be positive, definite, etc. There are some constraints to make sure that there's no numerical issues. So it's a complex problem. Of course, this is not convex, so you will use alternate minimization. You will actually try to learn three things: the spectral representation of your signals, the matrix of containing the eigenvectors, and the eigenvalue of the Laplacian matrix. So I'm not going to detail for the algorithm for optimizing this problem, but I will show you some results. So here is the easiest case, meaning that we computed two types of synthetic graph, and we generated graph that were band limited and smooth graph signals. So this is a proof of concept because yes, you see that of course with the algorithm you can retrieve you can retrieve the weight matrix here, but it's well, you know, the data is generated exactly according to the model. So what is more interesting is to see something on real data. The problem with the evaluation of this type of task is that we don't have the ground truth. So actually, what we will be able to do is to just look at the data and figure out whether it seems accurate or not. So here you have some temperature of the data in Brittany. So you have several. You have 700 samples, and here you can see the graph that is learned by the algorithm. This is just we were happy about that. We were one of the students working on that was from Brittany, and he said that it was okay. So we thought that it was a good test, but the idea is to say that it's something. Well, we learned that the north actually there's one cluster at the south and one cluster at the north here, and it's something that was kind of expected. We don't see relationship between stations that are very far away. And we don't put this geographic information into the model. So it was like the first way of validating the algorithm. It's not proper validation. And we did another experiment on brain data. It's data that was we had two types of subjects, some healthy subjects and some people having attention deficit, you know, people that are unable to concentrate. And the idea is that we use some fMRI data that is recorded on here 39 different areas, and we try to learn a graph for different subjects and to see whether or not we could see a difference between what happened for an healthy subject and for ADHD subject. And what we observe here in what we learned is actually something that is documented in the literature, is the fact that the connection here between for the healthy subject are more structure and are more communication between the left and the right, which is apparently something that is supposed to it was a resting state task. And here you can see that for the patient with attention deficit, you can see here that the structure is quite different. We wanted to go a bit further, and we decided to do some classification on the graph. So we used all the graph for the LC and for the ADHD, and we used the agency matrix, and we computed some basic classification, and we obtained this score. What was interesting for us is that when we compare that with building a standard correlation graph between the different signals and applying the same task, we obtained better performances by learning proper graph with the different constraints that we put. So we said that, okay, it's still better than doing a simple correlation graph. For the interpolation of missing sample, the idea is the same. We will take one multivariate time series that will be seen as a collection of different graph signals. And we assume that for some sample position and some dimension, the data is unknown. So we will have a set of unknown sample and a set of known sample here. We have the graph, and the idea is to interpolate and to reconstruct the missing data from the input graph signals. So the problem that we are solving here is actually something that does not, well, the smoothness does not appear in this problem. The idea is that we will seek for a linear reconstruction of the missing data from the available data. So we'll use here a linear structural equation model, which is a simple model, but here the graph does not appear. So we can learn here the different weights A and B to reconstruct the data, the missing data from the known data. What we used in order to incorporate the graph knowledge is an additional term here, which is a locality term, meaning that we want that if you look at the weights that are used for reconstructing a sample, we want this weight to be large. It's always the same idea. We want this weight to be large when the dimensions are close to each other, and to be small if they are very distant. So we use here this term, which is a localization term here. You can see that it will make sure that if the distance between the two nodes that you want to use is very large, then you want the weight to be as small as possible. So this is the one that we use, and you can use several distances on the graph. There are several distances that you can define. For instance, you can use the geodesic distance on the graph that will tell you whether the two nodes are connected or not. So once again, this problem, you cannot solve it. It's not a convex problem. So we solve it with alternate minimization. There are some closed form solution for the two problems, but they are very heavy to compute. So we did a relaxed iterative method as well. We also took we have another algorithm that does denoising plus interpolation. So I'll just show you the interpolation part, but you can denoise your data as well if you want by using this method. So here you have the performances. It's a normalized root mean square error. It's like so the larger the better. So in blue you have the classic method that do not take a graph into account. Then in yellow you have all state-of-the-art methods using graph, and in orange you have the different algorithm that we introduced. So you can see that yes, the performance are better on several data sets. You have here one data set of 3D movement, which is a motion capture movement. Here we remove 20% of the sample, and here it's 50%. So it's really a lot of missing data. And here it's another one. It's a very common data set we know for people working GSP, which is a walking dog. It's a dog walking, and you have some intensities on the dog that is walking. And what was interesting here is that we saw that actually adding the graph information could help to improve the performances. It was something that was, when we started to work on GSP, there was something that was a bit intriguing, is that each time we took the algorithm from the literature, we replaced the graph that was a good graph by a random graph, and sometimes the performances are exactly the same. So you're saying, okay, maybe the graph is not good, or maybe all this GSP field it's I don't know, it's not very it's like a dream, but it doesn't work. So what we wanted to do is since we have a localization term, here, that takes into account the distance, we said, okay, we are going to change the distance. So we will have some good distance. For instance, you have the geodesic distance, which is good. And we can replace that by a distance that put 1 everywhere. So it's like you have the graph and everything is connected. So it corresponds to the fact that you don't have any information. And you try that with the distance where everything is 0. So nothing is connected. And we were very happy to see that actually the use of the graph really improves the performances. So you can see here we change the ratio of missing values. So of course, your construction error becomes greater when this ratio becomes large. But what is very nice is you can see that there's between the distances that take into account the graph and the one that do not, you see that there's a large gap. And it was something very important for us to see, okay, we're not just doing graph because we want to do graph, but the graph can actually improve the performances on this particular task. So it was something that we are very happy about. So as a conclusion for my talk, so what is nice in this framework, in the GSP framework, is that if you come, well, just like me from the signal processing communities, there's a lot of intuition that you have on your data that you will be able to find in this new domain. So you can have smoothness, band limitedness. If you look at sampling algorithm, etc., they come from bases that are actually quite similar from the one used in signal processing. What is also nice in this framework is that the graph can model kind of anything. So you can have a graph that will incorporate some knowledge. It doesn't need to be a correlation. You can put a lot of different prior, I will say, but maybe it's not the right term, into your data. And of course, there's a lot of applications, there's a lot of work now working on that for sensor network, for medical data, for etc. And it's a framework that is very versatile and that you can use for your data. And that's it.
Excellent. Thank you.
Okay. It's our great pleasure to have Stéphane Coulon, that is join us for this workshop. Stéphane is a professor at ILLS, École Technologique Supérieure. He's also associate member of ILLS, and he's an expert on multimedia, video compression and processing at last. So, please, Stéphane.
Okay, thank you for the introduction, and thank you for the organizer to invite me to this nice workshop. So today I'm going to talk about immersive video challenges and some AI solutions. So first I'm going to introduce what is immersive video. Are you mostly familiar with immersive video or not at all? No. So I have an introduction on immersive video. I'm going to present some of the challenges that we face and some AI solutions that exist and some that can be developed to go further because the applications are evolving actually. Maybe very quickly, because we're here in visit to start collaborations, and I'm from École de Technologie Supérieure, and I know that many of you don't even know ETS, while probably you know McGill. And so ETS is located downtown Montreal. It has over 11,000 students and nearly a third are graduate level. 60% of our research activities are performed in collaboration with industry. We're the second largest engineering school in Canada. So usually people don't know that, and nearly 260 professors and lecturers. So it's quite a big engineering school. Who I am, my research interests are video processing in general and communication. I have quite a significant industrial background. I've worked 2 years for Bell Northern Research, which became Nortel I also worked at the Nokia Research Center in Dallas. And since 2004, I'm at ETS as a professor in the software and IT department. I continue to collaborate heavily with industries, companies like Summitech, Nokia, Octasic, Grass Valley, Ventrix. I was chairholder of the Ventrix Industrial Chair in video optimization from 2009 to 2019, and since 2001, I'm a co-chair of the Summitech Industrial Research Chair in interactive immersive video, the topic of today. So what's immersive video? There are several types of experience involved. You know about augmented reality, virtual reality, mixed reality. They all have a different purpose, provide different experience, different capabilities, and they can involve multiple modalities like visual, sound, pressure, even smell. Today I'm going to concentrate on 360-degree video, which we call 3D of freedom, because the freedom that we have is move the head in all the possible direction. But we want to move that to 6 degrees of freedom, where on top of moving the head, you can actually move your body inside the whole environment. So what are the applications? Virtual tourism, so visiting a museum or historical sites while staying at home. It can be useful for people with handicaps or elderly people. Many reasons for saving money because it's too expensive to travel. So many reasons why you want to do that. Participation in a live concert from home. Maybe there's not enough tickets for a certain artist, too expensive. Again, you can watch from home. Real estate, virtual visits of homes. Virtual shopping as well. This is actually one application that our industrial partner is deploying. So what's the processing chain? So what happens in 360 video? So first you have to capture the environment, and we see here this weird camera. Basically, it's multiple cameras. You have cameras looking at all the possible directions to cover the 360 view, and you end up with a bunch of views that are disconnected, and you need to connect them. So you're going to stitch the content, and you're going to make a projection to eventually make it a flat image, flat video, so that after that you can encode the information using traditional encoders. So this is for 360. This is actually evolving when we have 6 degrees of freedom. We're not necessarily going to use those codecs. We will use other technologies to compress. Then there's the transmission. And then you receive the content, you decompress it, you render it, and you have the view from all the angles. But when you're there, you're going to render the viewport, basically what the person wants to see at a certain time. And then you're going to display it. And as we'll see, most probably you have to provide the head orientation if you want to do the rendering properly. So where AI is useful in all this chain? Actually, pretty much everywhere. In the stitching, it's not so easy to take all those views and stitch them together, connect them together into one single image. There's going to be problems with calibration of the cameras, many problems, compression. And I'm going to show one example where we use AI to drive existing the parameters of existing videos, but we can think about other technologies, like Joseph is going to talk about point cloud in a few minutes. There's also neural compression. So this is very active area. At the reception, if the content has been damaged during the transmission, you may use AI to repair what has been damaged, because you don't have time to retransmit and get the information, because As we'll see, delay is a key problem in those applications, and you have to keep it very small. Head orientation. You want to render where the person is looking, but if you're over a network and the content come remotely, you will have to know not only here when you do the rendering, you need the orientation of the head, but if you're having a real-time application, this head orientation needs to be known by the server to send you the proper information if you're not sending the whole 360 view, but just where the person is looking at to save bandwidth, as we'll see a bit later. Maybe projections, transmission. If you can predict what's going to be the network condition, you can decide what to send. So basically, there's a lot of areas of this processing chain that AI can contribute to improve the quality or improve the user experience. Again, just to make sure you understand the 360 video, you have the whole field of view that is modeled by a sphere. And so if we model what's happening, we have the whole sphere, we have to make it flat. So it's a bit like when you have a globe and you want to make a map, you have all kinds of distortions that happen, like the poles are distorted. But you end up with a rectangular image. And out of that, at a certain moment, you're not looking at the whole 360 view. You're looking just at a certain viewport, a certain region. Our field of view is limited. I cannot see behind my head. So this is going to be really important when we want to save bandwidth or information. Okay, so this is a typical example of the YouTube VR channel. This is what they typically send. They will send you have all the information to reconstruct the 360 view. This application doesn't know where the person is looking at, so it sends you the whole image. And the player, either you control it with a mouse, but ideally you would have a head-mounted display, and as you turn your head, it will give you the view that that corresponds to the orientation of the head. So the stitching is a really important part. It can be done two ways, either offline, like this is an example of the 360 camera that we have. It comes with a stitcher, and this is one example of one of the camera, what it provides. And you have to fill in a bunch of parameters. And after a few seconds, it will create the stitched view. Why I'm talking about that? It's because this one is offline, but if you want to stream video in real time, you'll have to do it online in real time, and then complexity of the processing will become an important issue. So it's a compromise between quality and the processing it will require. So now that we know what 360 is, what are the challenges? So the first challenge is that it requires a lot of bit rate. For instance, let's say we take the YouTube channel that compresses with 4K. ERP is this map view that I showed you, equi-rectangular projection. So as a human, you have your field of view is about a fifth of that sphere, especially with the head-mounted display that are limited in terms of degree. So you cannot see the whole 360. So it's a big waste of information. You send the whole view, and you're looking a fifth of it. And you may think 4K, that's pretty good quality. Yeah, you have 4K for the video, but you're looking at a very small part of that. So this small part is very low quality, actually. So this example is showing a HD HD image. But if I look at the viewport in my head-mounted display, the quality is not so good after all, because again, the resolution becomes very small. So if you want to have a good immersive experience, you have to increase the resolution. You have to go to 8K or 12K. And then you can, and the other thing is that it needs to be at high frame rate, because otherwise the experience is not very fluid. So you need to compress heavily. I'm not talking about non-compressed video, because non-compressed video, it can take tens of gigabits per second. But if you compress, still a 4K image takes 45 to 60 megabits per second. It can go to, this is not 4K. That's probably the 8 or 12K. 8 or 12K is this bit rate. So it's quite high bit rate, and it can increase by, don't double it, but close to, if you want to have stereoscopic experience. So you need this kind of bit rate for each of the two eyes if you want to have depth perception. So that's quite a big bit rate. So what are the solutions for that if we want to reduce the bit rate? We have to compress efficiently, again, with better algorithm, maybe AI. But if you do that, it comes at the price of computational complexity, latency, 8K, 12K real-time compression. Not every device can do that. It's actually a challenge. Also, what we can do is send just the information that is in the field of view. Why send the whole sphere if we just look at 1/5 of it? Let's send 1/5 of the information. But then we need to know where the head is positioned. And and to know that, there's going to be a delay to transmit that information. And then delay becomes another issue. So this is what people are doing. They take the 360 video, they break it into tiles. And the user can select the tiles that is needed to view what it needs to view. So basically, you will get high quality tiles in the viewport, and maybe medium quality a bit outside, and very low quality still in the rest of the. You cannot not send those tiles, because if somebody turns his head very quickly, he doesn't want to see darkness. He wants to see maybe low resolution, low quality, and by the time his brain will make sense of the content, you will have sent the high quality content, because you know the position of the head. So this is typically what people do, but then you have the problem of latency. You need a latency of 20 milliseconds or less. Otherwise, you're going to be cyber sick. Like if you move your head and the picture doesn't follow your head, you're going to be sick in no time. When there's no correspondence between your inner ear and what you see, your body thinks you've been poisoned, and it will react accordingly. So this is important, because if we use tiling, we need to know the head position at every moment. And if there's delay, we won't know that. So where AI comes in is that we will have to be able to predict the head position. So we can look from the content and from the current head position, where the head position is likely to be in the next couple of milliseconds, seconds even. Then there's also the issue of quality. Of course, if you do compression because you want to save bitrate, then it's going to impact the quality. And it's always the same thing. It's a compromise between the bitrate, the quality, and the computational complexity. So how do we evaluate the quality? Many reliable quality metrics have been developed for standard video, but it's still lacking for immersive video content, 360 video content. So this is quite an active research area. There could be also transmission errors. We don't have time for transmissions. We have to deal with what we have and repair the video in real time. So I talk about the problems, and there's many of them. So many opportunities for collaboration. What we've done so far, so in the first phase, I explained what was immersive video, some of the challenges and problems. And now I'm going to talk about some of the solutions, but there's many more problems remaining and solutions to be developed. And interestingly, those problems that I'm addressing, actually, for each of the problems, it's a different AI solution. For this problem of predicting where the user is going to look, so basically viewport prediction for tile-based video coding, our solution was based on LSTM. Other problems, we have other solutions. So basically, we have a solution to predict where the user is going to look using LSTM. So of course, we take the user's viewpoint position history as a sequence, and then we predict the future. And what we want to do is we want to have this prediction not for a given time, but for any time that we want, depending on how long we think the delay is going to be and for how far in time we have to predict. So we don't want to predict for half a second. We want to predict for any time between now and a couple of seconds. And of course, the accuracy will change depending on how far in time we want to predict. Yeah, so ranging from the next one up to n frames in the future. So architecture of our LSTM. We do some prediction adjustment. Yeah, using LSTM does the job. And another thing that we do is we use some users. Basically, there are some users in this application that is meant to stream to many people. Some users have very low delay and some have high delay. And we use the information of the head from those who are connected with low delay to help those who have longer delays in the prediction. And it helps quite a lot, the prediction. So just very quickly, we weight our prediction between our LSTM prediction and what the guide users are providing us as far information. The guide users are the ones that have very low delay. And depending on a confidence factor, we can put more weight on one or the other of the prediction. Another thing that we do is, since we know the position of the head, or we predict the position of the head, we're going to send tiles at high quality, at full bit rate. And we'll have tiles at medium and low quality around the viewport and outside the viewport. And that will help to save a lot the bit rate. I'm going to skip those details, but we can see that with our method, without the guide users, we can predict with nearly 88% the position of the high quality tiles where they should be. If we look at high quality and medium quality, it's nearly 99%. And if we have those guide users, then it increases the accuracy of placing at the right place the high quality tiles. So it works pretty well. If we look at the error, of course, in all the methods, the error will increase with the time for how long we want to predict the time. Like actually 3 seconds is pretty aggressive. Usually systems don't need to have such a high time to look ahead. But yeah, we can see that method with the guided users have lower prediction errors than the LSTM, and also much lower than the other methods. Yeah, so I'm going to switch to another problem, which is CU size decision for HEVC. So basically, HEVC is a video codec that is widely used. And a problem with coding is actually you do two things. You decide how big the blocks need to be for the coding, and also you decide what coding mode you should use. And typically, the codecs, they will do some kind of exhaustive search. They will try big blocks, smaller blocks, and so on. And it will take a lot of CPU to do that. So we can use AI to speed up this kind of process. So with this type of solution, we're using deep reinforcement learning. It's so I'm going to skip those details, but yeah, so we have reinforcement learning that we apply, and we train the codec with many sequences, and at the end we end up having an encoder that can be 50% less complex in terms of computations, while providing a bit rate for the same quality that is about 1% larger. So you have an inefficiency of 1%, but you save 50% in terms of compression, in terms of computational complexity. So we can, in the future, continue to have this type of approach where we use AI to replace exhaustive operations or heuristic operations by something that is more efficient. So basically, it's still using the same codec that we've developed that are quite efficient, but to make them less complex in terms of complexity, because in reality, we have a lot of codec. We have AVC, HEVC, even VVC now, but in reality, when they're deployed, they don't use the full power of the syntax. They're not as efficient as they theoretically could be. And the reason for that is that operators don't want to spend the effort in terms of complexity to achieve the best performance. So these kind of things can improve the quality of the existing technology. And of course, the other approach would be to use different technologies for that. I'm comparing with other methods. I mentioned other methods. Yeah, we can use autoencoders, point cloud compressions. If the content is point cloud, there's many options. Another application is to try to reconstruct damaged video. Let's say that during the transmission you have errors that were bits that your video packet has errors in the bits, and you want to use, let's say, a list decoding solution. So you have information about which bits are less reliable. So you may try to flip those bits in an attempt to correct your packet. And then you come up with candidates, corrected candidate packets, but you don't know which one is the one that you managed to, that is the corrected one. So you can use a neural net to look at those decoded videos, assuming that they don't crash the decoder. And those that don't crash the decoder, you look at them visually with a CNN, let's say. And you can rank them in terms of quality to select the one that has the best one. So this is an example. If you corrupt the video packet by flipping bits, you have all those versions, and you don't know which one is the corrected one. Of course, as a human, it's easy to see that this one is the one that I've repaired. But if you want to teach a machine to do that, then you have to train it. And CNN is a good tool for that. So you can see the visual problems. In that case, it was easy. Still here, it's easy to see where the problems here are. In the other videos, it's not so obvious. Like here, I don't know if people know this, but it's less obvious what happened to the video. But still, your system needs to be able to recognize which one is the good one. And if it makes a mistake, I would forgive the system to make a mistake between those two pictures, but I would not be forced. I would not accept that the system selects this one as a corrected version, especially that in video, if there's an error, it will propagate with time. So, typical processing chain where you do the encoding, the transmission over noisy channel. You have your list decoding where you identify all your candidates, those that are possibly corrected versions of the video. You decode, and then you will train the system with the supervised method. Basically, when you train, you have the original image, you have your damaged image, and you can know, you can find a metric to guide the system to adapt. And after, when you're in the inference mode, you do the same thing, but of course you don't have the supervision, you let it do its job. So basically you have all the versions of the image, you give them a perceptual score, you find the one that has the best quality and you select it. And yeah, for that we needed to have a database of damaged video. A lot of the visual quality metrics, they have distortions, but those distortions are uniformly distributed, like noise, like coding. This type of distortion is different, so we have to build a new database. Yeah. And after the system is deployed, this is an example of how it operates. It gives different scores for different images, and then it realized this one has a better score. Probably not so far from this one. This one has a little bit of distortion here. Again, I'm not so unhappy if it selects that, but of course I prefer that this is the selected video. And now we decide we have some kind of map of quality. And right now we're just doing an averaging of the quality, but eventually we will do something smarter and look at some correlation between pixels, because between blocks, because usually when the video is damaged, there's going to be not just one block that will be damaged, but a bunch of blocks in that region that will be damaged. Right now for intra-frame, it's working pretty well. For inter-frame, it's not as good. We're still working on it. Again, I could explain why it's more difficult to work with inter-frame. One reason is that there's not a lot of information in inter-frame. You just send differences, and if that packet is damaged, often it doesn't have a big impact on the visual quality.
Excuse me, how compute the accuracy there? The accuracy is a normalized error?
So we have all the choices of selecting the fixed one versus the non-fixed one. Mm-hmm. And it's the percentage of the time that we select the fixed one, the corrected one.
Okay, okay.
So 96% of the time we get the corrected one. But yes, we want that. If it's
there's always one correct one. That was my point. Yeah,
there's just one correct one.
Okay.
And
you count if you're selecting the right one or something else, which is a mistake.
Yes. But we have to go further because if you make a mistake, it's not the same thing if you make
as he was showing
this
before.
mistake or if you make this mistake.
So
So we have to check
so
that.
this is too hard, maybe as an error, no?
So this is why we look at the average quality that the system provides. So we have higher PSNR compared to other methods.
Yeah, but maybe a soft measure of accuracy will make a bit more sense, no? Something that ponderate, okay, you're wrong, but how wrong you are. That's because here you have like two different measures.
Two different measures. If we could find a measure that would embed both, it would be nice. And another application is no reference visual quality assessment or video quality assessment. This is work we did with Christian. So basically, most of the no reference video quality metrics, they are built for one type of distortion. Typically, people, they separate or categorize the distortion into authentic distortion, those that are created by users when they film something like blurring, problems with color, focus problems. And they have traditional errors that are noise, compression, distortion. And methods typically are good for one or the other. And we developed a method that is actually good for both types of distortions. And so we use an architecture, again, CNN with glue, encoding, attention, all things that are widely used in the literature. And we end up with a metric that is good for in-capture distortions. So maybe not better, but close to being as good as those existing metrics. But what makes the difference is that they also work pretty well for traditional distortion, where we have much higher performance than would exist. And of course, the next step would be to apply that to 360 type of video, because this is for traditional video. So future work, there's a lot of future work. Viewport prediction, it's not perfect. It needs to be improved. Content compression, error concealment. There's also a new standard that is MPEG-I. It works differently from traditional video compression method, where it's using information from multiple cameras plus depth to reconstruct that actually don't exist. Like if you want to move in an environment, you're not going to have the view of all the position in your environment. You will have a few cameras positioned in some key places in the room, and then you will interpolate the view, and you will use depth to do that. Point clouds coding, stitching, as I mentioned, is a problem. I just mentioned depth estimation and view import interpolation and visual quality assessment for immersive video. So these are many of the areas that we can work on. This is a view of our lab. Like we have a 3D conferencing room. We have a 3D 360 capture and visualization space. We have a control and processing room. And this is actually how it looks like. I think the picture makes it smaller than it actually is. It's quite large. And we have some 8K 3D 360 cameras that capture in HDR. And we have a few of them. There's one here, there's one here. We have 3 of them. We have Pimax Vision 8K Plus. So we have a lot of space to perform our research. And yeah, this is what I was explaining when we talk about 6 degrees of freedom. You have cameras and you interpolate the views. And we look at just taking the views from the cameras and estimating the depth using the traditional MPEG tool. And it didn't perform as well as we expected. Like this is a poster. We would have expected that the depth would be the same everywhere on the poster as it should, but we ran into problems. So is it problems with calibrating the cameras? These are the kind of things to look into. So a lot of tools, they look well on provided data, but when you run that in the real world, then you have to make some adaptation. Another problem, like this is the footage that we captured with one of those cameras, and this is the stitching that it did. So, and it was with the offline tool. So that creates some problems to use that content professionally. Yeah, so in conclusion, immersive video is a fast-growing technology with many applications. We have a lot of challenges in terms of low latency, high bit rate, transmission errors, high computational complexity. Sometimes we need very powerful GPUs, visual quality, and AI can help in all those problems. Thank you very much for your attention.
The next talk is going to be a different topic. It's because it was a time issue, and we would like to have Leurs to accept the invitation, but she has a constraint, so that's what we managed to do. So we're happy to have you here.
Thanks.
Leurs is she's a professor at the NCA, if I'm not mistaken, associated with Lycée. And her research interests include semantic and tell at large. So we hope that, yes, great. So this was much more entangled with another talk that we had yesterday, so that was the original idea. But anyway, it's good that we can see this here.
I wasn't in Paris today, so I explained the method before, sorry. So thank you for the introduction. I'm going to talk about the environmental impacts of AI. I'm doing my research at the Lycée lab, and my research topic is actually, I worked for more than 10 years in NLP, but now I'm focusing on the environmental impacts of information and communication technologies. And since I worked for so long in NLP, I focus mostly on AI, but not exclusively. So first of all, I want to say that I'm going to talk about artificial intelligence in all my talk, but it's actually specifically the deep learning methods that I will focus on because, well, as you know, they require a lot of data and a lot of computing, so that poses specific environmental problems. There has been work on the environmental impacts of computer science and digital systems for some 15 years, but there has been a focus on AI for a few years only, specifically since the paper from MS Rebel and colleagues on natural language processing models 4 years ago. So in this paper, they studied a variety of state-of-the-art NLP models, and I think there were 4 types of models, if I remember correctly, and they performed software-based energy measurement. So that means that they measured the additional energy consumption due to the execution of the programs, and specifically here, the training of the models. So their results were that the training took from 12 hours for the smallest model to several weeks. And the emissions in terms of carbon footprint were between 18 kilograms of CO2 equivalent and 284 tons of CO2 equivalent. So there's a huge difference between the small model and a larger one, as we will also see in other experiments. And the most used model at the time was like half a ton of CO2 equivalent. And I just gave equivalence just to give you an idea of how much it is. It's, for example, a one-way flight from Paris to Hong Kong, or like more than 2,000 kilometers by car. And I'm sorry, I'm talking kilograms and kilometers. I hope it's okay. And also to give an idea of the cost, the environmental cost of all of this, the sum of the experiments for the training of all these models in terms of GPU time was like training using 60 GPUs for during 6 months. So this had a huge impact. You probably know this paper, but it had a huge impact on the NLP community and not more largely on the AI community, because it was one of the first estimations of the carbon footprint of models. And after this paper, and in parallel actually to this paper, there was also works on several tools for carbon footprint estimation of AI models. So this is one of them, but there are also Python packages such as Code Carbon or others. And so this is an example of an online tool that's called Green Algorithms. So it performs an estimation of the carbon footprint of the execution of a program. And it's based, for example, on it's based on several factors like the runtime, the number of cores that you use, the memory, the type of cores, etc., etc. And it gives you both the energy that was used and the carbon footprint, the equivalent carbon footprint, by using the energy intensity of the location where you performed your experiments. And it also gives you a very long, I don't know, latest equivalence to give you an idea of the cost. And also there were several experiments at the time about the main factors that influence the carbon footprint of training models. So of course the type of model, the quantity of data, and also the energy efficiency of the data center, which is usually modeled by the PUE factor that you can, for example, give here for your specific location, well, infrastructure, and also the carbon intensity of the electricity. And that's one of the experiments that was done, for example, 3 years ago. This is the carbon footprint for training several, different models, but at different locations. So, for example, if you look at France, that has a low carbon electricity, well, with other problems, but it's low carbon. You can see that the carbon footprint associated is around, I don't know, like 100 grams of CO2 equivalent. And for example, if you consider Poland that has a very high carbon electricity, you can see that it's like 10 times the carbon footprint of training the same model in France. So as you can see, the location of the infrastructure that you're using has a huge impact on the carbon footprint. There was also a proposal of working on green AI. So the idea was that, up to this point, it was mostly red AI that was worked on. So what's called red AI here is the fact to try to improve the accuracy rather than the efficiency, that is not considering the resources that you have to use to get this accuracy. As you know, most of the state-of-the-art paper use massive computational power and do not take this into account. So this paper stated that it is, of course, very valuable because it contributes to knowing the boundaries of AI. So what can AI bring? But it also says, the authors also say that to allow for more equitable comparisons, there should be a few things that should be, there are a few things that should be done differently in the papers, even in Red AI. For example, reporting training curves so that you can compare the performance with the same resources. And they also said that the AI community more largely should recognize more green AI work. And they define green AI as AI that takes into account the resources that are used for doing the experiment. So the idea would be to encourage results that enable a reduction in the resources spent to do the experiment. In the papers that I wanted to present here, there are also several papers that studied, for example, the how to balance the precision, so the accuracy of your results versus the carbon footprint. So this is a paper from 2 years ago on the speech recognition. The two graphs are from two different data sets. This one being much more difficult than this one. So this is the error rate. So, well, it's the lower it is, the better. So, and it's so you can see the curves during the time of training. And the authors wanted to see what the difference in the accuracy would be if they had stopped the training at half the carbon footprint. So for this data set, you see that the difference is of around 3%. So, okay, this is quite a lot for this kind of model. 3% has a huge difference in the results. But for this data set, for example, you only have 0.3% or something like that. And well, what they're trying that I try in this paper to raise the question: do we really have to go to the state of the art, even though it requires a huge carbon footprint? Well, huge, much higher anyway. Just doing this specific experiment is not such a high does not have such a high carbon footprint. And to give you just an overview of the kind of work that was done about this, and then I will focus on what is done at Listen. There was also, I also wanted to mention this work from Facebook. So for now, we have only seen work that measured the energy consumption, well, actually even more precisely, the additional energy consumption of the servers that compute the experiments. But actually, you can also, if you use a correct environmental evaluation, you should also take into account the life cycle of the equipment that run the experiment, because, well, you have partly bought them to run your experiment, maybe in a little, very, very little part, but it should be taken into account. So in this paper, they measured the production carbon footprint also, so from the raw material extraction, manufacturing, and distribution of the equipment. And they compared it to the carbon footprint due to the use of this equipment. So that is due to the energy consumption when the equipment is used. And as you can see, the production part is not negligible. It's sometimes like, well, it's in the same order of magnitude anyway, but maybe like up to half of the total carbon footprint. This is, well, this has also been done for other kinds of parameters, for example, in a computing center in Grenoble. And well, they did a very extensive life cycle assessment of of 1 hour of computation. But if you focus specifically on the carbon footprint due to the servers, 40% is due to the production part and 60% to the use part. So that means that when you only consider the use part, you forget a lot of the carbon footprint. And in the same paper, they also try to see the difference of common footprint between the training and the inference. So inference is in black here, and the rest is training, with both online and online, but it's training. And you can see that the carbon footprint of inference can be as high as the carbon footprint of training. Well, it depends on the kind of models, because, for example, for machine translation model, it's not trained very often, so the carbon footprint of the training is lower, and for the information retrieval models, for example, it's trained much more often to take into account the latest research, and so the carbon footprint of the training is much higher. And the last work that I wanted to mention is work from 2 years ago that tried, well, it's much more than just this figure, but I wanted to show this figure because for in what I've shown up to now, it's only been about the compute-related impacts, that is the impacts due to the life cycle of the equipment on which the AI is executed. But AI also have second and what is called second and third order impacts, that is impacts on other sectors. And for example, if you think you're going to use AI for, I don't know, smart buildings or smart transports, etc., you're considering second order impacts. That means you think that AI will help optimize, for example, the energy consumption in the building. And these third and second and third order impacts are almost never computed or assessed. So just to focus on what is done at Listen. Okay. For the research about this has been focused on three axes. So the first one is carbon footprint measurement for NLP tasks. The second one is life cycle assessment of AI system, and the last one is a bit specific. It's more like practical guides, so I will not spend a lot of time on this. So the first kind of research is about carbon footprint measurement. So I wanted to mention a paper from 2 years ago that we did with my colleagues Yasmin Banou, Aurélie Nevon, and Sarah Ganet. So we studied 6 different carbon footprint measurement tools that were available at the time. Well, I'm using the past tense because it has changed quite a lot since then. And we focused on 2 NLP tasks, actually just one, name entity recognition, but with very different settings, on open domain or medical domain, and with embedded entities or not. Well, it was quite different tasks. And we also compared 2 settings, whether we're on a local server or a dedicated AI infrastructure, which changes mostly the energy efficiency and the kind of hardware that is used. And the results are that we found were that the tools gave quite different results due to difference in energy intensities used, to some of the hardware models that were lacking, and the fact that some tools measure the actual energy consumption, whether others just estimate according to the parameters that you give it. And I wanted to say that, okay, this is a paper, it only has it was only 2 years ago, but it has changed a lot since then. So there are new experiments by Mathilde J, who's doing her PhD in Lyon, who did the same kind of experiments, but with newer tools and newer settings, etc. And another work is from Aurélie Catan and Christophe Servan and others, but that try to assess the carbon footprint of fine-tuning and inference of several French and multilingual models, so transformer-based and pre-trained models, and they tried to see whether there is a difference. The performance is quite the same in terms of accuracy and error rate, but they tried to also assess the carbon footprint. And what they measured was that the compact models, such as this one, had comparable results in terms of accuracy to bigger models, such as these ones, but they had a much lower carbon footprint than the big transformer models. Another work is the work that we did with Sacha Lucioni and Sylvain Viguier on the Bloom language model. So we tried to assess the carbon footprint of training and for the inference also of this big language model that was trained last year. And for that, we first had to create a methodology for estimating the carbon footprint of the Jersey infrastructure on which the model was trained. And then we estimated the carbon footprint for training the model and including something that is generally not taken into account, that's the idle consumption, because as some of you may know, a server has a very high idle consumption. That is when it's on, but just not executing any job. And so part of this consumption is also due to the fact that you're executing your program, otherwise it would be shut down. So we took this into account, and we also took the embodied emissions, that is the emissions from the manufacturing of the equipment. And we showed that the total carbon footprint was around 50 tons of CO2 equivalents for the training of the model. And we also tried to assess the carbon footprint of inference. And then I will mention another work on life cycle assessment of AI system. That was published, I think it was last year, but it's okay. And the idea was to try to assess the environmental impacts of an AI system and to take into account at least the life cycle assessment. So life cycle means that you take into account both the production, the use, and the end of life, and with several environmental criteria. And we also try to see how in AI for green systems, these benefits were assessed. So to do that, we took the paper from David Warnick and other colleagues tackling climate change with machine learning. And we studied some of the reference of this paper. So this paper tries to see how climate change can, how machine learning can help address climate change, for example, in these farms and forest domain, and for example, by using precision agriculture or by managing the forest fires. And we studied more than 50 of the references that were given in this paper. And so you can see the domains on the left. And we had several categories to see what kind of environmental benefits, how they were computed. So you can see that nearly half of the papers did not mention at all an environmental gain. And at best, they evaluated the energy gain, but without taking the AI program into account. And we had other categories, but we could not choose them because none of the papers fell into these categories. And just to finish, my time is already up, so I'm just going to mention two reports that we wrote. So one with Sacha Lucioni again about what you can do to reduce your carbon footprint as an ML or AI practitioner, and another one about the environmental assessment of projects involving AI methods. So we wrote a document to help people assess the impact of such projects, taking into account all the kind of impacts that I mentioned before. And just to conclude, I wanted to mention the current and future work. So we are currently working on integrating consequential life cycle assessments. When I mean consequential, it's it's attributional that I wanted to write, sorry. That means take into account the idle consumption life cycle and the different impact indicators that I mentioned before into the existing impact estimation tools, such as green algorithms that I've shown before. And we're also evaluating the potential benefits of AI in specific sectors. So for example, there's a work with Quant to see how the search engine carbon footprint would be impacted if by using large language models. And also we're trying to assess the benefits of AI in two specific domains that are agriculture and health. And I'm also working with a PhD student to improve the end-of-life impact estimations, because you may have noticed that even though I mentioned that the end-of-life is in the life cycle, should be in the life cycle assessment, I did not give any estimation about that, because for the moment we don't have any data about that. Thank you.
Thank you. Giuseppe is a research scientist from ILLS, working here at the ILLS, laboratoire des signaux et systèmes. And he has been working on multimedia video compression and signal processing for quite a while now. We're happy to have you here.
Thanks, Paolo, for having me here. So yeah, we go back to our video consumption. So indeed, this nowadays is estimated to be 76% of traffic, internet traffic is video streaming. So indeed, we consume a lot. Okay, so today I'm basically following up a bit the talk of Stéphane. So this is a bit complementary to that. So there was before a question about 6 degrees of freedom. I think here you can have some answer, I hope.
It's the way down.
Okay, yeah.
Very interesting.
Okay, so we already talked about immersion. Just to refresh what immersion means. So this is a definition by Marvin Minsky in the 1980s. So the immersion means basically the feeling being physically present in a remote location. Okay, so it's not a new concept that as you see has been there have been a lot of science fiction movies, and it has been taught for a while, but it's only recently that we start really to have the first application of this kind of immersion. In particular, here we talk about visual immersive application. Immersion can be also audio, can be all the sensorial experiences, right? So these immersive technologies could be actually useful for a number of applications that go from collaborative working, telemedicine, remote surgery, storytelling, and in general, this is one of the basic building blocks for the metaverse, as you want to call it. So this is something that, in my opinion, is going to be the future of our visual communication in the next years. And indeed, there are many ways to implement immersive video, many technologies. So we saw before. So we saw before 360 video that Stéphane presented very well, so I will not be back to that. We have also other technology that go beyond the conventional 2D displays that we're used to. So for example, we have light fields. So this is one of the formats. And today what I'm going to talk about is volumetric video, which is a big family of methods that enable applications like augmented and virtual reality. So volumetric video has the characteristics to provide the 6 degrees of freedoms that Stéphane was mentioning before. So the possibility to basically move around objects as you were physically in the scene. So they are kind of very close to the definition of immersion and telepresence that I mentioned before. So these are two examples of augmented reality here and virtual reality. So the difference basically is that in augmented reality, you have some object that is in the scene, in the real scene. Virtual reality is totally virtual. And in fact, you have a full continuum of options between the real reality and the virtual reality. This is, maybe some of you know the Milgram continuum. It's called Milgram continuum. And nowadays we use in general the term of extended reality to say that we don't have just the reality that we perceive with our physical senses, but we can have something more. And so this AR and VR are just two points in this continuum. So for volumetric representation, we have also we can have different options, but essentially the two formats that are mainly used nowadays are either point clouds, 3D point clouds, or 3D meshes. And they actually cover different kinds of requirements and applications. So if you're more around acquisition of content, then you tend to use more like point clouds, which are essentially a set of points in the 3D space without any specific order, which are characterized by the geometric position in the space, so basically X, Y, Z coordinates, and some attributes like the color of the point, the reflectance, the normals, and so on. So this is something that you directly get, you can directly get from a sensor. And then you have 3D meshes, which typically are rendered through some rendering process, shading. So basically, these are like point clouds, but on top of them, you have some connection between points, typically in the forms of triangles. And this kind of content is something that is also quite traditional and has been done for decades in computer graphics. And it's more close to rendering because having this connectivity on the surface enables you to make a number of shading operations on that. So this is again a matter of choices, but maybe So again, these things exist, been existing for a while, in particular the mesh. What's the difference maybe in the past few years is that the acquisition of point clouds nowadays it's become very simple, let's say, and very cheap as well. So you can buy the device for a few $100s and get very good 3D reconstruction of a scene under in the form of point clouds, and especially for communication application where you want to have low delay, low latency communication. You don't have always the time to reconstruct meshes or to make rendering, so you prefer to directly transmit code and transmit point clouds. So that's why for the rest of the talk, I will focus on point clouds as immersive video format. So when you look at typical point cloud, like point cloud video like this, so this looks like a 3D video, but in fact it is, the signal here, it's really 3D points. So this kind of video, it's huge if you don't do any compression. This would basically saturate the bandwidth of 5G very quickly. And so that's why there have been several efforts to design and implement efficient compression techniques for point clouds. So in particular, the Moving Picture Expert Group, MPEG, and recently also JPEG, which is another standardization group, they have been starting to produce new standards for this kind of content. In particular, we will see MPEG has done two standards. But also, more recently, we started to have some learning-based approaches for coding point clouds. So this is a bit following up also what happened for the case of 2D images and videos, where we have also this kind of AI-based techniques that have been developed. And in the case of point clouds, this has been also becoming popular. And just to give you a timeline of point cloud standardization and the activities that have been done. So basically, this has been going on for now 7-8 years. And as I said, the main motivation was the fact that we started to have a lot of this data. So when MPEG started to standardize something, it's because there is a demand, typically there is need. So basically, you have a lot of data. And so this led to the development of two different standards that were targeting different application scenarios. So one of them, BPCC, it's video-based point cloud coding, and it's based on a principle of essentially transforming your 3D point cloud into a 2D video. And so the idea behind this is that we are very good in compressing video because this has been done for 40 years. And so this could leverage all the technologies that we already have. But I also developed a geometry-based point cloud coding, and this is, I think, the most interesting from a research point of view, because there was basically almost nothing. When they started, there was essentially the octree based coding was the baseline, which was quite simple. And the other advantage of GPCC is that this is very general. You can apply to point clouds like the one I showed before. It is dense, but it can also target more sparse point clouds, any kind of point cloud content. And what's interesting as well is that since last year, basically in MPEG, they started a new activity, a new ad hoc group, as it's called there, about AI-based coding of point clouds. Okay, so now, I think in September this year, they're gonna publish the call for proposal for learning-based standards for point cloud compression. Okay, so now let's go more into that, into AI-based point cloud coding. Hope that the introduction was clear enough. And so the basic question here is, okay, we have been doing coding for many years. What's new about point clouds, right? Why this is different? And the main reason is that when you look at the coding for the traditional content, like 3D images or videos, you know, these basically are pixels that are organized over a regular grid. So each point, each pixel has a color. And, you know, we have been doing signal processing over regular structures for forever, basically. And we know very well how to filter regular signals, how to make transforms, how to make predictions, how to make everything on them. Now, when you go to point clouds, it turns out that the points there are not organized in this regular grid. They're they are sampled irregularly in the space, and the density of the point cloud is not uniform. Because space, you can have regions that are more dense, regions where you have occlusions, you don't have points. And in general, this could be very sparse, which is also not helping because we are not, you know, the tools for coding these sparse points are typically not very efficient because you don't manage to leverage the dependencies, the correlation that you have in the data. Okay, so so the first question that you ask when you want to work on learning-based point clouds is how can we filter point clouds? For example, you want to apply convolution there. How can you do convolution on point clouds? And the very basic way, the first thing that you can think about is to say, okay, like, can we try to convert this irregular point cloud into something more regular? And this is indeed what is done with voxelization. So voxelization essentially is quantization of your geometry over a 3D regular grid. So you essentially you divide your space in this grid, and then for each point, for each cell of this grid, you can define a binary signal. So if there is a point into that cell, then you have a value of 1, and if it's empty, it's 0. So you define this occupancy signal, which is binary, and with that you define your geometry. So once you do that, you can essentially apply convolutional neural networks. Just you have one more dimension, but it's like a normal CNN that you had on images. So this approach has been used for coding the geometry of point clouds in particular. So this is an architecture that this is simplified, but basically it's a basic architecture of an encoder, an autoencoder actually for point cloud compression. So as I said, it's an autoencoder because you have two parts. One is an encoding network and a decoding network. So the input here is voxelized point cloud, so it's a binary signal in 3D. And the encoding network and the coding network are neural networks that are trained end-to-end, so all together. And so the goal is to produce a latent code, which is essentially the code that is going to be quantized and entropy coded. And this is what you transmit, basically, okay? So this is the main idea. There have been a lot of course, of optimization over that, but this is the general idea. And this general idea, actually, we did some, well, probably the first to try that on the case of point clouds. So this same idea has been done also for the case of images before, of course. So this is inspired to that. But you see these results that date back to 2019, so it's now already quite old. But at the time, this was what they could do in MPEG, in the standardization. And this is what we got. So for a similar bit rate, we could get visual results that are significantly better, I would say. So this showed at the time the advantages, the potential of this kind of technique. And that's why, in fact, this also somehow stimulated this research on learning-based point cloud compression. And so, yeah, this method has been improved later, but the idea is always kind of similar. You have the same autoencoder structures, and maybe probably the thing that worked the best in practice is to use sparse convolution, which is a special way to do convolutions in which you essentially avoid. You have two advantages. One is computationally more efficient, so you can do training for a longer time, or you can use bigger filters, more filters. So this is one advantage. And the other advantage is that you avoid this kind of dilation effect, because when you have a lot of empty space, if you convolve things with zero, you get this kind of dilation, and with the sparse convolution, you don't have it. So this combined with the autoencoder structure I mentioned gives you basically state-of-the-art performance. This method is, I think, nowadays basically state-of-the-art. So to resume about voxel-based convolution, the advantages are that you can basically use convolution on your network. So it's a structure that is kind of in line with what is done also in the case of images. And it achieves state-of-the-art coding performance for dense point clouds. So if there is enough density in your point cloud, in your signal, then it works pretty well. There are still some open points to work on. So one of these is coding dynamic point clouds. If you have point clouds that vary across time, another big difference compared to traditional video is that the number of points can change from frame to frame, and also the voxels. So this is a bit tricky, and it's not yet solved. There is little work on that. And also the other problem is how to jointly code the attribute and geometry. Nowadays, the codecs for point clouds, they typically consider this separate. But the biggest problem here is, as I said, this works well for dense point clouds. But when point clouds are sparser, what does it happen? How does it work? So there, the problem is that you have something that has very few points. So when you filter point clouds, you might have a lot of empty space, and this doesn't help the learning, right? So in fact, these methods break when they are used on more sparse point clouds. So how can we solve it? And a natural way to proceed there would be to use other kinds of convolution, and in particular to consider point clouds as graphs, right? So this morning it was mentioned that graphs can be used to model point clouds. That's indeed true, but you need to construct this graph, right? Because point clouds are just set of points, you don't have connectivity. So you can construct graphs in several ways. People use typically KNN or other kind of graphs. And so the advantage of this is that you could use graph convolution, whatever kind of point cloud you use, right? Because you just need to define proper graph. It doesn't make any assumption on voxelized point cloud. Actually, you don't need voxelization. You don't need to quantize your geometry. You can just use the native coordinates and you don't care. But so the advantage is that you could use this even for LiDAR point clouds, which are another category that is very used in autonomous vehicles, for example. But then there are some problems. One of them is that, as we saw this morning, especially in graph signal processing, the hypothesis that you have a graph and then there is a signal defined over the graph that is changing, right? It's your signal. But here, when you want to code a point cloud, you change also the structure, the topology of the graph. So this is a bit less. This morning, I think there was a question about that. What happens when topology change? And you see that it's difficult. So this is one of the. Of course, you have topology simplification things used in the mesh, but the point is, what can we do with the graph convolution neural network? And this is quite open. And the other thing is there is an effect called oversmoothing in graphs. So what happens is that these methods, when applied to coding, they are not competitive actually with other approaches, because what you get is basically you lose a lot of high frequencies, and this is so far something that prevented these methods to be really competitive. So maybe one thing to look in the future here is to consider some graph generation, particular conditional graph generation for decoding point clouds for the generator in these autoencoder architectures. So so far, the structure that I described is essentially always kind of an autoencoder. So you have basically networks that are used to produce to encode your point clouds, produce an embedding that is in a latent space that is easier to code, and then you want to decode or generate your point cloud at the end. And what you transmit is this latent code. But there are also other ways to code an immersive scene. And in particular, if you look what is really needed to get immersion, you would like basically that, wherever you go in the scene, in whatever position you stay in the scene, and wherever you look at, you know what is the color and the intensity of light coming from that direction, right? So this is actually can be formalized. There is a concept, again, it's not new, it's called the planoptic function. So the planoptic function is in this case, 5-dimensional function that for each point in space, for each direction, give you the intensity of light that you perceive, right? So it turns out that, again, this exists for many years, but it's difficult to deal with this function. It's difficult to sample it, to measure. It's difficult to code it because it's high dimensional. So, but recently, what's interesting is there have been many ways to try to approximate this function, and one of them is called the neural radiance fields. So the idea here is to try to approximate this planoptic function here with a neural network, right? So if you have enough parameters, a neural network can approximate any function basically. So it can also approximate the planoptic function. And so the idea here is that what you're gonna code, so you can code all the scene through this neural network. So you no longer have a code that you need to transmit. What you're gonna transmit is the weight of your network. So basically, this network is typically overfitted to your scene, and then once you overfit the network, you just need to transmit the network. So this is quite interesting and new. It's very, very popular nowadays, NERF. And so there are also a lot of a few problems here that need to be solved. So how to compress this NERF, and also the case of dynamic NERF, it's quite difficult. So just to conclude, so this is just some summary of what we said. We saw two techniques that can be applied. So we know that for voxel-based techniques, we essentially are already quite mature in terms of what we can do. And we already state-of-the-art performance for geometry compression. For graph, I think there is potential there, but so far we are not competitive. So there is some work to be done. And then we have some open problems like dynamic point clouds, the joint coding of attributes and geometry, and this new neural scenes representation that have some potential as the next step for representing immersive scene. So I conclude on this. If you are interested, there is a book that I make some advertisement here, the book that I edited last year. And also you can find more information about learning-based point cloud compression in this paper. And if you want to contact me, this is my email address. So thanks a lot for your attention, and I'm ready to answer questions.
Sylvain, tu pourrais juste te dire s'ils sont là qui répondent. J'ai déjà essayé. All right, so the next talk is going to be given by Elie Adigi. He's associate professor to Central Supélec, also laboratoire des signaux et systèmes. He's working on online learning and bandits.
Come back to
So we're very happy to have you here. I think he's going to give a broad overview, an introduction that is in particular open to everybody in principle. So yeah, we will learn, I hope, things on this topic. Thank you.
Hi, hi everyone. Thanks a lot. Yeah, thanks a lot for the workshop. Thanks a lot for having me here. Yeah, so this talk is going to be a little special because there's no neural networks. So I guess it's the one podcast that's not going to be about, or maybe two. With no neural networks, but still, it's still machine learning, sort of in the field of AI. And so I'm going to talk to you about this special issue that I've been working on, which is, like, broadly speaking, the issue of adaptation in online learning, and also in bandits. Okay, so the setting of this talk is just going to be presentation. So, like, the whole setting is mostly going to be this online convex optimization case. So it's a framework that was introduced by Zinkiewicz in 2003, and it's just consider just a game where at every time step, you choose a parameter in a decision set W, so it's like the set of weights for your model or something, and nature is going to output some convex loss, a convex loss function, which is like measures the cost of the loss that you get for the parameter that you chose. Okay, so it's like optimization. You're trying to have, like, you're going to try to have like your loss to be as small as possible, and it's online because the losses, like this, it goes in a sequential fashion, so the losses are revealed step by step. And we always assume convexity. So that's actually the only thing that we do. Okay, and so the goal is to minimize this notion that is regret, which is the difference between the total loss that you get. Right? Yeah. So this here, it's the cumulative loss that you get throughout, like, key steps of the game. And you're going to compare yourself to, like, one model, like one choice of parameters, and you're going to try to have your regret against the best possible U, and you want this to be small. Okay, so it's exactly the same thing as saying I want my total loss to be small, but it's nice to compare it to a fixed comparator so that we can have, like, general results and like compare performance in different types of problems. And okay, what's special about this framework is that I'm not assuming anything at all about how the losses are generated. I'm not saying that they come from an IID data set in any way. Even worse than that, I can even assume that it comes from an adversary. Like, I could have an adversary that's here looking at me, knows the algorithm that I'm going to play, and picks the worst loss that could happen. And surprisingly enough, as long as we assume that the losses are convex, it's possible to get non-trivial guarantees. There is stuff that you can learn, and you can have a regret that's not too big. And that's the whole theory of online convex optimization. And okay, just to give you an example of a setting where like really this like this adversarialness could really make sense. So it's a toy example. It's nothing really practical, but still, it's a case where you can feel that IID-ness would make no sense. So it's the case of online spam filtering. So imagine that we're trying to train a linear model to filter spams. Okay, so every time you receive a mail, you say that your email is some sort of vector in RD. You have a way to say it's a bag of words. And when you're training a model, you get an email and then you read the email and you see whether it's spam or not. Again, so you have your outcome. And one way you can train your model to recognize spam is to say, okay, I'm going to compute a loss function that's going to I'm going to classify my email by a linear model, and I'm going to say, okay, if we pick WT in RD, and if WT times XT is smaller than 0, then I'm going to classify my email as spam. If it's greater than 0, I'm going to classify it as non-spam, and then I'm going to put a loss function on this after that to compare my prediction to the actual outcome that happened. So it's like similar. It's just like it's like supervised learning, except that if you're doing spam filtering, the IID assumption doesn't really make sense, right? You expect the spammers to have some sort of a behavior that's not IID. They're trying to adapt to you, and they're trying to make your life as hard as possible. And now in this context, so if you have like a convex loss function, like a regret, having a regret guarantees tells you that you can filter almost as well as the best linear model in hindsight. So you observe what happened and you look at what happened in the past and you say, okay, there was actually one best model in those, and you can filter as well as this best linear model. And so this is like one example to justify the like the adversarialness in this setting, but like OCO is much more than this particular example. Well, for one, you can cast prediction with expert advice, which is an older setting. You can cast it as an instance of OCO, and this has led to, I mean, this is basically where boosting comes from, and there's like tons of applications elsewhere. You can also cast portfolio selection, adversarial portfolio selection as and there are relationships to compression and stuff like this. Okay, you can see many more examples of problems that are special instances of online convex optimization. And also, and maybe the most obvious connection to common knowledge is that if you have an algorithm that's good for online convex optimization, you can use it for stochastic optimization or for batch optimization. And actually, like, this has had like real practical impact in the past. This Adograd algorithm, which used to be the best way to train, like the best optimizer to train neural networks, it was first introduced in the online convex optimization framework, and they put regret bounds, and it was like mostly theory. And it turns out that it had like a huge practical impact. Okay, so that's like trying to just put the the setting of online convex optimization, and what is like the main workhorse of online convex optimization. Obviously, you're trying to minimize like convex losses. You can do online gradient descent, and as anybody would expect, I guess, like the most basic algorithm you can do is gradient descent, and you have a very nice theorem. So as soon as Inkiewicz introduced the setting, he said, okay, let's do gradient descent and look at it. We have this bound. So yeah, basically it just says that, okay, online gradient descent, you can find a tuning of the time step. You fix the step size. And if you know in advance that your gradients are going to be upper bounded by G, the gradients of all the losses that you see are going to be upper bounded by G. And if you know in advance the diameter of the action set, then you can make sure that your regret with respect to the best W is going to be over the GT squared root of T. And it's not improvable. So yeah, so you can predict as well as the best, almost as well, except for this square root of T. And then if you divide by T, again, when you have your regret bounds, you divide by T here, and you say, okay, then like the average loss that you have is like 1 over square root of T away from the loss of the best action. And actually, this is not improvable. Zinkiewicz also proved this as soon as he proved his theorem. Yeah, there's nothing better you can do. You have a lower bound, like a min-max lower bound. For any algorithm that you have, it's impossible to be, like there's always going to be a loss, a series of loss function, like a sequence of loss function with the same gradients, the same norm, and it's not going to be, and it's going, the regret is going to be C times D times G times D times square root T. Okay, so that's it. There's nothing more to be said about OCO. You can, here we can say, okay, that's it. You have the best algorithm. There's nothing else to say. Well, okay, actually no. Obviously, when you have a lower bound like this, you want to look at the proof, right? And so I also have the honor of being the only one doing a proof in this workshop. So here's the proof. It's just one line. I don't want to actually do the proof. I just want to pinpoint one specific point in the proof that's interesting, which is that the way he builds the sequence of losses is he says, okay, what I'm going to do is pick linear losses uniformly at random between 2 points, basically. And always like independently all the time. So basically you're saying, okay, so, and then it's a one-liner, you can see that the expected regret is going to be of order G times D squared root of T, like because of the fluctuations of the maximum. And if the expected regret is at least this, then there is at least one sequence for which this lower bound holds, and you have your min-max lower bound. But like, okay, if you think 1 second about this, this is like not satisfying at all. Losses, okay, linear losses are not that interesting, especially it's like pure noise. There's, okay, you have your algorithms are min-max when there's absolutely nothing to learn. Okay, those lower bound holds when there's absolutely nothing to learn, and like in this case, any algorithm would get the same performance. This is completely irrelevant to practice, right? So you have to be, yeah, in theory, we always put our lower bounds, and then you have to be super aware of what a lower bound says, because, okay, online gradient descent is optimal, but still, there's a lot more to be said about this, right? And okay, so going back on the setting before, yeah, do we expect the data in this case? So your sequence of XTs and outcomes, like, do we expect them to be like in the lower bound, like pure noise with nothing to learn? Probably no, right? There's some relationship between the XT and the YTs that we're going to use, and hopefully we can get even better guarantees than the ones we get with online gradient descent, or at least a better analysis. And another point I would want to highlight in this case maybe is also like maybe adversarial is too much. Okay, maybe like, okay, adversarial it's nice for theory and everything, but for sure we don't want this to be IID, but like fully adversarial is not really realistic either. We don't expect the spammers to know all the time what algorithm we're using to classify, and so they're not reacting like immediately to what we're doing. It's probably like a slow process. It's not like the really worst sequence you could imagine. So there are limits to the setting, and like one feels that in practice, okay, you can probably do much better and try to adapt to easy data. Basically, most of the time data is not pure noise, it's not fully adversarial. It's like something in between, right? And okay, so this is like there's plenty of work in this type of they're trying to solve these types of questions. I mean, many more actually. Like the whole, like, all of online learning is about this in a way. And yeah, so this is something that I've worked on. For example, when the gradients are small, you can expect that your revenge bound, you should be able to adapt to this. Another interesting case is when you expect that the actual optimal comparator has small norm, for example, or small complexity, and you can do some sort of model selection and try to have better bounds when you know that the best comparator is a simple one. And okay, so recently at Colt last year we presented a work in which we sort of combine these two types of adaptivity. Yeah, there are also other cases, like oftentimes you have like other information than that's available, and you can use this to predict the gradients. Especially in these classification cases, you have the feature that's revealed before, and you can use this to have better, to get better bounds. Okay, and there's many more, and this is like really the point. I mean, I feel like we haven't found what exactly are the correct like assumptions that we should make on the losses, and this is where applications can really inspire theory here. It's kind of hard to know, like if you're just looking at a piece of paper and thinking hard about losses, you're not going to find like the actual form in which that their like real data is easier than these worst case cases. So at some point I want to look at applications to find some, like, to understand better which like assumptions I should be making on the data. And okay, another work that we presented in Europe last year in the same vein of questions that was I sort of teased earlier was this thing. You don't expect, in the spamming example, you don't expect the things to be completely adversarial. You don't expect them to be fully stochastic. I mean, the data is not IID, but probably maybe somewhere in between. Okay, that's arguable in this example, but there are cases in which you expect things to be like maybe stochastic, but with some corruptions, with a small amount of corruptions, for example. And in this case, like we had this paper in which we introduced this framework that interpolates between like complete adversarial and just IID, and we get the rates that interpolate between them. So, okay, like the big difference is that this G here that you get in the worst case, which is an upper bound on the true gradients, becomes the sigma here, which is actually the variance of the gradients in a way. And yeah, I think it's quite satisfying from a theory point of view, because it unifies better what is known from the for the IID case, and yeah, so that's one type of adaptation that's been interesting to me. How long do I have?
4 minutes.
Okay, sorry. And the other case, like the other part of my work, that's not online learning, it's bandits, which could be seen as a subfield on online learning in a way. And here you could see it as like a very, very similar thing as online learning. It's basically the same game, except, so you have an action space, whatever, you have a loss function from the action space to R. And this time you don't observe the full loss function, you only observe the loss at the action that you pick. Okay, so now things become a lot harder. And the regret is, let's say the same thing. Okay, you probably need to make more assumptions than that to be able to say meaningful things, but you can define things like this. And now you have this new thing that you don't observe the full loss. You have to find, you have to acquire information about the performance of every action. So you have to balance, do this constant exploration between this constant trade-off between exploration and exploitation of the information that you have. Right? You have to pick actions which are probably suboptimal, just to make sure that they are actually suboptimal. And okay, so it's basically the same thing as before, except that now there's this explore trade-off. And so you can ask the same question, right? You can ask exactly the same questions as before. Can I have this adaptation question? Is like, is it possible to have nice guarantees when the data is nicer than what is set from the lower bound? Like from when they're not really worst case. And so I want to do this without making extra assumptions. So I want to be able to do this and not lose the worst case guarantees because there are ways to make sure that I'm not doing anything too crazy. And so yeah, and I found out like this is most of my PhD work, but and yeah, we found some cases in which really like the fact that you have this new thing, this cost of exploration, and it really messes up your ability to adapt. And like we found some interesting cases, at least from a theory point of view. They're very interesting by saying like, okay, there are two cases I looked at. Like you have a continuous bandit, so you have a continuous set of actions. You have to assume some smoothness of your function, like of your loss functions, to be able to say something. And if you don't know the smoothness in advance, then it's impossible to have the same result as if you knew the smoothness. And this is like quite surprising. Like if you do estimation, like from statisticians, they're able to do the same, to estimate at the same rates if they don't know the smoothness of the function. And the fact that you have this cost of exploration breaks this completely, but you can still do some other stuff. And yeah, another example is imagine you have bounded losses, but you don't know the range. And again, adaptation is impossible. You can see that stuff. Yeah, suddenly in the adaptation, you cannot get the same guarantees as if you knew the range of the losses in advance. And okay, so this builds on lower bounds, and also from previous work. And again, it's the same story as earlier. If you look at the lower bounds, you're going to say, okay, but this is completely crazy. This makes no sense. I don't care. It's completely irrelevant to practice. Okay, I have to imagine this crazy thing where like something happens very, very far, but okay. And so, yeah, so these bounds, I think they're really nice from a theory point of view because they lead to unexpected phenomena. It's always nice like to have some surprises. And also, like they inform us about the state of like the common assumptions that we're making in theory. They're not the right ones, and we should be looking. I'm sure there's like interesting stuff to do with like better set assumptions and yeah. So yeah, that's it for me.
Thank you. We're happy to have you here.
Thank you. I hope, I mean, it's the last talk. I'll try to do it as painless as possible. So, as Pablo said, I'm associate professor at Paris Place since 2015. I was before at Huawei for a year, postdoc in Hong Kong for 2, and my PhD was at Telecom Paris. And I'm also a bit of an intruder here because I'm actually not really AI. I'm more in the communities of data mining because I came through the community of databases, ended up more data mining, so more precisely in graph data mining, uncertain data in general, and then got into sequential learning applied to graph problems and also the data streams. So what I care about is uncertainty, and especially uncertainty in graph data. So I assume I don't have to say what the graph is. So and an uncertain graph is when you have something that you don't know or you don't know exactly in the graph. So there are a few examples of this. So for instance, if you take social networks, right? You might know the topology. Sometimes you might not even know the topology. But you might not know what happens between people, right? So to what degree they are friends, they are connected, and so on. So it's not just the link doesn't tell you Knowledge graphs are kind of the same in that you usually extract them from something, right? So that extraction might be wrong. Transportation networks or maps in which you ask how to get to point A from point A to point B are also an example because there's uncertainty. Right. So when you have this uncertainty, it becomes a bit more computationally hard. Why? Because you no longer have one single graph. You kind of have a distribution of graphs, so you have to do things over it. So there are many applications from graph querying, so asking things on graphs, to analyzing dynamics or doing even optimization on graphs. And so from my point of view, I see, and at least I worked in two ways of seeing this kind of uncertainties in graphs. So for instance, one way of seeing what kind of uncertainty is thinking that you don't know exactly what happens over graphs, right? So for instance, this the most, and I worked most on this, are if you have a propagation process, right? So for instance, a message passing or a message getting this viruses also, because we just went through this, and cascading behavior in general. So here I worked quite a lot actually in online influence maximization. I'll talk about it a bit more. Recommendation algorithms over graphs or over social network, and another kind of uncertainty in graphs. So this is more databasey, if you want, are when you have your structure of the graphs be uncertain. So the topology itself, you don't know. You associate probabilities to edges, to nodes, to labels, to whatever, right? So then there I worked a bit on indexes for queries on probabilistic graphs, and looking at data structure, even some work in provenance systems. Today, this is okay. So today I'll talk actually about a little problem that's quite well known in the data mining community, which captures both of this, in my opinion, right? Both aspects. And this is online influence maximization. So the influence maximization problem takes a social network, right? And gives some kind of budget, a promotional budget, which usually in an abstract sense is just a number of nodes on the graph. And we want to choose several, that number of nodes on the graph, so as to maximize the spread of a message passing, right? The messages that you start from these nodes. This is called also the word of mouth effect, and then these seed nodes are called influencers. So this is quite important, quite well known. It has many applications in marketing, computational advertising. It is, like any nice problem, NP hard. Why? Because it reduces to optimizing a submodular function, and there are many approximation algorithms and a lot of heuristics, because even approximation algorithms, because we are talking about social networks, large graphs are still costly, even if they are polynomial. And they actually rely on two kind of models. One is a data model, if you want, of the graph, which is a kind of uncertain influence graph, which is the graph of the social network in which you have nodes, humans, edges, their relationships, and you attach probabilities to that. Which say what? Say that if I tell this person, send a message, this is the probability that in the next time step, it's a bit discrete way of looking at things, they will receive it. And then on this data model, you have what you call a propagation model. The most well known is the information cascade model, which just goes in steps. So you start from a node. If they can pass a message, then you activate the next node, which in turn then can go over neighbors, right? And so obviously it's a stochastic model. It's an uncertain estimation because you don't know exactly what you'll get, right? Because sometimes it might even stop here. So it will generate what we call a distribution of information cascade. These are some example illustrated, and it illustrates what happens usually. In that, most of the time you will not get anything, right? So whoever is active on Twitter knows, right? You put a message, most of the time nobody cares. Sometimes there are a few people, and very rarely somebody shares and replies to your thing. So this is the, so it generally the size of these follow power laws, etc. But it's not necessarily important. Yeah. There are problems with this in practice because I'm a bit more practical in my research. So there are two problems here. One is that you don't know these things, right? So all research that has been done in influence maximization suppose that you know the probabilities, you know the graph, and you use that model. The problem is one, you don't really know the probabilities, right? Because this, how do you get them? In the sense, how do you go over everything that happens over Twitter, Facebook, etc., and extract them? Even if you extract them, how do you extract them? Is it a real probability? Sometimes you don't know the topology of the graph because you don't have access to the entire graph, right? Again, think Twitter, think the fact that it's very limited, the access that you have to this. Second is that your propagation models are cool, are intuitive, are nice, but are they real, right? There were studies that show that, okay, the cascading behavior in social networks is like the propagation model I presented predicts, but there are others that say no, okay? So what is interesting, was interesting for us was, can we get some algorithms that do not assume anything about this model? So they don't have anything, and we'll get to exactly the setting of the previous talk. So once you don't know anything, right, what you need to do is adapt, right? So you need to start from something, some kind of very like a model, either of the graph or something that you try, and then you receive some feedback, so like a loss, and you adapt to it, right? So this is a setting of online algorithms. You start from something, and they are also sequential because you cannot do anything else, right? Once you have this model, you have to try several times because you have to learn. So there are several trial rounds, and it's exactly the setting of reinforcement learning and multi-arm bandits. And you have, as said before, you have the classic exploration, exploitation trade-off. So what do I do? Do I refine the model? So do I try other things in the graph? Or do I use it to maximize my okay? And the most interesting case that occurs is when we say we don't know anything except who we want to activate, who we want to give the message, right? So you have a subset of nodes of the graphs. You don't know the graph. You just know a few persons in the graph, which you can call also experts or influencers, which have access to other nodes that you don't know, which have unknown activation probabilities, something like this. So basically, when you send a message to this node, they activate the other nodes with some probabilities that you don't know, okay? So then the problem becomes you no longer have a graph, you just have a set of nodes. You have a budget of some trials and a number between 1 and k, so the number of influencers that you influence in each trial. And also the online influence maximization is to basically solve the problem of selecting at each step a number of nodes, so that in expectations, because again, this is a stochastic case, so you cannot, you will not have the same answer every single time. you maximize the expectation of the union of all the things that you activated. Why the union? Because you don't care about things that are activated twice, because you already passed the message, right? This is a bit slightly, for those of you who are familiar with bandit, is slightly different from the classical bandit case, in which you actually you do the sum of rewards as you go in rounds, right? This is not exactly this. There are approaches that said they solved this problem, but they took just the sum of activating messages, which is not that interesting because you can just find somebody who's very popular and just pass the same message multiple times and you say, okay. Whereas in this case, what you want to do is try to spread as much as possible. Okay, so you have this. So then what you have to do at each step, because of this, because the fact that you care about new things at every point, is to estimate at each, so you have this node, you have a node, let's say, they have this node. So let's say at the first you activated 3 of them, right? You don't know how many are left, right? There might be 1, there might be none, there might be the entire graph, right? So what you need to do to maximize this size of the union is to estimate what we call the remaining potential. So how much left do I have to activate? So we also call it the missing mass. And then the cool thing is that there exists an estimator which is actually seems, at first when we found it, it seems pretty magical, but it's actually quite interesting. It's called a good Turing estimator. It's of course not used only in this, and it's used in bandits or whatever. It's used, as the name suggests, it's quite old because it's that Turing. It was used in code breaking, etc., and it was used in species estimation. So imagine that you're somewhere on an island, and you have binoculars, right? And you look at birds, right? And you want to see how many new kinds of birds, how many species of birds are on that island. So you keep looking, right? And at some point, those birds will repeat, right? So then you start knowing that you don't have anything left to discover. So it's exactly this. This estimator says exactly this. So you repeat, you see, for instance, colors, right? And you want to see what new colors you have. And the estimator says that at any point, the estimation of the missing mass is the fraction of things that you've seen once until then, right? Intuitively, why does this work? Because imagine if you have nothing left to see, you kind of saw at some point everything what you saw twice, right? So that becomes the fraction of things that you only saw once becomes 0, so you don't have anything to discover. It's slightly biased, right? But it doesn't really matter. So this is an estimation. So you would say, okay, with every step, I just take the one I get the feedback. I take the one that has this estimation. Well, not really, because again, we are in the setting of multi-arm bandits, and we have to do that exploration-exploitation trade-off, right? So we have to give ourselves the chance of finding new things, so finding other nodes that might be better than what we already discovered, right? So again, we are in the setting of multi-arm bandits. They are sequential, several trials. You have several choices in each trial among several arms. In our case, the arms are the influencers. And one of the coolest, in my opinion, results in bandits, stochastic bandits at least, is that you don't have to make the choice between exploration and exploitation explicit. You can make it implicit. And how? By actually taking your estimation, right? So taking your, taking this estimator and adding to it what we call an upper confidence bound, which is kind of a bonus that says this is the bonus for you exploring things. Okay, so, and then basically you choose at every point, you choose the influence of the node that has best estimator plus this confidence bound. And of course, this upper confidence bound is computed in depending on your estimate, right? Without going into the formula, just to say something, when we say we have an algorithm, actually in Bandit, you never have a new algorithm. It's the same algorithm. It's called the upper confidence band algorithm. And what we all do in Bandits, applied or theoretical, is figure out the estimation and figure out this confidence bound, which usually is proportional to well, it's proportional to a logarithm of the number of times and inversely proportional to the number of times you selected that. This gives you the bounds on regret. So yeah, we have this. And I said something about regret, right? Generally in Bandits, you say, okay, what I want to optimize is the difference at the time t between my optimal algorithm that knows everything and the UCB algorithm that is. Except that in graphs, in our case, regret doesn't mean anything. Why? Because any algorithm I use at some point will have regret 0. Because my graph is finite, right? So even if I do it randomly for enough times, I will activate everybody. Right? So instead, what's more interesting is what we call a waiting time, right? So which is basically it says what's the number of trial before the missing mass that's left is no longer larger than a threshold, than a fraction of the entire thing with a threshold lambda. And so of course we looked at this. So we found that of course you have to perform more activations to learn. This is not surprising because you have to perform more activations than the optimal algorithm. However, if you have a large enough graph, so you are allowed to learn, right? And if you get enough feedback, then this algorithm is competitive with the oracle. So of course, experiments works better than baselines, and notice that we are never comparing the regret. We are actually comparing how much the cumulative spread, the cumulative number of messages we have for trials, right? Then we can add to it also context. What does context mean? It means that you have the node and you have a message, right? So you say something. So then each influencer is associated with the context. So the feature vector, which is an RD. So you can get that from whatever you want, right? Bag of words, embedding, whatever. And the reward depends generally linearly on the message that's received. We can even say adversarially, so you don't have any control on the message that gets sent. And usually your reward, so the thing that gets transmitted, you get as a feedback, is the linear combination of the hidden context and, well, I think I inverted the context and whatever, and the message, plus some noise. Why do I add this noise? To add stochasticity to it, right? Because otherwise you'll have the same. So, of course, then what you do, your estimator becomes something that's a least square estimator. You add upper confidence bounds to it, right? And this is the setting of many algorithms, which are called contextual linear algorithms, like LinUCB, linear, etc. In our setting, it's a bit different because my linear reward what I do with my linear function is actually change the unknown probabilities of each node. Right? So I have some kind of function that in a way captures the fatigue, so the fact that you get diminishing returns with the number of messages, and because this usually the number of new nodes that you influence tends to increase. So then here we had we adapted two algorithms. First of all, it was the algorithm that we had before, but we added a linear model to it, assuming that the rewards follow a Poisson distribution, because a Poisson distribution is a distribution of counting things. And why is it a generalized linear model? Because you're actually not learning, you're not doing direct least square regressions, you're doing Poisson regression, right? So you're basically learning using what's called a link function for Poisson alpha. This function is the exponential function. Another way to look at it is that you assume also that your rewards, so your number, are log normally distribution. So basically, this means that you predict no longer the exact number, but the scale of your spread, and you basically can keep more or less the same theoretical bounds of the original UCB algorithm. And of course, these are confidence intervals, but I think the projector doesn't really manage to show them. So generally, well, for now, we saw that they work. One works in some cases, and the other works in some other cases. Okay, so and we recently also looked at applying this with reinforcement learning, and here I think I can answer the question you had, because there are actually things that use UCB-like approaches for reinforcement learning, especially reinforcement learning with linear function approximation. Q function is you basically can approximate it like this, so that basically you use the LSVI algorithm, which is least square algorithm, to get this, and you add a confidence bound, and there's the same notion of regret even in reinforcement learning. So there are some things, right?
So provided that you manage to approximate your model as a linear, then you can go back to this.
Yeah, then you can basically use, more or less, you use the results here in linear bandits, because then you basically, I think it works because you no longer have, well, you basically hide the states in this reward function, right? Because in your in the how to say, in the context that you send. So okay, so what do I want to say with all this? Is that, well, bandits work even in practice. So they don't have to remain purely theoretical. And in this kind of problem, which might be a bit of a toy problem, but it's an interesting problem, it shows that you have potential in even simple model-free sequential algorithms. So they are simple, they are efficient, right? Because I just showed you this algorithm. What does this algorithm do? Well, never mind the linear one, which has to do regression, but the initial one, well, it keeps a number, or it gives a set and it keeps a fraction of those things, and then it computes this. That's it, right? So it's extremely efficient, and it works quite well. And generally, I mean, as I said, you have the same algorithm, right? UCB, you add, but you can make it work, but by taking your problem and finding an estimator that works very well, right? So it was an example of this. So in my opinion, so this can also lead to, for instance, taking a lot of optimization problem on graphs, especially optimization problems that depend on kind of stochastic return using sequential algorithms. And since they can be efficient, I really ask myself, in a lot of applications, do we really need more complex approaches, right? Even if, and I'm including here reinforcement learning, right? Do I need states? Do I need all this? Because, you know, those of you who worked with reinforcement learning, you know that it's extremely data hungry, right? So you have to do it 10,000, 15,000 times or even more, right? These things can work, and they actually do work in practice because bandits are used in everything from ad allocation to well, generally in ad allocation to placings to whatever, right? Spam, spam filter sometimes. So yeah, this is what I care because I think it's a subset of things that we can do, and it maybe links to Anne-Laur's, who's not here, talk more efficiently, more succinctly, and when you have access to only to limited data, or you have only limited space to do things. Right? By the way, this is I'm already working on this on the France-Singapore project, which is with the lab that's the equivalent of ILLS in Singapore, and this is a CNRS project that. Oh, it's a big project, but my part deals with this, and we're actually working a bit on space bounds for reinforcement learning. This would be for me. I think I made it more or less in time.
Thank you. Questions?
Yes.
I was wondering if this kind of formalism could be used to explain, to constrain deep models or maybe graph neural network models or.
Well, I know that there are.
You know if it's.
Well, I know.
Or if it is.
So I know that there are recent papers on optimization problems on graphs which use reinforcement learning and use graph learning to basically learn more or less heuristics on graphs. So for instance, imagine that you have a hard problems on graphs, right? You can use reinforcement learning approaches to give it examples of solve things and make it learn the heuristic to solve it. Right, so how to choose? I think the examples were for the traveling salesman problem and classic graph problems, and it's actually a quite recent thing. I think the first paper I saw was 2020 or something. So and I think it used DQN, if I'm not mistaken, so the deep neural network-based Q-learning, reinforcement learning. So that there are things that start being looked at. But I still think that maybe it's not needed that much because again, if you're using neural networks, you have to train them, you have to give them a lot of data. Maybe there are more simple ways to solve this problem.
Any more questions?
Yeah.
Is there any assumptions on how the connectivity is distributed in your graph? For example, that's, most nodes are connected to very few other nodes, and then you have some nodes that are connected to a large number of nodes. Did you consider this kind of a...
Well, I mean, I think it's implicit, but what these things, well, we're going maybe a bit... this thing only works well if you have outliers in the probabilities, right? Because if you have uniform probabilities here, you don't need all this because so basically you have to have some nodes that are very hard to activate, right? That you have to keep trying. This corresponds to generally to I mean, generally, this means that you kind of have to have a topology that's like a social network, right? In which you have, you can access a lot of nodes quickly, but a few nodes you have to go. Right. So basically, it's implicit, but.
And this diagram is simplified in the sense that it's not always a single hub, right? You could have.
Well, no, you have several. These are the hubs, right? That you know.
I mean, the distance between an influencer and any node is not always one. You can.
But that's the thing. We simplified the model because we said reaching it, no matter where it is in the graph, has this probability.
Oh, okay. I see. Right. I get it. So you collapse. Let's say.
Yeah, we collapse basically the entire graph in a few trees. This is a bit misleading, and we kept it. But actually, to be able to analyze the thing, you kind of have to have them independent also, right? Experiments, they were not independent, so there could be nodes that can be activated by two. But to be able to, those of you who did some proofs in this, you know, usually you have to get rid of the things that are too messy and to have something that's reasonable. So basically, technically, you assume that they are disjoint, right? This who you can influence. In reality, it's not the case. Okay.